Okay. Welcome everybody to this second workshop on human-centered AI, which is the appointment of the Spoke One group of the FAIR project. It's a pleasure to welcome everybody and also the authorities that are with us to launch this today workshop. As you know, FAIR is a big nationwide Italian network of research centers operating on developing the future of artificial intelligence research. 10 spokes that are distributed across Italy and coordinated by a foundation which is called FAIR. And our spoke one that is based in Pisa is focused on among the many facets of AI on human-centered AI. Together with myself, Francesco Marcelloni is leading the spoke. Francesco is arriving a little bit later for health issues. The partners of this spoke are, besides my University of Pisa, who is the leader of the spoke, is the National Research Council with two institutes of Pisa, IIT and ISTI, and Scuola Normale Superiore. Together with two industrial partners that are with us since the beginning of the project, Banca Intesa San Paolo and Deloitte. During the last year, new academic partners have been affiliated to our spoke. You will be listening today of the advances of their research together with us in the spoke. And they are Università Cattolica del Sacro Cuore di Milano, Università di Siena, Università di Firenze, Scuola Alti Studi IMT Lucca and Scuola Sant'Anna in Pisa. It's as you know, I will only take a few minutes to frame our research and our ongoing project. Our focus is on human-centered artificial intelligence, this European view that has been developing over the last 10 years, which sees AI as a technology that is geared towards human needs, towards the ability of developing a hybrid human-artificial intelligence that is respectful of human autonomy and human rights and the ability of empowering people. So this is, in short, the manifesto of human-centered AI, which is a study of systems that cooperate synergistically, proactively, and purposefully with humans at different scale, at individual and collective scale, with a main aspect is amplifying instead of replacing human intelligence, maximizing benefits while preventing and minimizing, mitigating risks. So the kind of adjective that we like to see together with artificial intelligence is, there's a short list here, is adaptive, collaborative, responsible, interactive, co-evolving. Technology that is capable of evolving together with us in a way that these systems are able to leverage human strength, human intelligence, and compensate for the weakness of human intelligence while respecting human rights and within a context that takes into account society, ethics, and law. Really the focus is developing tools that are able to enhance the ability of people to take important or potentially risky decisions, like in healthcare or in jurisprudence. No? The point is not replacing, the point is empowering and having a kind of approach where the hybrid artificial human intelligence is better than artificial intelligence alone and human intelligence alone, which entails developing, designing a new generation of AI systems that are aware of their own limitation. They know when can be trusted, and they are able to somehow give advice to human when there is a difficult case to handle, when there is some reasoning that is needed. In a way, we might call in Italian these systems macchine per pensare, thought partners that are able to co-evolve with us, creating better and better abilities to tackle difficult decisions. And we are aware that this, the design of our very ambitious FAIR project occurred concurrently with two huge game changers that entered the picture during the last few years. One is, of course, the generative AI, large language models. No? A new generation of systems able to create artificial content that, of course, is creating more and more opportunities and also more and more risks, because we should always remember that producing human-like content doesn't necessarily mean to be human-centered. On the opposite, this could also be easily served to manipulate, for instance, humans, or to replace humans in certain jobs, like writing news articles. And the other big game changer is the first systemic law on the AI market that was launched by the European Union and is under the implementation now, with a big impact on the way we audit, manage, and design AI systems. And I must say, even if these were a big disruptive events during the last few years of AI research and innovation, our scientific program anticipated these novelties, so this kind of new topics are very well dealt with within the scientific program of our spoke, where our general research questions are about human-centered machine learning and reasoning, so developing models that interact and co-evolve with people, how to understand and manage human AI ecosystem at scale, at societal scale, at community scale, and how to responsibly design a new generation of trustworthy AI systems that are compliant by design to the European Union regulation. And of course, all this is being pursued by many experiments, case studies, and pilots of this new wave of human-centered AI techniques. We are many people working on this, and actually we started in 40 multidisciplinary scientists from 9 different departments of our universities, 2 CNR institutes, 2 classes of Scuola Normale Superiore, and then we expanded by many ways, by integrating other colleagues from our institution and beyond the new academic institution and the industries. We hired more than 40 young researchers, 17 researchers, 11 PhD students, 13 postdocs in all the 3 institutions. We broadened the FAIR partnership through cascade calls. We're able to fund 6 projects with the new universities that I mentioned earlier, 2 projects running with the industrial partner within the Innovation Grant Initiative, and a cascade call for new small or medium companies that are being selected these days, and their projects are starting now. I just want to give you a little numbers to show how much activity we have been pursuing in these first 2 years of the project. We have these big numbers, more than 120 journal papers together, 168 conferences, 43 book chapters, a productive publication production that is steadily increasing and steadily providing more and more collaboration among the many teams involved. Just to somehow to see how this activity is really very much let's say strong. If we consider the total amount of publication up to now, they're already more than almost double the target that we set at the beginning of the project for the end of the project. No? So it's an interesting outcome. Also taking into account that most of this publication activities is done with top or A-level conferences and the best journals of our sectors. The first tier of journal publication. We have also quite robust co-authorship with researchers of many institutions around the world. Almost 40% of our production is co-authored with colleagues from outside the spoke, from many, let's say, high-level research centers, universities, and industries. An industrial co-authorship which is meaningful but yet to be improved, and a strong emphasis on multidisciplinary research application and beyond. There is also a steadily increasing production in terms of benchmarking data sets for benchmarking and developing AI systems. Many delivered concrete systems for human-centered AI innovation, more than 60 deliveries from this point of view, and a lot of activities from the point of view of dissemination in terms of invited keynotes, panels, and many different forms of dissemination events that also show a very good participation of female researchers and female participants. Of course, there are rooms for improvement, both at the level of scientific work and administration. It is a very complicated project from the point of view of administration that requires a lot of effort from both technical staff and scientists. But certainly we can improve with the collaboration with colleagues of other FAIR spokes and the transversal projects, both in terms of publications and joint PhD thesis supervision. And also we can improve for the outreach to general public, especially events that are related to gender issues and female researchers' valorization. You know, this lineup of speakers shows that still something that we can do better concerning gender better equal representation. But one thing I would like to mention is that it's just news from 2 days ago on 8 March, the International Women's Day. Fosca Giannotti, who was the coordinator for Scuola Normale Superiore in FAIR, was awarded by Regione Toscana of a prize, of an award for her professional career and her story of female protagonism. One final aspect I would like to mention is we are also, as a spoke, as FAIR scientists, we are organizing here in Pisa next June, 9 till 13 of June, the 4th edition of the International Conference on Hybrid Human Artificial Intelligence, which is a somehow a very natural venue for the research that we are collectively pursuing. Our researcher Chiara Boldrini and Luca Pappalardo are the program coordinators for the program chair for this conference, and this will be for sure a very important showcase for the research that we are pursuing. This workshop has a very rich program, 35 highlights for the different work packages, 20 posters, more than 150 participants registered online and will be present either here or online. We have a young researcher panel, an innovation grant session, a transversal project session, and of course also a session dedicated to our new academic partners. As you see, the agenda is very packed, so I don't want to use more time. I just want to say thank you to the people that worked hard to organize this today, so I hope you will enjoy it. Last year it was a refreshing gathering with many ideas. I hope that this year will be analogously so. And the thanks especially goes to Francesco Marcelloni, Mattia Setsu, Camilla Sovani, Vittorio Romano, Stefania Pasqualetti, and Daniele Fadda, who really helped a lot with this organization. And of course, also to the work package leaders and the presenters for today. So thank you very much for being here. And I would like to give a word to the representative of our institutions, starting with Professor Giuseppe Iannacone, who's the pro-rector of University of Pisa.
Thank you, Dino. Thank you, Dino. And here we are again. I was here last year to also, as this year, provide you the welcome on behalf of the University of Pisa. And I'm also very happy to hear about the interesting and impressive, I would say, results from a quantitative and from a qualitative point of view that the whole group has obtained in the course of the project. So congratulations to all of you for the work that you have done. Congratulations to Fosca for the recent award. Very recent indeed. And boy, how things have changed in the last year. Because, I mean, things in this field are moving extremely fast in industry, extremely fast in society, in intergovernmental organizations. And, of course, this, I assume, is posing a lot of challenges and a lot of questions to all of you. Because even if one of us focuses on fundamental aspects of AI, or on applications of AI, in any case, all these changes at the industrial level and at the intergovernmental level are extremely important. And there are important questions, I think, that also for this community are important. And I see they are considered in the program of the partnership as a whole. For example, I mean, this year, the global investment on AI, on hardware for AI, data centers, and so on, is going to be about $250 billion. And it's a lot of money. It means that things are moving extremely fast. But on the other hand, we really have to understand what is the impact, what is the economic impact, industrial impact, what is the return on the economy, what is the return on societal organizations, on the work of all of us. And I mean, there are more questions than answers on this point. I'm really happy to see that in FAIR, there's a lot of space. I assume, especially in the last part of the project, on experiments, on use cases, on pilots, which I think are extremely important to really understand something about the impact that this progress in the field of AI, of generative AI, and adjacent fields can really have. I think also from the academic point of view, I mean, this fast progress poses some questions of other type. I would like to say more fundamental, because it's really hard as an academic group to be effective and to have impact when things are moving so fast. As academics, we're really in our best situation when we can work on things that are a bit far away, I mean, that are going to happen in the medium to long term. But when things change so fast, I mean, it's really hard to have the capacity to have impact on what is going on. I'm happy that you have these collaborations with non-academic organizations, with companies within FAIR, and that some of the algorithms and of the use cases that you're working on are actually really focused on short-term and let's say applications that are very close to what is of interest now. With this, I wish you a very productive two-day workshop and continue in this way. Thank you.
Dr. Marco Conti is who is the coordinator of the scientific board of the FAIR project.
Thank you, Dino, and welcome to everyone. It's a great pleasure for me to welcome you to this workshop on behalf of the FAIR Foundation and its scientific committee that I have the pleasure to chair. And as a FAIR, we think that we have pushed a lot to have this kind of workshop, this second year workshop, because we believe that these events are fundamental for several reasons. Okay, now we are almost close to the end of the project. We are about 1 year far from the end of the project. So it's the time, the last checkpoint that we can have to evaluate the status of the quality of the research that is carried out inside the FAIR in general, and in particular in Spoke 1 of FAIR. And now, as also Dino said, we have significantly enlarged the partnership of FAIR. We started with 25 partners, and now we are more than 140 partners. So we have included 53 additional university and research centers, and almost the same, and more than 60 companies, and more companies will join the project soon. So now we have really created an ecosystem, an AI national ecosystem around artificial intelligence. But okay, we have just 1 year to finalize and to achieve the result that we promised when we launched this program that is very ambitious. So the workshop is very important to check the status of the project, to define a roadmap toward the end of the project, and in order to also to guarantee that the result that we have planned, we are able to achieve those results. And this is very important for another reason, because this is not a project as usual, that at the end of the project everything closed and we have done. If we have achieved the result, we are very happy, but the project after 3 years closes. This is not true for this case, in this case, because in the reality, one of the objectives of this kind of initiative, national initiative, is to create an ecosystem. In particular for us is an AI ecosystem that should survive after the end of the 3-year project. As you may know, there are already initiatives at national level to put some additional money for guarantee that the project, that the activities of this project can continue, maybe in other forms, under other projects, but there are some money available that the government have already put in the national budget to push or to sustain this initiative. And this is very important also because just in FAIR, we have recruited more about 400 junior researchers, and we wish to guarantee them, or to almost of them, a future in this AI ecosystem. So we need to survive beyond the end of the project. But to achieve this, there is a very important question that as a FAIR Foundation we are asking to all the spoke. And this is the question that the ministry and the government is asking to us. It is, what are the main scientific results, the main objective that this project has achieved, given the huge amount of resources that the government gave us? I remember you that we received more than 100 million euro, which is a huge amount for a research project in Italy. So if we wish to survive and to sustain this effort, it is very important that from a workshop like this, we are able to observe and to say which are the key results that we can show to the ministry, to the government, to justify the fact that it is important that this community will continue to exist after the end of the project. So we have a main question for all of us during this two-day workshop, and it is to answer to the question of which are the main results that we are proud of and that we want to show to our institution to justify the need that they provide additional support to us to guarantee that there is a future for this AI ecosystem. And I would like just to conclude, say that this is a unique opportunity because having this huge amount of money to build an ecosystem, it's been a very rare event in the scientific scenario in Italy, and there will be no another opportunity in the next medium term. I'm not expecting that there are other resources soon. So we must try to exploit at the best this opportunity, showing that, that we have been successful, that have been able to achieve what we have promised, and possibly even more than that what we wrote in the project. And so this is very important. So the expectation is that at the end of this today, we are able to have a set of results that we can present soon to the Ministry of Research to justify that the need that this community must survive. We need support for continue our activities. So this is conclude my brief introduction as the chair of the Scientific Technical Committee of FAIR, and let me just add a few words on behalf of the institute that I am part of, because the director of the institute cannot be here, Andrea Passarella, cannot be here due to an health problem. So he asked me to, on behalf of the institute, to give a welcome to all of you, and also to remark that artificial intelligence is one of the key research areas of the Institute. I would say the main research area of the Institute, according to a recent survey that has been conducted inside the Institute. And therefore, FAIR from one side as a research program, and the Italian National Research Program on Artificial Intelligence that are working together in a tightly coupled way, because most of the junior researchers that we have recruited in FAIR are also part of the national program, so there is a tight connection between the two initiatives, and these two initiatives are the key initiative for the Institute of Informatica and Telematics inside the artificial intelligence area. And we are also already working to look at the future of this area, and inside the CNR, we are promoting an initiative that is looking to pervasive intelligence, which is putting together artificial intelligence with the future of 6G network that are not anymore a pure communication network, but a distributed intelligence system. So we are also working toward the future, and therefore, for us, the result and the activities that are carried out inside the FAIR are of great interest, and therefore also from the Institute standpoint, I wish you a very fruitful workshop, and I hope that this workshop will be successful in terms of a result that it will be able to produce and the result that will emerge from this today's discussion. Thank you for the attention.
Professor Paolo Mancarella, Director of Computer Science Department.
So welcome everybody. I'm very glad to be here because, you know, everything started when I was rector, and the FAIR project was starting, you know. We had a lot of phone calls, of meetings, etc., and I pushed very hard for UniP to be involved in this big project. And well, I've seen the presentation of Dino, and I'm not amazed, I'm not surprised of the great success of this project up to now. And you know, Pisa and all the institutions involved in this project in Pisa, University of Pisa, CNR, Scuola Normale, Sant'Anna, IMT, etc., are a network, an ecosystem that has been built during the years. And everything started here. Many years ago, computer science was born in Pisa, in Italy. So this is not surprising. We have very, very good researchers. We have top-level researchers. So someone can be surprised of all these publications, high-level quality publications, etc. I'm not. I'm not, because this is what we are. This is what we have been during the years, and I hope this is what we will be in the future. Artificial intelligence, you know, we hear about artificial intelligence every day in television, radio, and discussion, etc. But most of the times not in a proper way. So one of the I think one of the most important things that we have to do is to disseminate from a scientific point of view, and we are able to do so, what AI is really, okay? And projects like this and network like this one can help a lot in this. I don't want to take your time. I have to be in 10 minutes in another event here, so let me conclude by thank you all to being here. I hope you'll have a fruitful workshop. I'm sure you will. And last but not least, congratulations to Fosca. Well, Fosca, I know you don't want to be congratulated, but we know each other since 40 years, so is the minimum. So I wish you a good workshop, and welcome to our university. Bye.
Professor Luigi Ambrosio, Director of Scuola Normale Superiore.
So, welcome to you all to this workshop. Well, a lot has already been said, so let me just add a few historical remarks as on the line of Paolo Mancarella. So the Scuola Normale has always been very happy to collaborate with the other institutions in Pisa, National Research Council, University, Scuola Sant'Anna. And I think in this area of research, everything started with the PhD program in data science, which initially was placed in the Scuola Normale, but then this project evolved very well into a national PhD program now coordinated by Pisa University. Then came the Next Generation EU, then came this project. The Scuola Normale opened to computer science with the arrival of Fosca Giannotti here, and also, of course, in the Scuola Normale there is a lot of interest in this topic, and also, I would say, a lot of this interdisciplinary collaboration. So among our students in science, mathematics, physics, biology. There is a lot of interest in this area, and so many more opportunities. So I wish you a nice meeting, and thank you.
Thank you. Dr. Roberto Scopigno, Director of CNR.
Thanks a lot, Dino. Thanks for inviting me. I'm very glad of being here with you and to open these events. I will be very briefly. I want just to underline the very good quality results, the number of KPI indicators that have been raised by Dino in his presentation. And these are, by the way, a first reply to the comment given by Marco Conti of the importance of this third year, which should be a year in which the very good work done in FAIR and in Spoke 1 of FAIR should become very visible and should bring to a very successful comparison with other projects, other PNRR projects, and to contribute to the future of this line of activity. I don't want to spend words concerning the importance of this topic of research, which is also of fundamental importance for my institutes. It's one of the topics on which many people are active at ISTI. And I have just a small message maybe for the younger. Either because I participate personally to another PNRR activity and also because of my role of ISTI director, so I am following several PNRR activities, I should say that I do not see the same level of interactions and coordination that you have here in other projects. In many cases, other projects are just activities in which research labs work alone in a separated manner and then send the results to the coordination of the project. Here, the impression is that it's a real project with a real community working together. The fact that you are in the second year of the workshop is a demonstration of that, because in other projects, I remember I have in my mind a single case, for example, in which we had the first workshop of the entire PNRR activity just a few months ago, and you are in the second edition. And I think it's important to keep this level of interaction between groups. It's important to have a working workshop in which you gave presentation, not just poster-based activities, in which there is some discussion, some interconnection between the work of all the groups. So I think you are on a very good level of activity, and I am very confident that the result of assessment of this specific research activity will be highly successful, and I'm looking forward. Good work.
Thank you really very much for these contributions. We can now proceed with the program. We are late, of course. We started late, and therefore we are late. But now it's the first session dedicated to the work package 1, Explainable AI for Synergistic Human-AI Collaboration. It will be chaired by Fosca Giannotti and Riccardo Guidotti. We postpone by 15 minutes the coffee break, so we'll have a buffer to...
Siccome c'è il presenter a pulsantino, potete rimanere seduti, tanto la vedete e vi passate questo, capito? Ognuno presenta dal suo posto. Cosa cambia? Però poi dove... Dal telecomando, sì, sì. Il primo è Lorenzo, io faccio da qui. Vai. Okay. Yes. Good morning. I'm Riccardo Guidotti from University of Pisa. I am the co-leader of the VP 1.1 Explainable AI for Synergistic Human AI Collaboration, together with Professoressa Fosca Giannotti from Scuola Normale Superiore. Since we want a successful workshop, we need a successful coffee break session, and therefore we will try to shrink a bit this session. Okay, I will start to summarize a bit, but I want to remember to you which are the objectives of the first work package. So 3 objectives. The first one, we want to study methods, models, and algorithms for conversational explainable AI. So to study the way we can interact with these machines, the way we can argument, we can have feedback from this kind of machine. And we will see in the first highlight that we have selected a, let's say, special way to interact with this kind of AI models. The second aspect is the content of this interaction. That should be mainly the explainability part. So how these models, these algorithms can justify the decision they make, both in a factual and counterfactual way, but always staying at a high level, okay? In a way they can generalize the way they take the decisions. And finally, we don't want only machines that are able to take decisions, but only machines which are, in a certain sense, introspective. They know when they are not able to take a decision, and they are able to defer from the decision to a human or abstain to the decision. And to reach these objectives, we must face 3 challenges. The first one is obviously to open the black box. We face this challenge in 2 tasks. In the direct way, let's say, explanation of AI black boxes and the design of models which are interpretable on its own. And the idea is to put the user in full control, making the user aware of why not, what to change to have a different outcome. The second challenge is to habilitate a loop between algorithmic and decision making. So what I was just mentioning. So the models we design should be able to defer their decision, should be able to know when they are failing, when they are not good enough, when the human is not good enough, to establish this communication, this connection between the two, such that they can co-evolve, both in the learning process but also in the prediction process. And finally, the third challenge is the design of AI system based on cognitive theories. So the importance of the interaction, the way we interact with these machines, it's even more important than the way we interact with another human, because when 2 humans interact, let's say the interface is more or less the same. It's not always said, but with a machine it's much more difficult. And that's why we need to be aware that there are these 2 systems we have and that also the machine might have. Just a bit of, let's say, background for the next coming presentations and the next coming highlights we have selected to show you how we decided to cover the 3 challenges. An XAI taxonomy that is covered by the 2 tasks. So when we have a black box, we can either decide to build an explanation subsystem on the bottom, so a system that is working in parallel and is responsible to explain the model that remains a black box. While on the top we can see explainable by design methods or interpretable by design methods. In this case, we want to put aside the black box and replace it with a white box or a transparent box, or at least a gray box, where the reasons for the decisions are accessible together with the mechanism that takes the decision itself. And still in the taxonomy, we can distinguish between global explanation when we unveil the logic of the entire model, and local explanation when we explain the decision for a single instance. In the presentation, we will see both of them. The overall focus of the community is on local explanation, but we have also some novelties to go from local to global. Then we can distinguish between model-specific and model-agnostic explanations. In the first situation, we are in the post-hoc scenario, so we have the black box and we want to explain it, and the black box is a specific model, either a deep neural network, an ensemble method, a convolutional neural network, and for the explanation process we are using some of the insight of the box. While a model-agnostic tool can be used on any kind of model. Our research are showing that obviously model-agnostic approaches can be used in any scenario, but for specific case studies, it's perhaps better to refer to a model-specific approach. And finally, which are the type of explanations we used in our research? The first one on the top left, feature importance. So we attach a number that is telling us how important is a feature for a certain decision, can be positive or negative. If it's close to 0, it means it's not important. Then we can have rule-based explanation expressed in a logical form, which is quite close to the way we use to explain why we decided something, maybe having a bit more constraints than feature importance-based explanations. And finally, counterfactual explanations, showing us what we should change to revert the outcome of a certain model. And here we have the classical example of someone asking for a loan to a bank. So this is the outline of the remaining part of the presentation. We will have, let's say, 5 main contributions. The first one is able, the way we championed to show you how we can interact with a machine in a full and complete sense, I would say. The second one is, let's say, a medley of works we did in healthcare that is a quite important case study for all the research teams involved in VP 1.1. And then 3 models and algorithms addressing in different ways the problem, let's say, of moving from local to global the explanation. That is a limited study in the XAI community, but it is an important one because in the end perhaps we want an XAI tool that can give us the overall global vision of the decision of the model. And finally we will have some conclusion summarizing the results and showing briefly what have not been highlighted by the highlights. So without further ado, I leave the floor to Federico and Lorenzo.
Thank you, Riccardo. And let's start with this part of the project, of the work package. And we mainly try to answer to a question, which is what happens when an AI has a body and can interact naturally with us, so in a social context, in a real context. And to explore this, we built a robotic platform, which is mainly based on Abel, which is the very realistic robot that you can see in the picture. And with this approach, we use a human-in-the-loop approach because all this architecture is designed to collect data from the subject which is interacting with, and this ensures that AI behaviors are not only safe and effective, but also truly designed to a seamless collaboration with humans. And I want to underline the fact that we call this an empathetic HRI, so human-robot interaction, because emotions are ubiquitous and pervasive in all the systems. So we assess the psycho-emotional state of the subjects. We have internal emotions of the robots that guide decision-making and behavior, and we embody these emotions, meaning that the robot can express if there is an emotional content is in its interaction. Of course, to do so, we have to go beyond some narrow approach. Of course, this slide is provocative, meaning that we solved, in a sense, a lot of problems. We've solved, I mean, that we have a sufficient level of reliability in certain aspects, but we need to pass from this approach to a more holistic, let's say, AI. And to do so, we have to solve a lot of specific problems, so perception, communication, reasoning, and control. This will be deepened by Federico. To do something like that, so to provide some information from the context, to let's communicate and integrate this information together, reason on this multimodal information and control this information in a sort of human brain. So I leave the floor to Federico.
Thank you. So in order to build this kind of system, we needed to rethink and redesign all the cognitive architecture of the robot. And starting from the perception part, we needed to redesign a perception module that had the person in the center of the design, in a way that is very different from having like a fleet of machine learning models that takes the input, and each machine learning model gives some output, and you have all this output and you put this output into the system. No, we wanted to build a system in which we have ontologies, in which we can control ontologies, and we use the machine learning models to fill the gaps between the classical approach on this kind of problem and a machine learning one. And so, for example, for the visual part, we have an object detection module that detects human beings, and the human beings get fed into an ontology defined in which a human have a face, has some kind of expression, have an emotion, have an identity, and all these kind of fields get augmented by other modules. Some of the modules may not work, some of the modules will work, but we don't care that all the modules work, because we have this ontology of a person that can be enriched as the model produce their output. And the same thing we did for the auditory perception. So we have an auditory processing pipeline in which we can do voice activity detection, and from the voice activity detection we can select the speech. From the speech we can do speech to text and prosody analysis to extract the emotion of the speech, but also we can do voice identification, and we can match the information coming from the visual processing system and the auditory processing system to enrich the same person. So this model goes from something like this, in which we have a person, another person, a face, some smile, some stuff in some places, in a more coherent and enriched representation in which we don't have a person, but we have a Federico, and I'm doing something and showing something to someone else. So we have this situated and augmented perception. But we also needed to rethink and redesign the planning, because in this kind of system, we have a system that is planning some action to do. For example, the human starts speaking, and the system decides there is time to reply to the user, and so decide what to reply. But the inputs can change, so the context can change, so some information from the perception module can arrive to the planning, and if these information are very disruptive, the planning needs to be retaught. And the problem is that this is a distributed system, so we needed to find ways to roll back and revert the spurious states produced by the previous planning. And so we designed an algorithm and a framework to do that. By the way, we are going to release this framework as open source software in the next months. But this software, what it does is that we have a distributed system in which there are a lot of inputs coming from different modules, both externally, so the perception module, both internally, like emotion module, emotion states of the robots, and we need to merge all these states in order to produce a coherent and always replanned series of action and planning of future interactions. But we also needed a way to control the system, and so to control the system, we takes the output of the perception module and gives this output both to the inference engine that is completely artificial intelligence based, and both to an expert system in which we can define rules. And of course, the form of these two, the perception is different, because the inference engine sees mostly text and the expert system sees facts. But the expert system can stop, can revert, can roll back, and can stop the propagation of events based on rules. So the rules that are in the expert system, we can be sure, 100% sure that will be followed. And so we have these two words that can interact together and work together. Sorry, I forgot about. We also had a huge problem from a communication point of view, because since we work in a very distributed environment, we need to face challenges on how to make the module communicate across different data center and networks. And so we also developed a framework mostly inspired by ROS2 that solves all the networking problem, like NAT traversal and this kind of stuff.
So to conclude, we designed and built a platform and we made it available to the scientific community to measure what is the perception and the impact of AI once is in our real world. And our vision is to move beyond this rigid vision of let's say, one-size-fits-all AI systems to produce an AI that is not just functional, but is socially attuned. So is to create a deeper synergy between technology and human experience. So human-centered and human in the loop at the top level that we can imagine. Okay, thank you.
Okay, just a sort of deep discussion of some of the use cases that we have, let's say, tackled within the the work package. And let's say, besides all the different use cases and methods that have been used, we try to focus today just to make a specific discussion of use cases in the healthcare sector. Of course, let's say many, okay, this is just a selection of the use cases that I will present. And I will try to highlight some of the dimensions that Riccardo was presenting at the beginning. So how the human-centered approach is enforced, which type of explanation are used, which type of transparent or black box models are employed for each one of these. Let's start from the first one, that is about skin lesion classification. This is a use case that we tackled as a public challenge organized yearly by an organization capturing and, let's say, providing skin lesion dermoscopic images, like a few examples that you can see here on the screen. And this is a task of, let's say, helping the clinician to find out the classification of each one of the case on the base of the images that the black box is collected. Of course, as you can imagine, it's just a matter of having a huge library of cases that can be used by the black box to provide an explanation. I'm not going into the detail of the different cases, but let's say they are arranged in a way where, let's say, there is, from the same type of lesion, there is a benign and a malignant one. So we have a black box that is trained, that we train, that is, let's say, compatible with the state of the art, that is able to provide an explanation, a classification, sorry, given one image to be classified. So what we did was to build all the explainable AI environment within by creating, let's say, I'm just showing you the final result, but creating a post-hoc explanation system that is able to provide context, so exploiting the local nature of each single case, providing, let's say, additional evidence, let's say, on the type of reasoning that the black model is taking. In particular, the type of interface that we chose is to use exemplars and counter-exemplars. So, okay, I do not have a pointer, but on the bottom you have a set of prototypes images, so images that are similar, and the black box is classifying according to the previous one. Just think as linking to what Dino was saying at the beginning, having a machine that helps on reasoning on cases, like a team of doctors, each one of them bringing a case that he saw in the past. So bringing more, reinforcing the classification for the prototype, and also providing a counter exemplar. So what should I change to the image, or an image that you can see is quite similar to the original one, but has a different type of classification. Of course, there is not a direct, at the moment, let's say, pointing on which are the difference of the different image, but the doctor reconstructs in its internal model the differences and is able to, let's say, build trust towards the model that we have. This was also a very interesting work because it was based on a real user study evaluation of the interface and of the type of the output of the explanation. Another interesting use case that is still ongoing, so on top of which we are still working, is the evaluation of prostate cancer lesion. Here the medical problem is the following. Given a patient, a clinician have to decide to give a grade to the lesion. At the moment, the very resolutive option is to make a biopsy, so making surgery, extracting a piece of tissue, and so on. So here the challenge is to try to support the user in this kind of classification by using images, so less invasive, let's say, exams on taking this decision. And here the scientific challenge are a lot, mainly because we have MRI images, so in principle they are multidimensional. You can think like cross-cutting images of the human body. They are coming from different type of imaging systems. You can see the free image on the left of the slides. So because these are the type of image that the clinician have to look and when getting this type of decision. And plus the doctor has all the interview surveys that is making with the patient. So here the challenge was to bring all this type of information to the black box that is able to, that should mimic the doctor on observing multiple dimensions and taking the final decision. This is the type of model that we implemented. I'm just going very quick on this slide, but basically it's a combination of different neural networks specialized in image recognition, classification, and segmentation, and a tabular classifier for the history of the patient itself. Everything is combined into a single model that is able to provide a very accurate prediction on this. Besides, of course, this model, as you can see, is quite complex in its architecture. The second challenge was to bring also an explanation on the type of output of the model itself. As you can imagine, there are, as I showed, there are different levels of complexities, different images, different dimension within the same type of exam, different nature of input, images and tabular data. So all this information that are used on the model should be also evident on the explanation interface. And here you have one of the first prototype, final prototypes that we are using, where we are combining the three different basic images, the first three black and white images here, plus additional, let's say, augmentation of these images by using explanation based on saliency map in this case, and some, let's say, annotation. The red zone is the interest zone that, let's say, usually the doctor look at, so where the prostate is located, basically. Another as you can see, these are all tasks based on image, also for this selection. Another one challenge that is still ongoing is on blood cell classification. So given a set of images, try to identify different types of cells within blood, and giving also let's say, grade on how much they are, let's say, in standard form or they have completely functional. Well, I'm just not going into the detail, but here the point is that, again, we have a black box model that is able to provide a classification for a specific blood cell, but here we try to build the exemplar and counter-exemplar also with the support of the clinician, not just by presenting, as I showed in the first task, exemplar and counter-exemplar as they are extracted by the machine, but he or they can intervene on the type of selection, providing directions. So let's see here, you see two lines where, starting from the same example, the same instance that is highlighted in orange in this case, we can go in, let's say, two different dimensions, two directions, left and right for each row, where on one side we have a very connected nucleus of the cell, while on the other side it is disconnected, meaning a different function or some level of lesions or intervention. And this can be done on multiple dimensions, sort of, I would say, semantic direction, even if this type of semantic is not built within the model, but in some sense is provided by the user, by the clinician looking at a different type of image. So he can explore the latent space, that is this low-dimensional space where all the images are mapped, in order to move to zones that have particular visual characteristics that the clinician may want to explore further. So it's a kind of induced semantic, even if it's not embedded directly into the model. All the three cases that I presented so far are part of the classification that Riccardo was showing at the beginning. It's our post-hoc explanation model. So we have a black box and we try to explain how it works. In this other use case that is about oral lesion classification, so let's say detecting by images if a lesion is of a particular type or another, this one is implemented instead using a interpretable by design approach. So we have a model that is completely transparent, and it is based on the concept of classifying instances on the basis of similarities with other examples that the model has been trained on. In this way, how the classification proceeds follows a little bit also may follow the internal reasoning that a doctor that may take. Just to show you an example, this is an extract of this decision tree called pivot tree. Pivot because at each decision point we have an image. So accordingly, if the given instance is close visually to this case or not, we take a different path within the tree until we arrive to the leaf. Of course, the different decision defines which are the boundary of the type of classification that is applied on this type of model. And pivot tree is, let's say, also achieve very good accuracy. I'm not going into the detail of the table that you see on the bottom right, but actually try to find a very, let's say, efficient trade-off between transparency and the explainability and the efficiency of the model itself. Thank you.
Okay, hello everyone. I'm Alfio Antonio Luca, and today I'm going to present you a procedure that we developed in order to get global feature importance by leveraging local counterfactual. This technique, the research question behind this technique was trying to understand if by combining these two strategies in order to get an explanation, we were able to get some improved form of explanation, overcoming some limitation of these two category of these two family of explanation, the feature importance and the counterfactual themselves. But before focusing on the strategy employed in this study, I want to stress the part that let's say, for example, that we have an explanation. And we, as an expert or domain expert or anyone that needs the explanation, understand that the explanation is not so good. In some way, it doesn't make any sense, commonly in common sense, but also from the domain knowledge perspective. If this is the case, by using just post hoc explanation, we are not able to understand where the bias comes from, because the explanation procedure as a whole is composed by three main parts. The bias can be in the data, and so can be originated by the data, but injected in the model during the training. Can be also due to the model itself. During the training procedure, you can have some bias that are injected according to some specific condition. But also the explanation itself, being post hoc, can introduce bias, because in the end of the day, a post hoc explanation is still a procedure that you apply on an already trained machine learning model. In order to understand if there is something that doesn't sum up in the explanation, one strategy can be employing the domain knowledge. So having an expert, for example, that is able to validate the explanation for you and say, okay, for example, a doctor that says this specific saliency map does not make any sense in my domain context to explain why this is a cancer or not. Of course, this is a very costly procedure because you need to have human experts that are willing to provide some information to inform you and also to provide this information in a format that is usable for you to understand and measure if the explanation, whatever the form is actually good or not. For example, let's say you want to validate a feature importance. You need your expert to say, okay, this feature is super important to recognize these specific things, and this other feature is not. This is not, let's say, free to have, but we managed to do this in this study. And also, we addressed two of the main issues that we have with both these two families that were mixed together in order to get Boxer, our procedure. They were feature importance and counterfactual. As we know, counterfactual provide only local explanation, but maybe we want to have a general view of the decision-making process of the algorithm, of the model. And on the other hand, the feature importance are most of the time computationally inefficient, very expensive in terms of computation time, and unreliable, especially with the features that are some codependence and correlation. This is well known in the literature, especially, for example, for SHAP. So, our counterfactual-based feature importance procedure is pretty simple. We try to approximate the decision boundary of the model. We do this by just looking for closed samples that are recognized differently from the model itself. Once we get all the set of these points that should surround the decision boundary of the system, of the model, we do some linear interpolation in order to approximate even better this decision boundary, trying to stay as close as possible to the decision boundary. Once the classification change, by using this new point originated via linear interpolation, we consider this a potential counterfactual. And we start flipping one feature at a time, starting from the original sample toward this counterfactual, the value of this feature. If, by changing one single feature, these samples correspond to a different classification, we consider that feature relevant. In the end of the day, after we made all the switches with all the samples across the decision boundary, we can consider the frequency of this, let's say, relevance of a feature as a proxy, as a measure of feature importance. We test this approach both with the benchmark dataset and real-world dataset. We were lucky enough to get some real-world dataset from a company, a manufacturing company here close to Pisa in Lucca. And we were lucky enough not only to get the data, but also to get this domain knowledge. So in this case, a 3-level rank of importance for each feature according to the goal, the target of the classification. Specifically, this data was gathered during the production, in this case of tissue paper. During the production, a lot of sensor provided information, we gathered, we collected them, and then in the end of this process, we gathered 5 different experts of this manufacturing process at the same table, trying to agree on the importance level of each of these features in order to classify, in this case, recognize the quality of the final product. Using the 2 different measures, bulk and resistance, which are very important for the paper to the tissue to be produced. We compared our approach with the famous and well-known SHAP in order to understand if by using just a multivariate perceptron to derive this feature important, to derive first of all the resistance and bulk level in terms of quality, and then the feature importance, we were able to be more or less aligned with the expected informativeness of each feature provided by the domain expert. And as you can see here in the results, Boxer is the blue bar, we were able to be consistently, mostly all the time, better than SHAP in providing this alignment. This, in our understanding, is because SHAP is well known to be affected by correlation and codependency in the feature. We are not showing this in this study, but we also tested our approach specifically against SHAP with this specific research question, if it was more or less robust toward correlation in the feature set, and yes, Boxer is more robust. Not only, is also way more computationally efficient. Here in this table, I'm reporting the computation time for the feature importance with a number of UCI datasets, something very straightforward, benchmark dataset, using different kind of different number of classes and different kind of features. And as you can see, Boxer is consistently the one that results in the less computation time. So this was greatly appreciated, because if you have ever used SHAP, you know that SHAP is barely impossible to use on your personal computer unless you do some undersampling, because it's very expensive from a computational point of view. Okay, I leave the floor to Mattia.
Okay, thank you very much, Luca. So now is it working? Okay. Now we flip the page, and moving from feature importance, we move to another form of explanation, and we move to decision rules. And not simply decision rules, but as you see in the slide, fuzzy decision rules. This is because, as you have seen in the first presentation by Federico and Lorenzo, we want, at the end of the day, to have a dialogue with the human. So in a way, we want for our explanations to be as close as possible to the way that a human has of reasoning. And I don't know about you, but I usually reason in terms of concepts, and these concepts are often overlapping. And this kind of very high-level idea finds a direct implementation in fuzzy explanation and fuzzy decision rules. As you see in the slide, for instance, when we think about age, we do not think about someone who is just simply 23 years old, but they are very young, and they are somewhat going towards their middle age. And thus also we ourselves reason in terms of concepts, and these concepts can be fuzzy and can be overlapping. And this is very, very useful for us, because having this kind of artifact allows us to have explanations which are, in a way, directly understandable for us. They are, of course, very flexible, because, once again, we can overlap different concepts. And since they are directly understandable, they are also, in a way, very general. So whenever we construct our decision rules, we can simply go and use, rather than the raw values that we have in our features, use these fuzzy concepts. As you see, for instance, in here, if we have someone that is 19 years old, they are, of course, still a teenager, and they are, at the same time, very young. This also enables us to do another interesting step, which is if you want, globalization. As you have seen, we have several types of explanations, one of which are local explanations. Thus, we are explaining the black box on a single instance. But since we are reasoning, in this case, in terms of concepts, we are also, we have an easier path towards generalizing, and thus take many different explanations coming from many different observations of the black box, and we can aggregate them. And this is, as Riccardo was mentioning in the opening, the approach of local to global. Once again, to aggregate different local explanations into global ones. And the way we do it, as we will see in just a bit, is through a genetic algorithm. And without going too much into the detail, when we think about genetic algorithms, we mainly think of algorithms that are trying to optimize some objective, and they're trying to do so using kind of a evolutionary approach. Thus, as it happens in evolution, we have mainly two concepts to deal with. First one is a concept of chromosome, which in our case will be a candidate solution. That is a set of decision rules that are explained in the black box. And of course, we have also the process of evolution. That is, from one generation to the other, different solution, different chromosome, that is, different decision rules are merged. There is some form of crossover, and then only the best are going to survive across several iterations, thus yielding our optimized set of global decision rules. The way to do it, of course, is in a way to encode this decision rule in a format, and for our format, that is for our chromosome, we are simply going to have a vector. As you see here in the image, we take, for instance, the decision rule that you see in here, age in 2035 means that we are going to grant a loan, and we can encode this into a vector. And as you see color-coded in here, we have in this vector, for instance, the variables that we are using in this decision rule, its the values of the features, and so on and so forth. And as I'm sure you're familiar, when we're talking about vectors, we can talk about set of vectors. So rather than simply encode with a chromosome a single rule, we can encode a bunch of rules. And thus we can go from a single decision rule to a decision theory. And thus we can extend our chromosome, our vectors, including multiple rules and having additional information. So for instance, as you see color-coded in here in green, we have also within our chromosomes some features that allow us to drop or use some of the premises that you have in our features. And thus with this, we have a simple and direct way, straightforward way to encode all of our local explanations. As I've mentioned, we're going to aggregate them with a local to global approach. And the way we are doing this, we are going to do is, once again, to use this evolutionary approach. Thus, we are going to start from a set of local rules that you see here on the top in the populate phase. And much like in evolution, we are going to mutate our chromosome. We are going to have several different chromosomes have a crossover in between them. And finally, at the end of each generation, we are going to perform a selection. Thus, of all the new decision rules that we are aggregating, we are only going to select the most fit ones. That is, the ones which are both simple and at the same time very accurate. I will not go now into the detail all of the results. I just want to show you this very compact aggregation of the results, in which I want you to focus on mainly two of the columns of this table. First one is, of course, the fidelity, that is the accuracy of our decision rules with respect to the black box, which, as you see, is relatively high regardless of what black box we are trying to explain, thus also regardless of the complexity of the decision boundary. And also, at the same time, we're also able to achieve this high fidelity with a relatively explainable model. Because as you see in the rules, number of rules and number of premises columns, we have a very compact set of rules. Meaning that at the end of the day, starting from local explanation and aggregating them, we are able to have both an accurate set of decision rules to mimic our black box, and this set is also relatively explainable for our user. And with this I conclude, and I would leave the floor to Simone.
Thank you, Mattia. I am Simone Piaggesi, and now I present Ilium, the last method of this session. This method is tailored to generate local explanations, but starting from global explanations. So in this sense, it works in the opposite direction with respect to the model that Mattia was explaining. Okay, so nowadays we are witnessing a paradigm change in explainable AI. There is a growing number of methods known as self-interpretable methods that simultaneously and in a differentiable manner train a machine learning predictor together with a local explainer. This is in contrast with traditional post hoc explanation methods that, given any pre-trained black box, optimize an individual separate explainer for each instance that we want to explain. In this context, we aim to redefine the post hoc explainability paradigm by introducing a trainable generator of local explainers that support any type of explanation, including feature importance, decision rules, and counterfactuals. To do that, we rethink the post hoc explanation pipeline. In particular, those explanation pipelines are based on interpretable surrogates such as Lime or Lore. And we do the following. So at training time, we learn a latent space model that accounts for both the data distribution and the black box decisions over the data. This latent model is a complex neural network model that we called meta-encoder. This meta-encoder learns how to generate interpretable surrogate as local explainers. Instead, at inference time, given any new unseen instance, the meta-encoder network is capable of generating a local surrogate from which we extract the local explanation. One of the strengths of this approach is that we can ensure in the training phase several desirable properties for explanations, such as robustness and faithfulness, for instance, by including them into the training procedure, their optimization in the training procedure. So we introduce Ilium. At the heart of this approach, there is the meta-encoder, the latent space model. The meta-encoder globally is a complex neural network, but locally, so at the level of specific instances, it behaves as a linear transformation that map each instance into a latent space according to its features and also according to the decision of the black box over the instance. So from this latent space, we generate explanations by leveraging a global interpretable surrogate whose decision logic dynamically adapts to the instance under consideration, according to the local transformation learned on the instance in itself. To ensure high-quality explanation, we basically insert explainability constraint in the latent space training objectives and architecture. But now let's see briefly how to generate different kind of explanations. On the left, you see for feature importance, we train a global logistic regression classifier over the latent space. And then once we have obtained the coefficient betas of the logistic regression, we weight them with the local parameters of the transformation W to obtain for each instance X the feature relevance of the feature J. Instead, on the right, you see how to obtain factual and counterfactual rules, training a global decision tree over the latent space. And then for factual rules, we extract the decision path corresponding to the root leaf path over the tree that leads to a given decision. Instead, for counterfactual rules, we search for alternative path that leads to a different decision, but with the minimal changes in the splitting condition. Given a set of rules that will be defined in terms of latent variables, because the decision tree is on the latent space, we rescale them with again with the local transformation parameter W to obtain the decision rules and the counterfactual rules defined over the input features. Finally, briefly see what are the explainability constraints that we can ensure. First of all, the architecture of the meta-encoder is based on local linearity. Local linearity ensures that from explanations obtained in the latent space, we can express them by an easy map back into the original feature space. Second, we ensure with decision conditioning that the similarity between latent data points of the latent space will reflect both the similarity of the original data points, but also the similarity of the black box decisions. We experimentally see that these conditions ensure the faithfulness of the resulting explanations. And third, with mapping consistency, we ensure that given any pair of latent transformation, they resemble the similarity, their similarity resemble also the similarity of the corresponding input instances, and we see from experiment that these conditions ensure the robustness of explanation with respect to perturbations. So to conclude, with Ilium, we redefined the landscape of post-hoc explainability. We have conducted extensive experiments on tabular datasets, so showing that we can generate robust, faithfulness, and also accurate explanations. We plan to, in the future, to work also on other types of datasets, for instance, images, time series, and text. But also we want to study the explanation inference process with respect to the generalization capabilities according to distribution shifts of the data and also across different data sets. Thank you, I have finished.
Okay, so now it's my turn to close this session. So what we presented is only one part of the many methods which are developed in this work package. We try to accommodate this presentation from those 3 points of view. From the first, it's what would be, this interaction person-machine, even if Abel is physical, but there are all the difficulties that is the big picture that on which we can accommodate the various pieces that we are developing. And then the point of view of the decision maker, the health, and then there are only few of the cases that have been presented, the one that are developed in health. There are other 2 applications that are, collaborations that we are trying, which we are trying to experiment all the methods. And then the third part was about the algorithms. So producing explanations, artifact out of the complexity of the growing complexity of black box is still an ongoing research activity. It's not the end of the story. But however, in the project, we also pursued other 2 lines that we didn't present, not because they are less relevant, but because we had to do a choice. And there are important results there. One is the one that is mentioned several times, so the algorithms that are capable of that are aware of their limitations, and that's also the door that allows open the collaboration with the group of the cognitive and psychological scientists of University of Cattolica. So from one side there is the problem of algorithms which are capable of defer. On the other side is in which kind of a relationship machine and humans we have to collocate such deferring. What is the relevance from the point of view? So and then there are five different lines that we are studying, including the interleave between learning to abstain to defer with the explanations, which forms so essentially, how can we emphasize the uncertainty of the system to highlight this to the user? And then the other line, which is another important one that we are pursuing, it's the design of this collaboration using methods and theories which come from human-computer interactions in the design function, even the experimental setting since the beginning. So using different forms also of techniques for the co-design of the AI system. So it's even revolutionizing what is the design phase and the collection. And of course, all these things that you have seen also in the generating explanation artifact. There is also this new challenge of double challenge. What does mean explanations for foundation models, for even more complex architecture? And there are some of us that are studying from different point of view this line, and then how to take advantage of the capabilities in terms of quality of language that a large language model can produce. So that can be a very important, useful tools for producing and supporting these interactions with the end user. So there is a group studying how to transform explanations, even those that have been presented so far, from the artifact that those algorithms are capable to produce. Still, there is a path to do for bringing them to the end user, and large language model that might be an important path. And there are people studying this in this work package. And finally, so what to say? There are plenty of, so the people involved are 15, and we have been quite productive. Of course, some of this research was already based on previous path, but we are consolidating and we are opening new research questions. So still a lot to do. So we have plenty of algorithms, more than 20 have been produced, and also the curation of data set is another important part. From many of these experiments that we are doing with the collaboration with the various health systems, we try to take advantage to share the data set. And of course, there is we are also a lot of synergy with other projects, and a lot of activities also in the disseminating. So there are several XI conferences, workshops, tutorials on which we are participating. We are part of the organizers and of course also the presenters of our research. So we are still trying to bring a fair project in the international community with very valuable results. Okay, so thanks very much for your time. Now it's time for the coffee break.
Coffee break now, but let's start again at 11:15 sharp.
Okay, I forgot to say there is also a demo of Abel available over there.
Prova.
Okay, I think we can start again. Can we start, Okay, welcome back to the second session, which is about the work package 2. The title of the work package is System 1 and System 2, Machine Learning and Reasoning. It's led by Umberto Straccia and me. And a brief introduction recalling the objectives of this work package, which are twofold. From the one side, coupling the neural and symbolic subsystems. And the neural one is known as System 1, as symbolic as System 2, allowing for learning and reasoning by merging the more number crunching part with the symbolic reasoning to get the best of the two worlds. And the other main objective is to explore the mathematics and physics foundations of these two paradigms by understanding with formal models the reasoning patterns behind black box neural networks. The work package has 4 tasks. For each task, we will present one highlight. Before that, some numbers. Here there are the people involved from the institution of University of Pisa, Scuola Normale Superiore, and CNR, and some key performance indicator about the last year with 19 papers, most of which are accepted both in conference, prestigious conference, and journals. There are also synergies with other projects regarding the topic of this WUPI. And here are the papers, the list of papers of the last, of the second year of the project. Let me now move to each of the tasks. And the first task is about integration neural symbolic representation for learning and reasoning. And the highlight will be presented by Francesco Giannini.
Thank you. Okay, so good morning everybody. Today I'm going to present you a work that has been recently published in collaboration with the University of Siena and KU Leuven, and that is called Relational Reasoning Networks. That is about a neurosymbolic model. So what is neurosymbolic? Maybe none of you are familiar with this word. So neurosymbolic is the combination of two different areas that are neural and symbolic approaches that has some advantages and disadvantages. And the idea of this field is to integrate both the advantages of the two fields to get something that is better than the two taken isolated. So neural networks are very good at processing low-level data, but in general they need a lot of data to work properly. On the other side, symbolic AI is more interpretable, can generalize better with few data, but in general they are not scalable. So the idea is to develop a framework that can combine these two words. And the context of this work is on relational data, in particular on knowledge graphs. A knowledge graph is a collection of triplets where you have two different entities and a relation between them. Like, for instance, the fact that the Last Supper has been painted by Leonardo is a triplet, where we have an object, the Last Supper, a relation that is painted by, and another object, that in this case is Leonardo. As you can see, the objects can be of different types, and the relations can act on different kind of objects and connect them globally. So, for instance, this is a part of a knowledge graph. The main issue with knowledge graphs is that they are generally incomplete. So the point is that only a few relations are known between different objects. The other ones need to be discovered. So the idea of some of the tasks is to exactly complete the graph. This is called knowledge graph completion, or some other times link predictions, in understanding what is the link, what is the relation between different objects. And there are some methods, knowledge graph embeddings, that do that exactly by encoding the statistical correspondence between these objects and relations, just by providing an embeddings to all of them. And there are many approaches to do that, like, for instance, TransC is one of them, trying to embed each of these entity and relations with a vector, and then representing the facts, the triplet, with a translation between these vectors in a latent space. And the idea is that a fact is true if the transitive, translating one vector into the other, actually correspond. So there is no residuum between the translation of a vector and the other vector. So KGE works in this way, but in general, the KGE acts as black box, so you don't have any idea of how they work and why they provide a certain prediction for a certain triplet. And our idea is to develop an easy method for KGE, and the main goal is to take logic rules that are somehow more interpretable than just KGE encodings, and to inject these logic rules inside the way the KGE provide these embeddings, so to refine their embeddings according to these rules. For instance, if I know some relations about countries and continents and some neighborhoods between countries, I can infer that if Italy is located in Europe and Italy is a neighbor of France, then also France should be located in Europe. And these rules can be expressed between all the possible countries and continents. And so the goal is to apply these rules into KGE. Let's see how does it work. So the idea is, let's have a initial incomplete KGE with some facts, here denoted by a continued line, a solid line, and we want to infer some missing triplets, some missing links, denoted as dotted lines. So for instance, I want to infer if France is located in Europe. So according to the rules that I'm given, I'm perfectly able to do that. But what about Spain? Spain before was still unknown, and France was not helping before. But now that I infer that also France is in Europe, I can apply the rules again. So the idea is that these rules, according as the knowledge evolves through time, through the applications, can actually provide multiple inference steps. So they can be used to perform multi-hop reasoning inside the knowledge graph and allowing us, helping us to complete the knowledge graph. But there are also other cases less straightforward, like imagine you have also Morocco. Morocco is close to a country that is in Europe, but Morocco is not actually in Europe. So the problem is that some of these rules can actually be holding just a statistical level and not being hard rules. So we need a methodology that actually allows us to use the rules only when it's needed. The information is important, but the way it is done, it is not straightforward. No? I should evaluate if applying the rules or not. Also, the problem is scalability, since these rules, applying these rules to all the possible entities and relations may be totally unfeasible. So we want to solve these research questions, or at least try to help with the method we developed in solving these 3 points, basically. So the way we do that is to combine 2 words. So the entity relations graph that we saw before, a knowledge graph, with another kind of graph. And that is provided directly by the grounding of the logic rules on the elements I have in a domain. So the idea is, let's take a certain set of elements, objects, constants, relations, and some rules on them. Like, for instance, the one we saw in the previous slide. Then we have this initial graph that would combine these 2 parts together. And this is the object of our study. And the problem is, so given a part of knowledge, we want to learn the evaluation, the interpretations for the queries, so the triplets that are unknown. So we want to discover if these facts are actually true or not, given what we know to be true. So on a first side, we have the entity relation graph. That is the graph connecting the entities like France, Italy, Europe, and their predicates. We reported here the factor graph, but it is exactly the first knowledge graph I showed you. But we have also the other graph that can be built by using logic rules. And in this case, the graph is built like standard Markov logic network, if you are familiar with them, or probabilistic graphical models in a sense. So for each rules, we ground the rules and we connect each triplet to this rule where it is occurring. So like, for instance, France is located in Europe and France is neighbor of Italy, implication Italy is located in Europe, involves 3 different atoms, 3 different facts. That France is located in Europe, that France is neighbor of Italy, and that Italy is located in Europe. So these 2 graphs, actually these 2 graphs are different, but they can be combined together since they have some joint elements that can be connected. And what we want to do is to perform message passing on the full graph. So where we have these 3 different kinds of objects: entities and relations, facts, and ground rules. These are like rules applied to specific facts. And relational reasoning networks, our model is actually building a network that performs inference exploiting these relationships given by these message passing algorithms. And so here I show you the unfolding of the network. That is exactly the unfolding of the message passing equations I showed you before. And so the idea, we go from the ground atoms to the ground rules, and then from the ground rules to the ground atoms, and so on. So the idea is to refine the embeddings and the predictions of the ground atoms and of the ground rules according to the relational structure given by the knowledge expressed by the rules. And we can reiterate this process simulating multi-op reasoning. Of course, the objects involved here has associated their own embedding that can be provided by a KGE initially and then refined, or by neural networks and then refined again according to the message passing, but also an output. So in the end, when we reach the maximum amount of steps we allowed for the reasoning, we provide the final output given the final embedding representation of each of the facts. And on this final output is where we calculate the supervision. So we are just in a supervised learning setting where we are enforcing the supervisions on the final prediction according to the refinement. So just few remarks and conclusions. So these methods, actually, that I give you just a highlight, an overview, provide a way to represent logic formulas, additional knowledge inside the knowledge graph, and use this to refine the way the embeddings are built in this latent space. But for sure, the main idea of the method, or at least the initial version, was considering to have all the possible full instantiation of the logic knowledge in all the domain. But this cannot be feasible. So there are many heuristics that have been developed in the literature that provide a trade-off between expressiveness and scalability of the approach. And we have some work submitted to IGI in these directions, so to provide more interesting, let's say, reasoners that have this trade-off as its aim. Also, the semantics is something that I didn't talk enough. I didn't talk at all about the way these rules that have a precise semantics in logic can be enforced. And just to tell you, there are some ways to enforce these rules, also given the embeddings of the elements, and there are some works ongoing also on these directions. Some of the works we are doing actually was trying to do that by also learning the rules. That is the last limitation that I'm talking here. So the fact that the prior knowledge is somehow needed at the beginning, so the rules are somehow needed, where there are other approaches that we are working on that can learn these rules as well. So in a sense, you can learn the rules directly from the data. You can enforce the satisfaction of the rules symbolically so that you have interpretable logic, and you can do in a way that the grounding is limited to the very relevant elements inside your theory to preserve also scalability. This is more or less the highlight of this work. Thank you for the attention.
Thank you, Francesco. Let's move to the second task, which is explainable neurosymbolic system, and the highlight will be presented by Andrea Pugnala.
Okay, hi everyone. I'm going to present today a work that is joined with Filippo Palomba, José Álvarez, and Professor Salvatore Ruggeri. That is called a causal framework for evaluating the fairing system, and this will be presented in Thailand in a couple of months. Okay, so I guess that the idea is why do we care about the fairing systems, or more generally human AI teams? Well, we know that machine learning models are everywhere, they make mistakes, and what we would like to do is to avoid those costly mistakes. So we can inherit what we do as humans and think about what a doctor will do. Imagine that you go to a doctor and the doctor might not know what is your illness affecting you. And so here the idea is really the doctor can defer you to some other expert which is more knowledgeable of the possible illness. And that's what we are trying to do with the fairing systems. Indeed, in the learning to defer framework, what we have is a machine learning model and a human expert that is also another imagined predictor. And the idea is to learn a policy, G, that determines who will provide the final prediction. So a deferring system is just a system that knows when a machine learning model will make a prediction or where a human will make a prediction. And the idea is that you need to use a human whenever the human is better than the machine learning model. And how do you do that? Basically, you have to estimate a reject score that is called K, and whenever K is high, it means that the human is better at predicting. And so the deferral will occur whenever K is above a certain threshold tau, or K bar. How do you pick it? Well, in generally, you can imagine that humans are costly, you can't use them too much, and so you want your model to cover at least C% of the cases, and then you will have the human predicting on the remaining part. And so you just fix K bar by fixing the quantile over this reject score. Now, the question is, once we have a deferring system, how do we evaluate it? In the literature, what is done is just, okay, we have a deferring system and we compute the accuracy over a test set. But I argue, and I want to convince you that this is not enough. And why is that? Let's start with a simple example. Imagine that you have an observatory which has a huge telescope that takes pictures, tons of photos every second in order to detect whether there is a new galaxy there. Clearly, such a system can be done by humans, but basically machine learning models are trained to detect new galaxies. But the director of the telescope heard about learning to defer, and so wanted to implement a hybrid system where still most cases are handled by a machine learning model. But now there is also a human astronomer that is labeling, or better, predicting the difficult cases. And so in the end, is this really useful? This is the question. Similarly, whenever we have, imagine you have a hospital where you have several cases that you have to diagnose, and generally this is done by human doctors, but maybe for some whatever reasons you have in mind, read COVID-19, you don't have enough doctors, and so you might want to implement also a deferring system where some patients are diagnosed by a machine learning model. So the question is still the same. Is this deferring system really useful? And the question that we are trying to ask is a causal question. Because in the end, implementing a new deferring system is exactly as implementing a new drug or a new treatment, where we want to ensure that this drug has a causal impact on a variable of interest. In our case, it's the performance, like the accuracy. And so how do we evaluate this? We use a very old framework in causality that is potential outcomes that basically is quite easy in the basics, where we have a variable, a dummy variable that prescribes whether you receive or you don't receive a treatment, and then potential outcomes that are these OI of 0, OI of 1, should capture what would happen if you receive or you don't receive the treatment. Here we have an issue, because in real life, especially in social sciences, experiments can't fully controlled, and so you have only one outcome that is observable. So basically, you can't either receive the treatment, meaning you can't receive the drug, or not receiving the drug. And so this is a problem, and we have to find a way to retrieve causal effects. How do you do that? Well, typically, a common strategy is to use a randomized control trial, where you have a control group that receives a placebo and a treatment group that receives the actual drug, and then you compare the outcomes over these two groups. But often this is not ethical or not possible to implement such a trial. And so what you want to do is exploiting extra knowledge on the treatment assignment. And one very old-fashioned way of doing this is through regression discontinuity design, that is quasi-experimental design that basically knows how the treatment is assigned. In this case, imagine that the drug is given to patients if the cholesterol level is above a certain threshold, let's say 200. So with very few technical assumptions, you can imagine that people with 201 of cholesterol are very similar to people with 199. And so those people very close to the cutoff are comparable. Maybe some of you might have guessed where I want to go, but this way of describing a treatment is very similar to what is done in the deferral policy. Because in the end, our treatment is whether we implement a deferring strategy, and so whether the human will provide the prediction or not. And so in this idea, we can imagine that the potential outcomes are now whether the machine learning prediction is correct or the human prediction is correct. And so in a sense, we can estimate now the causal effect of introducing a deferring system without recurring to randomized control trials. And moreover, we designed two different scenarios. And I think that the first one is quite interesting comparing to what we have done in the social sciences so far. Because in the scenario one, we assume that all the machine learning models' predictions are available. Meaning, imagine you are the owner of the machine learning model, such as the observatory that has its own machine learning model to query whether there is a galaxy or not. And in this case, we can access both the human astronomer prediction, but also the machine learning prediction. And so at this point, by how we define the causal effects, we can retrieve all the individual effects. That is quite a unicum. Basically, it's one peculiar setting where you can observe both the potential outcomes, which is generally not possible. And so for all the deferred instances, you can compute individual treatment effects. If this is not possible, imagine you're not the proprietary of the model, so you can't query it, or maybe you are the hospital where you shift from a fully human to a hybrid setting. What you can do is still getting to RDD, and you can estimate the causal effect at the cutoff. And so this is a local effect that tells you what is the effect of implementing a deferring system for instances that are close to the reject score of the cutoff. We evaluated this with 3 questions. That is, what causal effect can be computed for scenario 1, what other causal effects are also available, and what is under scenario 2 the causal effects. We tested 5 data sets, 7 baselines. I'll go quite quickly on this, because maybe if you want to chat a bit more, you can, we have a poster later. And then these are the metrics. We have the deferring system accuracy, the average statement effect, the conditional average statement effect, and the tau RD. While the first question is quite easy to answer, you can see it. I think that the most interesting is what other causal effects are possible to compute under scenario 1. Because in this case, we can, since we have access to all individual treatment effects, we can ask ourselves whether there are some issues with fairness, for instance. If we see that there is a huge difference in terms of causal effects from male to female, this might mean that for some reasons your data on which you built your system are kind of biased. And this is quite interesting to solve. This is a real example with X-ray images. Similarly, we have results for Q3, where we show that there are basically, when you have a maximum, these effects should be close to 0, but for the details, I invite you this afternoon to the poster. So conclusion, deferring system impact accuracy, but we argue that this is not enough if you want to implement such system, because you want to ensure how to causally evaluate these systems. And I think these are nice because you don't need a randomized control trial to assess their impact, and this is something nice. And I hope I convinced all of you that this is possible. Future directions, we want to extend our approach also to other forms of human AI teams where this is possible. For instance, decision support systems or conformal prediction. But also, we would like maybe to shift from evaluating also to learning policies that maximize this causal effect. And how to do that is a work in progress. So that's it. We also, just a quick reference to the importance of use cases and how these learning to defer systems deal with real humans is an open question, and we are also working in that direction. Maybe you will hear about it later this afternoon. These are my contacts, and I think I'm done.
Thank you, Andrea. We move now to the third task, exploiting non-standard analysis to empower deep neural network and reinforcement learning. And the highlight will be presented by Lorenzo Fiaschi.
Thank you. Okay, the idea is to implement prioritized learning. Prioritized learning means I want to learn something or more than one thing, and I want to learn them in a prioritized way. Why? Because the world is made by priorities. Okay, this is a problem that interests a lot of industries like autonomous driving cars, industries like I have to develop an autonomous driving car with a neural net, equipped with a neural network, and I want to guarantee that my learning will for sure, or statistically for sure, try to not collide. Then it will try to satisfy the driving rules. Then it will try to get you to your goal, okay, to the place you want to go. And as a technique, we are trying to, and we are actually achieving some results to achieve this goal, is non-standard analysis. Non-standard analysis is the use of infinities and infinitesimal numbers in computations. And with these numbers, we can represent priorities. We present an under review achievement, which is fully tested now, where the application is in hierarchical classification. Okay, here there's an introduction to infinite and infinitesimal numbers. I will be super quick on this. You are quite familiar with this chain of inclusion of totally ordered sets, but these totally ordered sets are infinite. Okay, so there are many infinite sets of numbers containing the real numbers. One of these, all the sets contain real numbers, contain even infinite and infinitesimal numbers. We have been able during our research to represent these numbers in a computers and do computation with them in a number crunching way. So no symbolic computations are realized, are floating point numbers, okay, and hardware-oriented computations. So I was saying, we have a hierarchical classification problem. I want to be super good on deciding if in front of me there's a tiger, an elephant, a shark, a pine, a cactus, or an onion. And to implement correctly this decision system, I should also induce somehow the information about the coherency on the hierarchical structure of this classification problem, because I know that a tiger and an elephant are terrestrial animals, while the shark is an aquatic one, and they are totally different things from, plants, okay? And a good decision system, a recognizing system, should learn this while it's learning the differences between tiger and elephants. And it's more reasonable to have an error between the classification of a tiger and an elephant than a tiger and an onion. If I have misclassification between a tiger and an onion, I would wonder what's learning my decision system. Okay, they are too far. So what we want to do, we want to use is the knowledge. Okay, we want to reuse the knowledge during the learning. I want to have an embedding of my animals, which is different from plants. So the embedding of the shark must be similar to the embedding of a tiger, but different. But I want the embedding of a tiger be closer to the embedding of an elephant, okay? Because they are closer in the hierarchical structure. There are many ways to do so. Most of them rely on just using some arbitrarily chosen weights to combine some losses, like the loss at the higher level, the loss of the second level, the loss of the third level of the hierarchy. And so these are totally trial and error approaches. You cross your fingers and hope that the choice of your weights is good, and you retry and retry until you are quite sure that your learning system is learning actually something. And this is an example, okay? You have a branching neural network. This network has a first part meant to learn the first part of the hierarchy. Then there is a subsequent part of the network with a goal to learn the second level of the hierarchy, and so on the third one, and so on and so forth. And these predictions are combined through their loss with these weights changing in time, okay? A lot of who knows what's going on. I don't know, I'll try. But there is this theorem. We proved that you can represent a classification problem with a loss function with more than one objective that have a priority with in a non-standard way, so with infinite infinitesimal numbers, where this eta value over there, like, I don't know, it doesn't work. No, it doesn't work. Okay, no, it doesn't work. Okay. Okay, so we have some requests. Okay, I won't go into the details, but the idea is that you can represent these functions in a more complex and more expressive domain. To do so, you need to introduce a projector operator in the neural network. Again, I don't have time to go into the details, but trust me, read the paper if you are interested into. And if you inject this projection operator in your network, you can change the shape of the network. The one on the left is the branching neural network I showed you before. Now we have just one single block of network, and with these projection operators, you have the guarantee that the three objectives are learned all together in a prioritized way. So the flow of information realize a single embedding for the image, but this embedding preserves the requests we wanted to. So we want embeddings similar for similar images and different for different images. And these gradients from the diverse objectives are not conflicting. So the gradient for the first objective, which is the most important, because if you are not able to discriminate between a plant and an animal, for sure you are not able to distinguish between a tiger and an elephant or a tiger and an onion. And this will be prioritized over all the others. So there is a reuse of knowledge. Okay, this is just an example of what happens when you put weights at random. You see the blue line in top left situation, the top left plot, is the loss of the first objective, so they distinguish between plants and animals. And you see that the error is higher than the classification error on the third level, so in the finest one, which is the green line. And this is totally unreasonable. You are better at distinguishing between super precise classification tasks, but you are wrong. You are worse deciding between plants and animals. So you are good knowing if this is a tiger or an onion, but you don't know if this tiger is an animal or a plant. And this makes some questions on how good you are using your parameters. On the other hand, you see on the top right one, all the losses are with our neural network are converging to the very same value, because, of course, your first objective is driving all the others. Okay, here we proved that our results are comparable or even superior from accuracy and coherency with respect to the hierarchy, but the most important thing is the number of parameters we are using. On the Cypher 100 or Fashionist the benchmarks, we are using 1/3 or even 1/16 of the parameters. This proves, or at least shows, that a better use of gradients and priorities allows you to use a lot, require definitely a lesser number, a dramatic lesser number of parameters to learn the very same thing, or even in a better way, just because your learning is prioritized in a reasonable way. Okay, I guess that's it. Okay, there are some ongoing studies we are using these networks in the abstention problem, where you have to decide where to choose between some cats and dogs, for instance. You have only saw the cats and dogs, and then at inference time you also see tracks. Okay, and of course you have to reject tracks, and you may be wrong between cats and dogs, and this is a prioritized problem, because you, of course, don't want to say that a track is a cat, so the abstention over never seen data must be prioritized over the misclassification of cats and dogs. Or, as I told you at the beginning, autonomous driving cars, where a jaywalker problem, you want to avoid collision as a prioritized problem, a prioritized task. Thank you a lot for your attention. I hope I've been in time. Thank you a lot.
Thank you, Lorenzo. And we move now to task number 4, which investigate mathematical structures in learning models. And the highlight will be presented by Caterina Papagiannulli.
Thank you very much. So today I will talk about our recent work, which is joint with Federico Pascalotto from Berkeley and Hannah Ceran from Tokyo. And it is about conservation laws and incremental learning dynamics and transformers. As the title suggests, we will talk about transformers, which is the building block of large language models, and it's a recent neural network representation, but theoretically speaking, not much is understood. And with this work, we are trying to understand what is going through the training of the dynamics of a transformer. And yes, and I will talk about a little bit about how we can understand a little bit better the training of the dynamics in transformers. So, by now I will be fast in this one because everyone knows what is transformers. It's like a deep linear model architecture which is introduced in 2017. And then the difference with the other architecture is that introduces this self-attention mechanism, which processes and generates the text. And this type of neural network architecture replaced older models like RNNs and LSTMs and for NLP tasks. So this transformer and like the large language models are like the basis for GPT, BERT, and TP. So how now the transformers work? As we said before, it introduces this self-attention mechanism, which determines the importance of words in a sentence. And then we have a multi-head attention, so we have a lot of heads parallel that allows the model to focus on different words, because its self-attention mechanism is focused for one word. So then we have the encoding and the positional, which adds information to the input, and then on top we add the feed-forward layers, which adds on top a non-linear activation function, and then we have a neural network. So the mathematical model behind the transformer is given by this representation. So first of all, we have these matrices, which introduces the self-attention mechanism, which is the WK, WQ, WV, and WO. And once we have this multiplication, we multiply it by the input of our neural network, and then we add the softmax function, and on top, at the end, we have this sigma function, which is the nonlinear activation. So basically what we have a matrix multiplication for the attention part, and then we add the nonlinearity in order to feed this attention mechanism to a neural network, a nonlinear neural network. So in our case, as I said in the beginning, we will try to understand the dynamics, like what is going on in the training, during training of a transformer, because it's not yet known in the literature. We're trying to bridge this gap. And for this work, what we assume we have these assumptions that our neural network, which is a transformer, we have a small initialization, and then that the stationary points are strictly local minima. And now what we are trying to understand, the problem, is like to explore the conservation law in transformer training for full weight matrices. And then to analyze the learning dynamics and study the evolution of the weights during training. Why we want to have this conservation laws? This conservation laws comes from physics and dynamical systems, and like tells us like which quantities are conserved during the training. So that's why we want to use these laws from dynamical system in order to understand in transformers during training what quantities are conserved. And why we want this? Because then we can understand like how the convergence, like we can understand the dynamics, we can say how actually transformers learn. So theoretically speaking. And to do that, we need to understand the evolution of the weight matrices. So again, in order, now we have to introduce the dynamics for these neural networks. So we assume, as usual, a loss function, and in order to understand the dynamics, we have to consider a gradient flow, and especially the solution to the gradient flow. So theta here represents all the parameters, which are like the W's of the self-attention mechanism, because we want to understand how this evolves. So we introduce this gradient flow. So the main result in this work is how actually the transformers learn, and we observe an incremental dynamics when we assume a small initialization. This theorem is just to say, I will try to keep it, so what we are doing, we are introducing a pseudo trajectory introducing this alpha scale and this logarithmic scale, which actually mimics the real trajectory of our parameters. So then what we are doing, like what we are trying to understand and what we observe is that we have this incremental learning, which means that I hit a plateau. Once I hit the plateau, my loss then is minimized, and I'm going for the next one. And then our model is learning what has to learn. So again, like in order to do that, in order to understand like the dynamics, one important thing is the conservation loss. It's like what is conserved. It's really important because we need to understand which quantities stays constant during training, because then we know that at these stages we have what stays constant and what actually explores a different direction. So the key mathematical insights here is that until now what we have found is that the weight matrices exhibit trace and norm conservation, and this help us to understand and like prove like convergence for the dynamics. And what does this mean? That the difference between the matrices that we can see in the transformers in the self-attention mechanism remain constant during training. So, and then once we have this conservation law, we can see that we have the behavior that it's called saddle-to-saddle dynamics in neural networks, and it is observed before for linear neural networks, and now we have it also for transformers. So basically here I just give you the how it looks like mathematically, this conservation law for square matrices, that the weights remain constant and the square norm is also remain constant. And using this, we can have actually the theorem that I showed you earlier and prove the incremental learning. So basically here we see the evolution of weight matrices during training for transformers with full weight matrices, and we see that like at some point, like in the second graph, like that the weights, the difference of the weights remains constant, and at some stages we have like this erratic behavior. So, and here we can see actually this more closely, that this saddle to saddle. What this means, like we have this loss, and then in the beginning, the first graph is the whole graph, and then the second graph is a close-up. So basically what we are doing, we initialize, and with this small initialization, we know that we will be in a loss, we will hit a loss plateau, and then our loss will decrease, and we will hit the next critical point. It will stay there in the loss, in the plateau of this critical point, and then again the loss will decrease, and periodically, like we can learn the task that the transformer has to learn. So what we have done until now is that we have observed the staircase pattern and loss function, which are the saddle-to-saddle dynamics, and how this is done, because what does this mean? That actually the rank increases during training in weight matrices, which is the part of the self-attention mechanism. And because of these experiments, we can see that actually we have a low rank bias, like, depending on the quantities that are conserved, this affects the learning dynamics. This is done until now for full weight matrices, but what we would like to understand is, it's an ongoing work, this one, is to apply Emmy-Noether's theorem for transformers, because Emmy-Noether's theorem gives us the conservation laws. So once we understand better which quantities are conserved, we can fully extend it even to, if it's possible, to large language models. If not the case, not just transformers with with self-attention mechanism. So, and especially like we would like to understand and study the dynamics when these conservations break, because when we have this, when the conservations break, then it's difficult to say something about the convergence, or if like we can have saddle to saddle dynamics and how like theoretically would look like when we have this break of conservation. So yes, that's what I would like to say. Happy to discuss further.
Thank you, Caterina, and let's thank all the speakers. Since we are short of time, I would postpone question to the lunch break, and we can move to the next VP. Thank you again.
Hai il telecomando per andare avanti con le slide? Ok, poi ce lo passiamo tipo il baton. Guardalo qua. Come ci va?
Okay, very good. Yes, okay, I am Alessio Micheli from the Department of Computer Science of the University of Pisa. I'm going to introduce you to the work package number 3. So the title is Human-Centered Lifelong Learning for Complex Data. The principal investigator are me and Fabrizio Sebastiani. Fabrizio Sebastiani is here. And yes, the aim is to study how deep learning architecture can continuously and incrementally learn a new concept, considering the human in the loop and small scarce data scenario. Also pushing forward the frontier of learning complex domains, including time series, graphs, or dynamical networks. We consider also cross-modal, cross-language lifelong learning. We have links to Traversa project of the FAI project, in particular lifelong learning and frontiers of machine learning. There are other key people involved, but we'll show you in the next slide. And yes, to the aim of this work package, we devised a list of tasks, indeed, you can see here. And in red, you can read the task leader. So namely, we have the first one is foundation of human and pervasive artificial intelligence. Number 2 is on lifelong learning for socially and environmentally sustainable AI. Number 3 is on learning in structured domain. That means graphs and networks. And number 4 is on cross-modal and cross-lingual learning. We have the number 5 on learning to quantify. That means basically to consider aggregated data instead of to classify singular instances. And the number 6 is on improving neural language models. So it's a rich set of topics, indeed, and to the aim of this workshop, we devised 3 highlights and 3 speakers. First one will be Marco Podda, presenting a work on explainable AI of graph neural networks. Then we'll have Nicola Messina, presenting a work on limitation of visual language models in object detection and counting, and Martina Miliani for investigating the semantic abilities and limits of large language models. And we have a further result, and we use a poster to present them this evening. So, in particular, Luigi Quarantiello for adaptive LoRa merging for domain incremental learning, and Lorenzo Volpi for LEAP, that is a simple method for classifier accuracy prediction under prior probability shift, and Domenico Tortorella for a transductive approach for biological pathways dynamical property prediction. And that's it. I want to say thank you for attention up to now, and I hope you can enjoy our workshop, our work package highlights, and have a nice day, of course.
Okay, so we move to the first presentation. First presentation being explainable AI on graph neural networks from Marco Podda. Please.
Sì. Scarica. Ah, non c'è più.
Sì, ce l'ho io.
Thank you. So I'm Marco Podda, and today I'll be talking about explainable AI of graph neural network. This is a joint work between me, Alessio Micheli, our PhD student Michele Fontanesi, and Domenico Tortorella, which is a postdoc researcher here at the Department of Computer Science. So this slide is like due diligence. We all know why we are here. We are trying to turn, let's say, opaque AI models into explainable AI models with all the nice properties that you see on the right. So transparency, bias mitigation, and so on. And this talk is also about graph neural networks, which basically are neural networks for relational data, so graphs, where there are entities or nodes which are connected by relations. So with the graph neural network, you can basically the cool thing is that you can give the entire graph as input to the model, and it will, let's say, exploit the structure to emit predictions. And so you can predict like single nodes of a graph. For example, if you have a social network, you want to predict some properties of the users, you can give it to a graph neural network. Or you can predict entire graphs, like you have a molecule, you want to decide some molecular properties, like whether it is toxic or not. And all this class of neural network models work by so-called message passing, where basically we associate a vector to each node in the graph, and this vector updates its state, let's say, by aggregating information from the neighbors. And as you iterate this process, each state becomes more aware of the general structure of the graph. So explainability is applied to graph neural networks, let's say the standard way. We have an opaque GNN to which emits predictions, which we don't know why, basically. And we attach to the opaque GNN an XI graph explainer, which basically gives us the input graph back, but with each node associated to a score. And the score indicates, let's say, the relevance
the node for the prediction. And by aggregating these kind of important nodes, you get relevant subgraphs, and you can then interpret the prediction. And this explanation can be evaluated to assess their quality with one of the standard metrics is plausibility, which is essentially the raw KUC of the importance scores with respect to the ground truth explanation, which of course you get once you use benchmarks for assessment. And one important part of graph neural networks, how they learn, is that they exploit inductive biases, and inductive biases are basically built-in assumptions that the AI model exploit to generalize to unseen data. Unfortunately, the term bias is a bit overloaded in AI. Here in this talk, we talk about, let's say, good bias, the one that lets you learn some task. As we know from the no-free-lunch theorem that says that without inductive bias, there is no learning. And for GNNs, basically we use two of the most known inductive bias that they exploit are the local inductive bias, that is the local interaction between the adjacent nodes influence the predictions, and the other bias is the higher order inductive bias, where basically takes into account long range and global interactions between the nodes. And here the key point is that no inductive bias is better than the other, because all of them allow to generalize to unseen data. So this research originated while we were, let's say, assessing different explainers with different GNN architectures. And at some point, you can see this task on the right, we were trying to classify whether the graph contained a 3x3 grid. So we knew the explanation, that was the presence of the 3x3 grid. But then we noticed a strange phenomenon where, for example, one GNN was achieving 100% accuracy and high plausibility, so it was catching the right explanations. And another type of graph neural network was also achieving 100% accuracy, but with low plausibility. So it was explaining the prediction in a completely different way. So clearly, GNNB wasn't doing a bad job. It was doing a good job, but it was solving the task using a different inductive bias. And so we started wondering why was that, and we started using XI to understand the GNN inductive biases. And to do so, we analyze explanation to detect explanatory patterns and relate them to the respective inductive bias. How we did it, basically we took existing benchmarks with, let's say, hard-coded ground truth, which were motif-based, so the kind of, the graph contains a 3x3 grid. And then we created a copy of the benchmark where basically we changed the ground truth. And for example, here we applied a correction, let's say, where the correct explanation became all nodes with degree larger than 2 become the right nodes for the explanation. And then we try different GNN architectures to see which kind of bias they were using to learn the task. And we explore this concept from different angles, from the point of the GNN architecture, so the number of message passing iterations, from the training dynamics aspect, so observing how the behavior changes with respect to the weight, the norm of the weights. And also we mapped different, let's say, inductive bias to known graph theory measures. So in our first result, we saw basically that some GNN architectures like to switch inductive bias preference from local to higher order, depending on the number of message passing iteration. You can see the graph on the right, top right, where basically a GNN starts with a strong preference for the local inductive bias with just one iteration of message passing. But as soon as we increase the number of message passing iteration, we see that the preference switches to the higher order inductive bias. Also, we noticed that some other different GNN architecture have a strong preference for local inductive bias, which doesn't change as you modify the message passing iteration. And this is useful for practitioners because then a user can select a different GNN architecture depending on which inductive bias wants to exploit during learning. Another result we have is that we have observed that depending on the norm of the weights, so the overall magnitude basically of the weights, GNN would switch preference over biases. As you can see on the plot on the right, you see that at the start, when the weight norms are small, the network high plausibility is achieved by exploiting the local inductive bias. But then as soon as the norm grows, we see a preference over the higher order inductive bias. And this is also useful for practitioners because by controlling the norm of the weights, we kind of can switch preference over different biases. Third result we achieved, we noticed that the explanation for local and higher order biased GNN have significant correlations with graph theoretical measures. And for example, the local inductive bias is very highly correlated with the cast centrality score, which is basically a graph theoretical measure that assigns node importance based on how many paths connect a node to other nodes. As you can see on the top right, you can see that the importance is that locally biased GNN gives to the nodes are highly correlated to the scores of the cast score. And the other result is that the higher order biased GNN are highly correlated with the Fiedler eigenvector, which is basically a vector that captures how a graph is split into clusters, so where we can, let's say, intend a cluster like a cohesive motif. And you can see on the bottom right that our importance scores for the higher order biased GNNs correlate with the Fiedler eigenvector. And this is also useful because then a user can analyze the data even before starting the training with the graph theoretical measures to get insights about which bias would be better to exploit. So this was all basically basic research, if you want, but we also are trying to apply this in the real world, for example, in chemistry. And we have this problem of structural alerts, which are kind of molecular patterns that are associated with adverse effects in molecules. And for example, they are an early indicator of possible toxic properties of molecules. And at this point, we have an ongoing collaboration to predict the toxicity of molecular structures using GNNs and calibrate the model biases using the tools that I illustrated before, and also discovering novel structural alerts. So we see on the right that for a known structural alert, which is this Michael acceptor pattern, we see that how it is placed in a real molecule in the center image, and how our XI model is predicting the node importance. So it's effectively figuring out that this molecule can be considered toxic because there are those specific patterns. And to conclude, so we have several studies that in which we try to relate the inductive bias of GNNs with XI, basically going backwards from the explanation to the bias used. And they can be related to the GNN architecture, the training dynamics, and other graph theoretical measures. And so this can be useful for users to get insights about which inductive bias to exploit. And we are also ready to apply this knowledge to real-world domains. What's next is to extend the results to other data sets and check results in real-world tasks, and also find other aspects that characterize these biases, or even new inductive biases that we haven't studied yet. I think there is no time for questions, so thank you.
Thank you very much, Marco. So we move to the next presentation by Nicola Messina from EastTCNR. And the title of the presentation is Limitations of Vision Language Models in object detection and counting.
Ok. Scaricata. Cioè ho aperta, perché vabbè anche su Google Slides. È già aperta in Chrome, forse. È già aperta in Chrome. Okay, we did it. Thank you. So yeah, I'm Nicola Messina from EastCNR. Good morning. And yeah, in this talk we're going to talk about some limitations of visual language models in two of the tasks on which we delved into in the last 1 year and a half, 2 years. So yeah. Without any further ado, so I would like to give some introduction on large visual language models. So, as we all know, we are in the era of large multimodal models that are basically models that enable a chat-based interaction. We are referring to these as large language models. But large multimodal models also enable vision capabilities usually. So they were able to achieve astonishing abilities in many image-based downstream tasks. For example, you can ask a large multimodal model to capture an image. You can ask very complex questions about an image. And you can also pretend, let's say, the large multimodal model to behave like an object detector or grounder. So you can ask to locate an object in the image and expecting pixel locations of the object that has been located as output. So basically, what we discovered is that these visual language models, not only large multimodal models, have very clear limitations. And we focus on two particular tasks that are prompt-based counting and open vocabulary object detection that are explained in these figures below. So for prompt-based counting, we are giving the model an image and a natural language prompt containing an object that we want to count. And the counting model outputs the number of instances of that object. Instead, in open vocabulary detection, we have an image. We have an open vocabulary, so a vocabulary of natural language sentences that are basically nouns taken from the English dictionary, but can be any language. And the detection model basically outputs the location and the extension of the objects in the image. So we found the following limitations. So prompt-based counting models basically struggle to understand the prompt because they tend basically to count even non-existing objects. That is a clear limitation in many downstream applications. And for open vocabulary detection, we discovered that they struggle to understand fine-grained differences. For example, if we are given as input two different vocabulary entries, white dog and black dog, we discovered that basically the model is confusing between the two different colors. So it finds the dog disregarding its color. So we have to maybe enter a little bit in the details about the common base that builds upon these models. That is contrastive representations. Maybe many of you already know, but model vision language models mostly rely on contrastively learned representations. And the most famous is CLIP that was introduced by OpenAI in 2021. Basically, what CLIP does is creating the so-called multimodal common space. Basically, you project an image and the text into the same common space using a different vision and text encoders, and you pretend that semantically similar image and text end up near together in that common space, while non-semantically similar, so semantically dissimilar elements end up far away in this space. And this enables a lot of very powerful downstream tasks, even in a zero-shot manner, so zero-shot image classification. It enables open vocabulary object detection and segmentation. And also, if you know, for example, delle 3, which is embedded in ChatGPT-4 for image generation, this clip is also empowering text-based image generation. So, yeah, what we say in this talk is that clip may have subtle yet important problems because may be blind to some features. So if we have an image of a white cat and the text a white cat, okay, we pretend it is possible that white cat and the image of white cat are near together in this space. But what if we give the sentence black cat? Is it farther away than the feature of the white cat with respect to the image of a white cat? And even we can do the same reasoning for counting, for the counting elements. So if we have an image of 7 cats, is it true that the sentence 7 cats is nearer to that image representation than the sentence containing 3 cats instead? So we perform some investigations in these 2 different works, and we try to understand how good are vision language models developed specifically for solving these tasks, so state-of-the-art models for these 2 tasks. And we ask what is the source of the problem. Is that the architecture, or maybe instead the data? And we try to propose ad hoc benchmarks for evaluating quantitatively these leakages of vision language models for these tasks. And we try to identify potential root causes. So I will start with this first work concerning prompt-based counting that actually we presented just a few days ago in Tucson, Arizona at the WACV conference. And yeah, basically, this is what prompt-based counting is. So you are given the model an image and some natural language prompt containing some objects to be counted, and you get as output the number of instances of that object. So, for example, if you input strawberry and this image, you should get 13. If you give an input blueberry instead, you should get 134. So, what we discovered is something very weird. So if you notice there is an image of marbles there, if you prompt the model with the class of the object that is actually present in the image, so the marbles, you get quite accurate results, so 66, that is a good estimate of the number of marbles. But the models, if presented with the prompt the elephants, also predicts an astonishing amount of elephants in this image, so more or less 57 elephants. That is, so let's say the model thinks that there are as many elephants as marbles in this image, and this is a clear limitation in many downstream applications where we don't want to count non-present classes of objects. So we propose this benchmark, the presence-aware counting benchmark, that is composed of 2 different tests. The first one is called negative label test, in which we present the model with the absent classes. So we have the image of a grape here, and we prompt the model with all the other classes in the dataset that are not grapes. And we expect that the result should be theoretically all 0 for these non-present classes. And we also present the mosaic test that basically tries to understand how much the model is distracted by elements in the image that are not pertaining to the correct class. So we create a mosaic image here where in the top part of the image there is the correct instance that we call positive image, and in the bottom is some random class taken, an image of a random class taken from the same data set, in this case strawberries. And in this case as well, we expect that the model only counts elements from the upper part of the image, keeping the lower part to 0.
And we define some metrics to capture this behavior. And here we have some results. I will not enter too much into details about the metrics here, but let's say that the noticeable thing is that on the classic metrics, that is the one on where all the state-of-the-art counting models report the results, more or less all the methods are equivalent, apart from some outliers. But on our metrics instead, we can see that there is a huge heterogeneity here. So depending on the architecture of the model and on how the model was trained, the model struggled more or less to understand that in that image there are some classes that have not to be counted. And also we have some qualitative results here that shows how many, maybe all the models are distracted by some classes that are not the positive one. And noticeably, we still have to go deep in the study of this, but it is worth noticing that the worst methods are end-to-end trained clip-based models. On this other work that was published at the CVPR last year, instead we focused on fine-grained open vocabulary object detection, so the other task I was talking about. So basically, in open vocabulary object detection, as I was saying, it is given an input, an image, and a vocabulary V of objects taken from a vocabulary, from the English vocabulary. Basically, we are not bounded to a closed set of objects. So at training time, this can be trained with a set of objects. At any reference time, we expect these models to work for different classes than the ones seen at training time. And so what's the point here is that since the vocabulary V is built of natural language sentences, no one, let's say, forced us to avoid to input to the model something like this. So not simple nouns, but complex, fine-grained descriptions of objects. So we fill the vocabulary V with, for example, a mug with blue rim and a plant with red flowers. And we show the following behavior. That is, the model basically discards any attributes of these sentences, focusing instead on the simple nouns that it finds in these descriptions. So basically, it finds all the mugs that it can find in the image, disregarding the fact that they had a blue rim or not. So we created, as in this case, a benchmark for capturing these failure modes of the models. And basically, we started from structured descriptions that were available in another dataset. And we input the structured descriptions into an LLM for creating a natural language sentence. So for example, a lamp with a white plastic shade and a gray metal pipe. So every object in its image have a positive description. And then we created some negative descriptions out of the positive one by randomly changing one or two or three attributes at a time, depending on the complexity of the benchmark. We have, in this case, 4 different levels of complexity that goes from hard, where we randomly change only one attribute, to the easy test in which we randomly change 3 attributes, and to the trivial case, that is the simple case in which we have very simple negatives that are basically sentences taken randomly from the same dataset, from the dataset. And so we input the image and the positive and the negative descriptions to state-of-the-art open vocabulary detectors. And without going too far into the details here, these plots on the right show that the more negative we present the model, so the more choices we present to the model, the more the model is confused to understand what is the real positive correct prediction. So, and okay, this is quite reasonable all, because the more negatives we give to the model, the more it is confused. But the noticeable thing is that even if we give one only negative, the model is often confused here. So even if we give the model the positive caption and one only negative caption, the model with some very high likelihood switches the scores, let's say, so the rankings of the positive versus the negative. Okay, yeah. So we just studied follow-up work on this, and we try to understand if clip is the main roadblock for fine-grained open world perception. And we basically made an hypothesis that clip encodes fine-grained information, but cosine similarity is not the right matching function. So basically, we employed some of the examples built, as previously explained, to build our benchmark, and we use them instead to fine-tune a matching function that is in this slide is the matcher, that basically tries to understand if in the clip embeddings are there enough information to discriminate fine-grained information. And actually, we succeed in this with even with a linear layer or a multi-layer perceptron, and ending up saying that probably the fine-grained information is present in clip, but we need probably some trained layers to extract it. So in conclusion, yeah, clip may be the issue behind visual language models, but more study is needed to better understand these failure modes. And the main takeaway here is that proper benchmarking is the key to understand and quantify the various limitations. And in the future works, we plan to also actually benchmarking large multimodal models that in this case we have not yet done, and try to overcome these limitations, for example, by using self-supervised visual models like Dino that seems more discriminative to fine-grained details. Having said so, thank you so much for the attention.
Thank you, Nicola. So we can move to the next and last speaker, Martina Migliani. And the title of the talk is Investigating the Semantic Abilities and Limits of Large Language Models. Please, Martina.
Yeah.
Okay, so hi. Understanding cause-effect connection is a hallmark of human cognition. The question whether large language models can truly understand causal relations is crucial for those domains that require inferential and interpretative accuracy. We know that causes precede effects, but causality is not merely temporal precedence. So the goal of our work is to investigate the knowledge of causal relations in large language models and to see if they can distinguish causal relations from temporal ones. To do so, we built Explica, which stands for explicit causality. It's a dataset that we annotated with the crowdsourcing data, and we carried out some experiments, and then we will see together these results. To arrive to Explica, we started from another dataset actually called Implica, in which the temporal and causal relations are not linguistically expressed. In fact, it is composed by 600 English sentence pairs. These sentence pairs are divided in three groups. In the first one, the sentence pairs are linked by implicit causal relation. In the second group, they are linked by implicit temporal relation, but not causal. And in the third group, sentence pairs are unrelated. Why implicit? Because we removed any anaphoric reference, causal connectives, and causal verbs in the sentences. So, Then, from here, we built Explica, in which temporal and causal relations between sentence pairs are expressed by explicit linguistic connectives. These connectives express the type of the relation, causal or temporal, and also the order of the events in this, of the relations, so iconic versus anti-iconic. So to express a causal relation in iconic order, so where the cause linguistically appears before the effect, we use the connective so. And for causal relations with anti-iconic order, we use the connective because. For temporal relations in iconic order, which means that they appears in a chronological order, we use the connective then, and for anti-iconic order, we use the after. These connectives were validated by a native English speaker, and we use them to link these 600 English sentence pairs in original order and the reverse one, and so in total we obtain 4,800 English sentences. We annotated these sentences with acceptability ratings through crowdsourcing. We asked the subjects to rate each sentence on a scale from 1 to 10 and to see how acceptable, to express how acceptable the connective is in expressing the relations between the events in the sentence. For example, Jude walked under the rain for an hour, so Jude got sick. In this case, so the use of so is highly acceptable because the two sentences have a causal relation in iconic order, so the rating is 10. In Mary bought some flowers because Jean went to the dentist. The use of because is not acceptable because we don't have enough information to say that there is a causal relation between the two events. So the rating is 1. And each sentence was rated by 15 English native speakers. So we use these ratings as ground truth for our experiments with large language models, and we wanted to evaluate them in under two aspects. As for performance, so prompt-based tests, we evaluated them with 3 tasks: acceptability ratings as the human ratings we see before, cloze test, and multiple choice. And we did that in several settings: 0 and few shot, with greedy search, and outlines, which is a framework that helps models to they guide them in returning their answers by choosing between a bunch of choices. Then we evaluated the models. We evaluated the competence of the models with the probability-based test. We used a perplexity measure. So we see how the models compute the likelihood of each sequence, and through these measures we obtain a score that we call acceptability perplexity score. We tested 7 instruction-tuned models, 2 closed models, GPT-4o and GPT-4o mini, and 5 open models, Falcon, Mistral, QN 2.5, Llama 3.1, and Gemma. As we can see from this first plot, here there are the results for each model averaged across all the tasks. We can see the results of prompting tasks in red with outlines, in few and 0 shot. In blue, the results with greedy search in few and 0 shot, and then the APS, the accuracy perplexity scores, are in violet. The first thing that we can observe is that there is an instability across scenarios and tasks, especially with greedy search, of course, but also for a commercial model like GPT-4o mini. Then we can see that the perplexity is actually more accurate than prompting for open models, and overall we can see that there is still a gap with humans, since also a state-of-the-art model like GPT-4o does not reach the 80% of accuracy. Then we decided to evaluate these models also by observing how they behave according to target relations and linguistic order, which was to analyze Falcon, Gemma, and GPT-4o over the acceptability rating task, and we also computed the APS. And we can see that the performance are strongly influenced both by the target relations. Temporal relations seem to be often confounded with the causal ones, and also the linguistic order affect the results, since there are differences between the relations in iconic, where the events are in iconic order, compared to those in anti-iconic order. Finally, we decided also to see how the model size affect both the performance and the competence of the models. So we pick a model family, QN, and we decided to analyze a bunch of models with increasing size belonging to this family. And we can see that the blue bars are correspond to the accuracy and acceptability ratings, where the red line is the accuracy perplexity score. And the APS is higher is higher than acceptability ratings accuracy on smaller model, but then this performance on prompting is higher with bigger models than APS. So we can say that linguistic competence is in some way partially encoded in smaller model, but it seems like that they lack the necessary scale to use such a competence in generation, as we can see for bigger models. Then we decided also to test some Italian models, so we translated Explica in Explicita. We translated it with the use of ChatGPT, and then we checked the translations manually. And the four connective we used for Italian are quindi and perché for causal relations, and poi and prima for temporal ones. The task we choose here were multiple choice to test the performances, and also here the perplexity for the competence. And we tested 4 Italian models. 2 native Italian model, Minerva and Velvet, with in different sizes, and 2 fine-tuned models, Lamantino 2 and Lamantino Anita. As for in this plot, you can see that the green bars represents the accuracy on the multiple choice task with greedy search, and in the blue bars represent the multiple choice accuracy with outlines. The red line still represents the APS as before. We can see that as for the English models, APS overpass the prompting accuracy, but we can see that there is a drop of APS in Italian models compared to English. We go from 0.66 of accuracy to 0.39. And then we also see that the size and the training setting do not affect performances as expected. We see that the size, for example, smaller models do not reach necessarily higher performances compared to the biggest one, as we can see for Minerva and also Velvet, and also that instruction tuning not always reach higher performance than the base one, as we can see for Minerva. Finally, the highest overall performance in prompting is reached not by an Italian native model, but by a fine-tuned model, as it is Anita. Oops, sorry. To conclude, the knowledge of causal relations is still suboptimal in large language models. The performances are strongly influenced by the relation type and the linguistic order of the events within these relations, especially for the temporal relations that are often misinterpreted as causal. The scale influences the relation among linguistic competencies and performances, since we saw that perplexity is more accurate than prompting for smaller models. Finally, Italian models seem to lag behind English ones in dealing with causal knowledge. This is our team, coordinated by Alessandro Lenci, and thank you for your attention.
Thank you very much. I have to thank all the speakers for staying within temporal bounds. You know, we have miraculously been able to finish on time. Unfortunately, in order to finish on time, we had to cut down on the question and answer part. So I invite everybody to reach up to the speakers during the break in order to ask questions and grill them. Okay, thank you very much.
Thank you. I wanted to thank all the presenters and the work package leader for this morning. In the afternoon, we will resume at 2 p.m. With work package number 4. And then we proceed today with the presentation of the new academic partner projects and the innovation grant with companies. So stay tuned and enjoy the lunch break now. Thank you very much.
Okay, let's start. We start? Okay. Okay, good afternoon, everyone, and welcome to the session for Work Package 4 of Spoke 1 FAIR project. The title of the work package is Human AI Socio-Technical Complex System. So it's sort of a mouthful of a work package title. So what we mean by socio-technical complex system is a system that integrates humans, AI, and technology into a dynamic and interconnected environment where the interactions between all the elements of the ecosystem evolve over time. The key characteristics of this complex ecosystem is the interdependence among all the players in the ecosystem, the adaptability. The system evolves based on the feedback, the learning, and the changes in the surrounding context of the players. Uncertainty, because it's a real system, so there are a lot of unpredictable behaviors that arise due to the interactions between human and AI agents. And also emergent phenomena, given that these interactions happen on top of a complex network. And of course, there are ethical and social consideration in terms of transparency, fairness, accountability, trust, and impact on society as a whole. So we want to keep the introduction short, so just to jog your memory, we will give you 3 examples that we gave you last year, and then with the highlights you'll see the novel stuff. So example of human AI socio-technical system is that of travelers that use a navigation app for driving around cities. So you get the feedback from, for example, Google Maps, and maybe we are in Pisa, we get stuck, and all we get the same suggestions, so we get stuck somewhere else in Pisa. So can we improve this kind of collective and unwanted effect? And there will be a presentation on that later on. Second example, the long-term impact of large language models. So the fact that as we are generating more and more data with generative AI, we will inevitably use this data to feed them back to the models, and this degrades the models. So the final result is that models start, let's say, to learn improbable events because they are not properly represented in the data that they generate. Third example, network effects. So when we do learning in a decentralized fashion, so basically you do it on top of a complex and possibly social communication network. So what are the emergent phenomena? How robust is this kind of learning to these distributed decentralized effects? Okay. So without further ado, just a list of the tasks. Our work is organized in 4 tasks. You can see the task leaders in the slide. There are a lot of people involved in this work package. Myself and Dino are sort of the coordinator, the work package leaders, but you see a lot of people both from the critical mass of FAIR and also what we call the support group, and also newly recruited researchers. So the support group is those people that are not technically paid by FAIR, but they work on FAIR-related topics, and actually they are a crucial element to the success of the project and of the work package. And of course, there are also several PhD students. This is some stats about the publications. So we have 28 conference papers, 26 journal papers, 7 preprints, 1 book, and 7 book chapters. So I would say this is quite successful. And you will see in the next hour 6 highlights, and we try to favor those presented by young researchers in the FAIR project. So you will see PhD students, research fellows. Of course, it was not always possible, so you will also see some senior people. So these are our 6 highlights, which I will not present because you will hear a lot about them in 1 minute. There will also be a poster for the work package by Gizem Gedzici from SNS. about characterizing model collapse in large language models using semantic networks and next token probability. Okay, so we can move on to the first highlight.
Okay, thank you, Chiara, for the presentation. And I'm Erika Kau, and I will introduce you why social, an LLM-powered digital twin. So let's start with the definition of the digital twin. A digital twin is a virtual replica of something that exists in the real world. For example, a replica of a school or an hospital to study, for example, the implication of adding a new structure and make tests that wouldn't be feasible in the real life. With Professor Giulio Rossetti, we introduced Why Social, which is a replica of an online social media platform that has the aim to allow for realistic social simulation, but in a controlled environment. So, for example, if we are computational social scientists and we want to study political polarization, we could set up a scenario on Why Social where LLM agents interact about a specific topic we give them in input. Why Social is organized in 4 different components because agents, these LLM agents, can interact by mentioning, posting, and reacting to the content generated from other agents. These agents can create contents and share multimodal posts, so they can share also images and news from RSS feeds. And all our agents have also a lot of interests we can set up in the initial stage, you will see later, and their interests and interaction evolve through time. Additionally, you can set up specific persona, and all our agents have different socio-demographic profiles and different personality traits. So the idea of this presentation is to show you a demo of this user interface. So you will see this Twitter-like social network populated with LLM agents. And I will explain you something more about how we realize it. So let's start with the interface. The idea is to have this Twitter-like environment where users, these LLM agents, can interact. And you can see that these posts are commented by other LLM agents. And one interesting thing to help researchers is that all the posts and comments are tagged by an LLM itself, in this case, Llama 3.2, and they are tagged with the elicited emotion and the topics. So you can create ad hoc scenarios. And each post is also tagged by the hashtag. In this case, you can see that if we click on hashtag ecology, you can find all the posts grouped by the hashtag. You can also see that each agent can comment and like the posts posted by another agent. Here's also the role of the admin. The admin is a real-world user. So the idea is to implement in the future a kind of human in the loop. So we want to, for example, study the effects of LLMs on real-world users, or vice versa. Another thing I want to show you is the experiment setup, because this fictitious social network has an architecture with the server and client, so you can set up a server, and then you can create a population of agents. These agents can be created by a method we implemented. There is on the left the button population, and as it's shown here, we can create a synthetic population, load from a file, or create one agent at a time. In this case, we can create a synthetic population by adding the population size, choosing the LLM model, choosing even the recommender system. So in this case, we can study even, for example, the effects of the algorithmic bias, which is something very interesting in previous research. We can also set up socio-demographic attributes, and then the idea is that we can start the simulation. Additionally, we can even set up the length of the simulation. For example, we can have agents discussing for 10 days. And another interesting thing is that Why Social is not a closed system. So agents can interact even with real-world news. We can integrate an RSS feed. So, for example, we can integrate, in this case, the BBC News RSS feed, and here agents can interact, for example, with already the recent news shown on the right. So we hope to release this interface soon, and we hope to help you in research on polarization and, for example, computational social science. So thank you for your attention. If you want, there is the QR code of the project, and if you have any question, you can ask Giulio Rossetti. Here's the mail. Thank you.
Okay, hi everyone, good afternoon. I will be presenting a slightly different topic. Me and Hans-Jörg are from Scuola Normale Superiore in Florence, and we do the political and social part of AI and its technology. So we were tasked with understanding the social and political effects of AI technology, and we started by looking a little bit at the EU AI Act, so how that was negotiated and whether there was some request on behalf of public opinion on regulating certain systems, and this is taken from the Eurobarometer. It's the data from April and May 2024, and basically, as you can see, there are many European countries that are asking to regulate AI technology according to the core values of the European Union. Secondary data, however, the one that's available, the one that we had a look to, is sometimes it leaves a little bit, it gives just very general opinions or attitudes and doesn't really go into whether there are ethical divisions and political divisions on specific issues of AI, right? So they're very general. And they're subject to desirability bias as well. So what we did is we decided to use the European elections, the European parliamentary elections in 2024 as a case study to see whether the topic of AI and its regulation was becoming political, especially vis-a-vis the regulation that was just coming into action. And yeah, so basically what we did is we looked at the AI Act, how that was negotiated, how, the framework came into place, also questioning ourselves how the risk-based frame came into place, how that was negotiated. And then we looked at the topics regarding AI. In order to become politicized, a topic must be salient, of course, must be discussed by multiple actors, so public opinions, politicians, and other stakeholders. And finally, it must become a contentious topic at one point. So you can have like different viewpoints on the same issue. So again, yes, we looked at the negotiations, and then we traced on the political manifestos of the European parliamentary elections of last year, and we traced the issues that were mentioned and the values that were mentioned together with them, and solutions for regulation. And the last bit of our research, which was actually very challenging, very long, we did a live coding throughout the last month of the campaign, of the electoral campaign. So that was in May and the start of June of 2024. And we live coded all of the posts, Twitter and Instagram posts of certain political actors that we were interested in, so European parties, Italian parties, the Spitzenkandidaten, and a pool of expert of people that were involved in the EU AI Act. And so basically these are very quickly, I'll give you the overview of our result. So in negotiations already, many topics emerged as conflictual. For instance, who was in charge of certain regulation, whether I don't know, whether foundation models and companies that regulated foundation models had to take on the challenge, or the startups. So already we saw some differences. This campaign, Reclaim Your Face, highlighted the importance of regulating certain biometric technology vis-a-vis the obviously privacy of citizens, and before this became relevant, biometric recognition wasn't discussed as highly challenging and invasive. I'll give you an overview of what we found on the manifestos. These are the European parties and their group. So I looked at all the manifestos, and basically I tried mapping in this framework all of the issues that came up in the manifestos, trying to obviously organize them on this framework. This framework goes from different scenarios, socio-technical scenarios, for instance, or attitudes towards AI. So we have on the vertical line, at the bottom, cyber skeptic, and then up top, cyber enthusiast, and then from left to right, we have like the responses, the regulatory responses that the parties were asking for. And without going too much into detail, I'll just talk about the areas that we found. So there's the regulatory liberal market narrative, which emphasizes the importance of financing big tech, having a global lead as the European Union on the world. There's a lot of emphasis not to be not to be competitive vis-a-vis China and the US. And there's on the opposite side, there's a regulatory individual and civic right narrative, which emphasizes the importance of protecting citizens' data and other stakeholders' data, journalists' data, for instance. They oppose surveillance. They tackle the digital divide, the problems that workers encounter, and they place citizens before businesses, and data dignity. And then there's an intermediate narrative that stands somewhere in between, and these were how the parties were basically placing themselves on this map. So you can see that there is a political division that follows the political division that we already know, more or less. So we have parties organizing themselves between like the center part, left and right. From the coding, we coded all of the Twitter posts. As I was mentioning before, we did a code book, then an Excel sheet, and manually coded all of these posts. These are the topics that I was able to summarize. Okay, I'll give you just like a quick a quick example, like fighting online violence and harassment, which obviously included many other subtopics like cyber violence, cyberbullying, and so on and so forth. And then lastly, for each political actor, we traced what the topics that were mentioned the most, and basically we find consistency. So we have center-right, experts from the center-left, and centrist actors, and basically we find that more or less they talk about the same issues with the same political angle as the manifestos. So you can see that there is some kind of politicization around AI topics. However, you can't see it here, unfortunately, but all in all, so yes, we can trace a slight politicization. There are contentious topics on issues of AI technology and different ways that, different regulatory responses that different actors praise. However, unfortunately, you can see it, but the topic of AI per se was rarely mentioned in the electoral campaign. So it's a politicization, but it's slightly delayed. So we'll see in the future if this carries on and becomes like an issue that is more contentious in public opinion as well, so not only on stakeholders. Thank you.
Okay. Okay, hello everyone. I am Federica De Santis and I work in the Department of Economics and Management, so I will give you a perspective more like the social one than the technical one. The highlight I would like to present here today is research we are conducting on how the use of artificial intelligence and maybe the promise of artificial intelligence are impacting an accounting profession, a specific category of accounting professionals that are financial statements auditor. The motivations for conducting this study is that there are several claims about how disruptive AI could be in all the accounting industry and specifically for the accounting professionals. Someone has predicted that 98% of accounting professionals will be substituted by AI in the next decade or two, or at least there will be a lot of automation in this industry. So we were concerned about how professionals perceive this claim and this potential impact on their activity, and how far are the certified public accounting firms in adopting AI technologies and how much AI is used in the accounting profession. We know from the website and other claims of the big four that are the biggest accounting firms in the world, there are a huge investment in AI technologies, but it's difficult to grasp what is actually their involvement in the use of this technology. For sure, we know that AI can intervene in almost all aspects of the audit profession, and it could provide auditors with several benefits, such as reduction in human errors and bias, facilitation of continuous auditing capacity. They can track patterns of data starting from financial data of the company they audit, and obviously this could lead to a reduction in audit cost, and from the client side, a reduction in audit fees. Of course, when we introduce new technology within a profession that is considerably bounded by a set of rules, regulation, and guidelines, we must also take into account the distinctive challenges that can be determined by the use of a new technology. And specifically in the audit profession, which deals with providing assurance on the reliability of the company's financial statements, we can see different types of challenges that relate to technological issues, organizational issues, and ethical issues. Another strong motivation that give us the kickstart for conducting our research is that since the 80s, we are witnessing several claims about how technology will disrupt the accounting professions and especially the auditing profession, but usually they were just flash in the pan. So we asked what's new about the use of AI in auditing, and we noticed that while previous technologies were claimed to mostly automate the audit profession, the AI and specifically natural language processing technologies and large language models have the potential to not only automate repetitive tasks but also augment cognitive tasks in the audit process that require professional judgment. That is what makes auditors professionals. So we adopted a specific theory to understand the beliefs and the behavior of the auditor against the use of AI. That is the paradox theory. And we posit that when a professional is challenged in using a new technology, can experience different types of paradoxical tensions that are tensions that are made by interdependent elements that cannot be solved so easily. So they pose significant challenge to the people who must confront these paradoxes. And when introducing AI in the audit profession, we can see all the 4 types of paradoxes that are learning paradoxes that manifest themselves when the old versus new conflict. So the established set of knowledge conflict with the new skills and competence that can be opened up by means of technology. But we also experience belonging paradoxes. That is a conflict between who I feel to be and who can I become by acquiring new skills and competencies. So it's a kind of a tension between individuals and group. Who am I as compared to other groups of people and other groups of professionals? Then we have organizing paradoxes. That is the typical conflict among routine and change. And finally, performing paradoxes that are tensions that are fueled by the need to fulfill competing stakeholders and competing demands. All of these paradoxes emerge in the audit profession just because of the nature of the audit profession that is highly knowledge intensive. These auditors are a type of professional that are very distinct from other accounting professionals. The audit profession is often referred to as a ritualistic process in which the auditor performs specific type of procedures in order to provide assurance to stakeholders. And finally, it has commonly established the need for the audit profession to answer multiple and often conflicting demands. As you can imagine, the need of providing assurance to the corporate stakeholders as compared to the very commercial nature of the auditing companies that are firms. They must conduct their business, so they must earn something from their activity while simultaneously complying with law and regulation to provide assurance to third people. So we asked what kind of paradoxical tensions emerge in the audit profession due to the introduction of AI, and how do they interact? And finally, what are the responses the auditors give to this paradoxical tension? And we try to answer this research question by conducting qualitative research, by interviewing a number of 16 auditors from the biggest audit company, but also the smaller ones, in order to have a possibly detailed picture of the audit environment. And we were able to distinguish these paradoxical tensions emergence and interaction into 3 main levels: the micro macro level, which refers to individual auditors, individual professional, a meso level, which refers to the audit firm level, and finally, the macro level, which also involve other actors within the environment, and first and foremost, the audit regulators. So at the micro level, we can see the key paradoxical tensions relate to learning and belonging paradoxes. Auditors showed different behaviors, different perception about the use of AI, because some of them feel the advent of AI as a big opportunity to acquire new skills, new competencies, and to advance their profession, while others experience the fear of losing their job and the fear of losing their professional identity, because the advent of AI has led the auditing companies to acquire people from other industries, such as and other professionals such as data scientists and other people with no specific experience in accounting and auditing, but in other fields of professionalization. So at the micro level, we both see virtuous and vicious cycle. So who feel the AI as an experience to spur innovation, started virtuous cycle of adapting to this new technological environment and to deploy AI to improve the way they are providing assurance, while the auditors, the individual auditors with a distinctive fear of losing their job and of losing their identity as professional, used to resist to the change and to remark their relevance as professional accountants. At the meso level, so and at the level of the audit firm, we see that the key paradoxical tensions, the key challenges were the need to align individual auditors' perception with firm-wide AI adoption. So audit companies and the managers of the audit companies need to take into account what their employees perceive about the advent of AI in order to proficiently include these technologies in their work. So another key challenge was to balance innovation with regulatory uncertainty. One of the big challenges in the use of AI in the audit environment is related to the absence of a specific regulation that allows or constrains the use of AI in the distinctive audit procedures. So the auditor are kind of blind in applying this technology in order to understand what to do and how to keep providing assurance while using AI. So, so the key things we noticed is that the audit firms try to hide the use of AI from the regulators. So AI is not involved directly in conducting audit procedures, but mainly is used for learning purposes and for enhancing the work of their employees by using generative AI models in order to assist auditors in searching for the best procedure or in interpreting the results of the traditional audit procedures. Thank you for your attention.
Okay. Good afternoon, everyone. I am Caterina Pareo, and I adopt another point of view because I come from the Department of Law. The focus of my research concerns the key role of workers' participation in the regulation of AI. First of all, I would like to thank the organizers of this interesting event for the opportunity to share my research. So let's start. As you know, the implementation of AI for workforce management presents many advantages. For example, can improve the efficiency of organization and working methods, can help to control the labor costs, can ease hiring processes, and then can improve safety standards at work. But on the other hand, the use of AI in their workplace could also present many risks. AI, as you know, can take unfair decisions or can undermine the dignity of the worker because of the pervasive control of the workers. Or in some cases, AI could present a risk of discriminatory decisions. So to deal with these risks, we need to set rules about how AI is used at work. And from this point of view, I think that AI Act and the EU Directive on platform work are a good starting point. AI Act set rules about AI using a classification of AI systems based on risk. On the other hand, the EU Directive on platform work concerns the phenomenon of the algorithmic management in the digital labor platform and provides rights for workers of the digital platform. So, question arises. Do the principles set out in the European legislation provide sufficient guidance? I think that these principles represent a good starting point, but I think that they are not sufficient to guarantee an effective identification of the risk associated with the use of AI in the workplace. So another question arises. Could workers' participation help to regulate AI in the workplace? About this topic, Article 26 of AI Act provides for an obligation of information for the deployers who are employers, who shall inform workers' representatives and the affected workers that they will be subject to the use of the high-risk AI system. But AI Act doesn't provide for an obligation of consultation, which is different from the obligation of information. The study of the Italian legal system offers interesting insights about the so-called participative tools used to regulate technologies. In particular, Article 4 of the Italian Statuto dei Lavoratori established that employers and workers' representatives have to adopt a collective agreement in the event of the use of technologies involving remote control of workers' activities. In this case, the technologies used in the workplace are regulated according to the context in which they are adopted, their purpose, and according to the effects they produce on workers. The main question of my research is if workers' participation in the regulation of AI could ensure a more efficient identification of the risks associated with the use of AI and the shared identification of measures to be taken in the case of materialization of those risks. My research is now focused on researching collective agreements on AI in the workplace, and I hope that I will be able to share the results of my research on collective agreements at the next workshop. Thank you for your attention.
Hello and good afternoon. As you can see from the title, I'm not Giuliano Cornacchia, who was expected to have this presentation. He's one of the young researchers behind the fair who passed from a PhD to a postdoc, but today could not be here. I'm a kind of a makeshift presenter, but I will try to do my best. The line of work regards understanding what are the effects of AI-assisted services, in particular in the context of mobility, where we have mobility demand, so people that needs to move, and their movement obviously has some collaterals like emissions. And we are in the context where this simple task has an intermediate, which are AIs like Google, TomTom, etc. All systems that are able to provide excellent suggestions for the individual, but leaving open the question what happens if thousands of users get excellent individual suggestions. The news provides us quite a lot of anecdotal answers. The answer is, well, something wrong. Like in the famous example of Leonia, where the traffic of an highway was, let's say, nicely channeled through a small city, creating great issues. We started this line of work trying to have a more scientific approach to this problem. And so we implemented a simulation framework that starts from real mobility demand on one side, and then ask for each of the thousands of users we are simulating to the navigation systems from Google, TomTom, etc., what should be the route to follow. And then we actually simulate with a micro simulator what happens if we put all these vehicles physically moving in the same space, so with conflicting let's say, objectives. You can see here some sample results in 3 cities where we see what happens when the percentage of vehicles on the roads that actually follow these AI's suggestions instead of moving more or less randomly in terms of emissions. You can see in the lower parts with the boxed lines that in some cases everything gets better. So using AI is really better. Unfortunately, these are the cases where roads are almost empty. The traffic is very low. So it's the easy part. When we go in the difficult part, which are the top lines, when the traffic kind of try to really use the road to its limits, you can see that there is a moment where increasing the percentage of routed vehicles is not beneficial, but on the opposite. Okay, there is a moment after which the AI suggestions are, let's say, misleading in some sense. We can see, let's say, an answer to the first question I gave, why this is happening, basically in terms of route conformism. What we can see with these plots, again, is that the increased usage of these systems reduces the distribution of traffic on the road network. So basically, the same resources, the same roads are used more intensively because the same shortest paths are more appealing to everybody, and so everybody tries to follow them. So this, let's say, suggests another question, which is how we can balance this phenomenon and so reduce the collaterals of these services. So the idea is to inject in somehow diversification mechanism in the routing provided by these systems. And to this purpose, we implemented a system named METIS, which integrates several nice features like generating several alternative routing, looking also at the short future, so where vehicles will be during their trips, and finally implement some heuristics to select the best routes, the most promising ones. The results summarized here very briefly are basically that our system, which is in the bold one, is significantly better than the best of the competitors, which are in turn already better than the baseline, which is, let's say, the navigator as is. So, positive answer to our question, can we do something? The answer is yes. At the same time, this answer raises another question. I know that the chain of questions is infinite, and this is the third step, but I will stop that. Don't worry. What we can observe from these plots is that actually the improvements we can obtain injecting this diversification is very variable. In some cities works very well, in others very little, In others, again, does not work at all, but I'm not showing them here. So the question is why? Okay, why effectiveness is so variable, and what are the factors that drive it? We started this third episode, let's say, of our saga, defining more formally a measure of route diversifiability, sorry for the terrible name, in terms of two factors. Notice that the name of the measure is a kind of pun on the diversity and cities. Basically, we put together on one side the number of possible alternative routes that we can find for given an origin and a destination. The more alternatives we have, the better. It's more diversity. But at the same time, you also measure how similar they are, because I mean, just changing the last 50 meters of a trip is not very interesting. Okay, and so we studied this measure. You see an example here on the left where this diversity factor is very low because we have just one single reasonable alternative. The red ones are not reasonable. They take too much time. In the other cases, like in the right side, you have several nice alternatives. So the diversity index is higher. We simulated massively a massive number of users in more than 50 cities around the world. And you can see here the distribution of these values, where you see on the left poorly, let's say, cities where the diversification is more difficult. So you have Mumbai, Rio de Janeiro, Dubai, Istanbul, Moscow, Amsterdam, etc. On the other side, you have a few Japanese cities, which were kind of expected, together with Sao Paulo, which is a surprise. Okay, so we have some variability across different cities. And analyzing more in detail geographically where this diversifiability is located, we see that city centers, tends to be less, have a lower diversity, while as we go outside, things improve a bit, with some exceptions, like, for instance, the city of Rome, which has a kind of stop point at 10 kilometers from the city center that, unsurprised, is actually the grande raccordo anulare. And if you plot actually the suggestions given by these systems, you see that they're concentrated there. We extended this work. I will be very short because my time is over. Basically, we compared this distribution of diversification and the presence of similar structures, which are, let's say, the grid attractors in black here. In particular, you see that in Rome, they correspond quite well with the red areas. But you can also see that in other cities, having these attractors does not correspond to low diversity scores. Just to make it short, the answer is, our conjecture is that the real factor is the presence of sparse and strong attractors in the city. So the fact that there are just a few of them, not the fact that they exist. If you look at Japanese cities, indeed you have a lot of them, but they form kind of a grid. Okay, so that's the point. Several, let's say, things for the future work, including use of machine learning to better routing, etc. But let me close here and take questions maybe offline, or you write to the main author, Giuliano. Thank you.
Thank you very much. I'm Marzo Di Vece. I'm a postdoc at Scuola Normale Superiore, and this presentation will be shared with Chiara Boldrini because Jack Tucky is not here. And I will talk about a method to pass from sequential data to relational data. What we want to do is to take any kind of sequential data, for example, a time series regarding blood oxygen level in brain, or stocks in finance, or human AI ecosystems, and try to understand and characterize their correlations, so their activation, their simultaneous activation, their co-activation, air correlations. So what we do here is, in our pipeline, we have the brain, two regions of the brain, What we do then is we sort those time series, and we do the multiplication between them that quantifies the correlation and anti-correlation between them. Then we sum over the time, and then we create what is called the co-fluctuation matrix. However, we want to see if the co-fluctuation matrix that we see is the result of some constraint on the time series. And when we filter that, we can see the redundant information of this co-fluctuation matrix, and then study different communities. These communities can be communities of AI systems or AI agents, communities of brain regions, or communities of stocks that move in the same way. For the methodological part, what we use is an information theoretical model based on the maximization channel entropy. So we want to maximize the uncertainty of our system, so reduce to the minimum our assumption without using thresholds. And we want to maximize the channel entropy by constraining some global or local properties. For example, global properties on different sequence and different times, or local properties specific to times or regions, in the case of the brain. Usually what you do is you fit the model using some optimization algorithm, generate many realization, and then extract your statistics of interest. In this case, we will not use sampling, and we will do it analytically, because we can do so, and this this renders our methods very fast and usable also for large-scale systems. So, for example, instead of the correlation, we will use something called signature that here can be seen as the number of concordant values minus the number of discordant values. So the number of co-activation and deactivation in the sense of concordant values, and the anti-correlations between different time signals. For example, you can think that you want to see the number of times different AI agents behave in the same way or activate in the same way, and or when they are activated in contrast with each other. However, we can extract the distribution analytically with our models, so that instead of sampling, as I said before, we can do everything analytically. And so, if we take brains as an example, we explore the space of 1,000 individuals or in 1,000 brain systems. And what you usually do in the state-of-the-art literature of neuroscience is you see the correlation, then you put a +1 between two brain regions if there is a positive correlation, or 0 if there is no correlation, or negative if there is anti-correlation. In reality, what is in the state-of-the-art of the neuroscience is that they filter correlations below a certain threshold, so that every sequence analysis depends on the thresholds. In here, instead, we do a sort of outlier detection. We have our hypothesis, and we put a +1 if the correlation or signature that we see is above those that are expected, and negative if they are below expectations. In doing so, if you can see on the left, there is the naive projected matrix, and on the right, you have filter matrix with, let's say, a lot more zeros. But why this is important? Because we have a clear insights in how brain regions, for example, cluster themselves. Using specific methods for side networks that are still in development right now, we can minimize the Bayesian information criterion and see that when you go in detail and see what they correspond to, these communities, you can see in the naive projection that they represent the state of the art from now. But when you go to the filter projection with our models, what we see is that there is an highlight on negative links. And in 2024, they saw that negative links are especially important in the integration of information between different brain regions. And finally, what we discover on 1,000 on 1,000 individuals is that when computing balance energy, that just says for example, you can think this on a part of the social media or social network, and you will like triads that refer to balance theory, so friends of friends of friends, and not many unbalanced regarding this structure theory. When you use on-brain networks, they see something like that, but we see that with our projection, we have an increased number of unbalanced triads and a decreased tendency to make up, so the connections are less localized for positive and negative links. So finally, this is a methodology to have a clear insights of brain networks or stock networks or AI systems in the future. Thank you very much.
It's not over yet. I will briefly tell you about a different type of signed network, which are social signed networks. And this is it was the research topic of Jack Tuckey, who was a research fellow in the FAIR project, and now he's working in Canada, so he could not, of course, be here with us today. So here the motivation is a bit different. So if you have been working with social media data, you know that the typical proxy for social tie strength is the frequency of interactions, which was not the only dimension in the original definition of tie strength by Granovetter, but is in practice the only one that is used in the related literature because it's so easy to compute. However, it is, I believe, like everyday experience that if you have an angry neighbor whom you fight with every day, let's say that the relationship with that person is quite different from a relationship that you might have with a best friend that you, I don't know, interact with. Maybe you give him a phone call weekly, okay? So the goal of this research line is to sort of capture this qualitative dimension of social relationships. And we do this by attaching a positive or a negative sign to relationships. And this is actually the contribution of Jack's work. So basically, he designed a pipeline, a method for extracting signs for social relationships, not just for single interactions, so not to a conversation on Twitter, but all the conversations that users have over time, they contribute to the definition of this sign. Guess what? We applied this method to Twitter, now X, and what we discovered that Twitter is a very negative social space. And if you look at the innermost social circles of users' personal network, you see that those circles are more negative than the outermost circle. So on Twitter, X, people, they interact a lot, and when they interact, they typically fight. No surprises there, but then we applied this method to other domains, so for example, stance detection or to investigate cultural effect, but our time is over, so I will stop here. Okay, so that's it for our session. We didn't mention it explicitly at the beginning because we wanted it to be sort of a surprise, but as you have seen, I believe this session sort of gave you a concrete representation of the diversity of the work package, because there are computer scientists, physicists, law scholars, economists, sociologists, so it's very interesting to see all these different perspectives brought together and working together to achieve the goals of the project. So, Dino, you want to add something?
If I can just add a word, I think that the common thread that is characterizing the work in this work package is actually the ambition not only to understand better the impact that AI has on society, but also the other way around, the impact that society can have on the development of technology, to study this, how technology and society influence each other, adapt to each other in a co-evolutionary sense. And we believe this is very much important if we want to somehow not only predict the future development of our societies, but also maybe to find new forms of technology that are more respectable of our objectives and somehow are able to become part of the solution instead of being part of the problem, as we observed in many circumstances today. I just wanted to add to this, and I would like to thank very much all the, Chiara for organizing the session, and all of you for this fantastic contribution. Thanks a lot. We now, just a couple of minutes for shifting the stage, and we proceed with the new partners of, academic partners of FAIR Spoke One. Okay, welcome everybody to this important new session of the program for today, which is getting to know the projects that are conducted by our new academic partners that were affiliated to our FAIR project at Spoke One, Human-Centered AI, through a public competition that took place last year. And you can see, together with my colleague Francesco Marcelloni, that coordinates the Spoke with me, we have Giuseppe Riva, Professor Giuseppe Riva from, Giuseppe is a professor of psychology at Università Cattolica del Sacro Cuore a Milano. We have Stefano Melacci, who is an AI engineer and, from University of Siena. We have Paolo Nesi, at University of Florence. We have Francesca Chiaromonte and Andrea Vandin, colleagues from Scuola Sant'Anna, and Professor Stefania Bellavia of University of Florence. We are still waiting for Diego Garlaschelli to join us. We'll see. The idea is to have now a first round explaining the projects that following this order that our colleagues are developing in collaboration with the project, and so I would like to pass the stage to Giuseppe Riva. Yeah,
thank you, Dino. If you can, yes, move to my presentation. Just a few words about myself. I am a cognitive psychologist, and I'm now the director of the Humane Technology Lab at the Catholic University of Milan. In particular, this lab is exploring the link between humanity and technology. So through an interdisciplinary partnership, in my lab we have researchers with different disciplines, many from humanities and many students from this national PhD program. And the idea is to understand some more about this link between the human and the technology. And my project, the project I'm discussing here with you today, is called Cognitive Decision Intelligence Framework for Explainable AI Systems. The focus is trying to integrate the reflection of cognitive science, the research of cognitive science in the design of explainable AI. So the basic idea is starting from what we know about cognitive psychology, and in particular about the process of decision making, and using this knowledge in order to improve the efficacy of explainable AI system. So we can say that the focus of our research is decision intelligence. So understanding how we can put together machines and humans in order to get better decisions. And we have a lot of background in cognitive science that I will try to summarize for you, because I have just 20 minutes to discuss. Where we started from? We started from the roadblocks. So we try to understand, using a systematic review, what is happening in the field of the cooperation between humans and artificial intelligence. And in the last few months, we found a couple of papers that I want to share with you that are putting in a different light what is happening in this field. This one is a paper that probably some of you already know. This was a paper published by a colleague, a young PhD students in the MIT, and they did a very interesting systematic review and meta-analysis. They asked, but what happens when we put together AI and humans? It will improve the performance or not? It's a basic question, but no one tried to solve it before. And they found that the answer is no. Typically, AI and humans perform worse than the best humans or the best AI alone. And in particular, this lack of performance in the union between the two sides is worse when we have decision-making tasks. When we have decision-making tasks, well, human AI teams perform typically worse than human alone or AI alone. And this is quite surprising. And why? What they have found? I think that also this is quite interesting. They found that when the knowledge of the human is better, higher than the one of AI, well, AI improves performance. If instead humans have less knowledge than the AI system, this is much worse. Why? I will try to explain you why in a few minutes. Another paper, very, very interesting, also this one published on the same journal, Nature Human Behavior, a couple of months ago. Again, they asked, but what happens to the human when AI and humans interact? What are the effects in the three levels of emotional, perceptual, and social judgment? So they found that AI reshapes these features. So AI is not a neutral tool, but is a tool that strongly modifies the way the human perceive the situation. There is another paper I have not presented here, but was published 2 weeks ago, always in Nature Human Behavior, that discusses this for large language model. And again, they found that people overestimate the knowledge of large language model, and when this overestimation is not clearly expressed by the prompt, typically users makes wrong decisions. And what is interesting about this second paper? Well, we found two interesting things. The first one, that even a slight bias in the AI training system produce a huge disruption in the human. So the big issue is when the system, the AI system, has biases, these biases are in some way even bigger for the humans. And even worse, humans are not aware of the biases. And these, again, disrupt a lot their decisions. I think that these two papers underline that the process of human decision-making is not easy, as we can expect, in the sense that some people still think that most of the human decisions are based on rationality. But since the work of Professor Kahneman, we know that our brain is based on two different systems, intuition and reasoning, that are totally different. But what we know now is that the picture is even more complex, that there are more layers of complexity that these papers underline. In particular, now we know that cognitive load also plays a critical role. And another emerging area in my field, in neuroscience, is the one of brain synchronization. We know that brain synchronization between humans is another critical feature that influences a lot the process of decision-making. Try to simplify. Well, System 1, System 2, I'm sure that you are aware of that because the FAIR project has a specific line on this. But probably less are aware that when we use System 2, so when we use rationality, we have two different routes. So even rationality can be high-level rationality or low-level rationality that is called central root or peripheral root. So even when we use rationality, the way we decide is different, and it depends on how we process information. So the way how we process information influences a lot the final decision. So when we speak about system 2, we have to distinguish between central root and peripheral root, because the way we use rationality in the two ways is totally different. And another very important knowledge that neuroscience underlined is that, well, if you remember the first paper and the second paper, a critical issue is that when humans interact, their biases do not increase. When AI interacts with AI, this increases the biases. Why? Well, we discovered that in the human brain there are different processes that have the goal of reducing distances between humans. The first one was discovered about 30 years ago by Professor Rizzolatti. Is the discovery that in our brain we have specific neurons that are called mirror neurons that are able to tune in with other people. And in this sense, we can reduce the cognitive distance, and even in the presence of biases in the other person, if we can tune in with him, we can reduce the impact of this bias. And even more important, in the last 15 years, neuroscience has discovered that this process is still improved by another incredible mechanism, interbrain synchronization. So what was discovered using a peculiar technology that is called hyperscanning? It was discovered that our brain can sync, and this syncing produces a homogeneity effect between the brains that reduce the impact of biases. So how we can manage bias? Through interbrain synchronization. And this process of interbrain synchronization is critical in physical communities. For instance, this is a very interesting paper published by a colleague that explored interbrain synchronization in a classroom. They try to understand what happens in a classroom when teachers and students pass time together discussing about a topic. They found that the more the time they spend, the more is the interbrain synchronization, and the better is the knowledge of the topic. What is the critical feature behind this process? Shared attention. Shared attention is the basic biological mechanism that is able to reduce the impact of biases between humans. And what does it mean, and how we are trying to exploit this vision inside our project? Well, the first point is the introduction of the concept of system zero. We said how we can put the AI in this complex equation. Our first suggestion is saying, well, we can have system zero as AI as a form of cognitive extension that is able to provide contents to system 1 and system 2. So the role of AI may be the one of selecting and curating information that then can be handled by the system. But this is just the starting point, how we can create a cognitive extension. Well, another interesting topic, I know that is quite different from your typical literature, so sorry for that. But again, another critical question emerged by neuroscience is why we have interbrain synchronization. And we discovered that interbrain synchronization is used for two different processes, totally one on the opposite of the other. The first one, obviously, is confirmation synchronization. So the idea that synchronization is used to reduce distances between humans. But recent studies underline that is not only confirmatory synchronization. We also have disruptive synchronization. What is disruptive synchronization? Well, it is what happens when a teacher provides to the student a novel concept that is not easily framed by the student. And this generates a desynchronization between the teacher and the student. But after some times, if the student is able to cope with this new concept, the brain syncs again. So the basic idea is that if we want to learn from our experience, we know that we need adaptive synchronization. So not always we need to be confirmed in our belief. We need also different situation in which happens the opposite. We are challenged in our belief. But inside the frame of brain synchronization, this makes the difference. And this is the conclusion of my talk. What we can do now in order to improve the efficacy of explainable AI? Well, this is a paper we have prepared with Dino Pedreschi. The idea is that we have to find a way to have in the interaction with AI these two different phases. So AI can support our belief, but sometimes it also has to challenge our belief. And the biggest issue now is that most of the AI system, LLM for sure, try to confirm and never disrupt the knowledge of the individual. And another emerging idea that I've discussed a few weeks ago in the US with some colleagues from Hewlett-Packard Enterprise is the idea of creating a synchrony between AI and the human brain. How? Well, there is a process that is well known by physicians and by neurologists, that is the one of neural entrainment. So the use of external stimuli such as sounds and lights to induce synchronization. When we are in a disco, the rhythm of music makes us to synchronize automatically. Well, an emerging area is the ability of generating neural entrainment through artificial intelligence in order to sync brains and simulate this brain synchrony that is behind the future of human evolution. Thank you very much for your attention.
Thank you so much, Giuseppe. Very insightful presentation. Next in line is Professor Stefano Melacci from University of Siena. I'll try to find out the slides.
All right. Thank you very much. Okay, so I'm really going to talk about, let's say, different context with respect to the one that we just heard. Actually, I'm talking about one of the projects that we are pushing in our labs that starts from, let's say, the perspective of the average machine learning scientist nowadays, and tries to, say, expand his points of view in a direction that you will see in a moment. That's the name of the project that we are talking about, the project that it's in the context of FAIR. And I've been skipping many details and just, I just left a few keywords just to try to, to keep the attention on them. In this project, it's called, Constru. You see, it's a collectionless-based neurosymbolic theory for learning and reasoning. So you see the keyword collectionless, and I can augment that keyword with time and interactions that are two other keywords. The second of them, we heard it many times today, I would say, since this morning, in different contexts, okay? But it's very popular, as you know. In this project, we are framing learning in the context of a novel perspective that we call collectionless AI. It's a bit a provoking thing, considering that today everything is about collecting, billions or whatever data points and brute forcing everything. And I will talk about a unified framework in which the protagonists are not, big data collections, but time and interactions. And this actually opens to, novel perspective, in our opinion. So just to motivate this, today, the way we learn, the way we live in our world, it's all driven by several things, several important things, but one of them is certainly interactions. We interact with each other, we interact with, information sources of different type, and we actually undergo a progressive development. We don't learn everything in one shot. It takes time, and we go from learning something to learning more. We improve through all our life. We are not trained once and deployed. And the other keyword is time. Interactions, they happen over time. We learn over time. And this is not like a secondary aspect. It's actually something that has a key role in the way we learn. So there's two things. Times and interactions is what drives our current research, and what basically projects toward this presentation that we'll talk about a couple of keywords that I already introduced a little bit. The first one is collectionless AI. Every time you see that funny cat, I'm talking about collectionless AI. So I think it's also very useful just to wake up after lunch. And I will just try to show you, I've been skipping all the technical details. I will just go through 3 steps just to try to open perspectives and to reach the point I want to make. And then I will talk about Narnian. That's just, it's a framework in which you can simulate basically the ideas behind collectionless AI and many others. It's a pretty generic framework, so it's not really crafted only around collectionless AI. So let's see these 3 steps in order to reach the goal of collectionless AI. As a machine learning guy, I've been, let's say, I think also many of you, I've been educated, right, with the idea of working on a very specific thing. Either you work on classification, either you work with, object detection, whatever. If you just take a random conference and you take the keywords, topics that you find there, I think I copied them from I don't know, New Rips or others, I don't remember, but there are many, many keywords, right? There is a big list of keywords, actually. And each of us is one of those nice scientists there that is basically looking at its own keyword, at its own topic, focusing on that. And even if each of us is aware of the others, we really focus on our own, let's say, field, small field. And we all also carry this funny luggage that it's actually a big data set and a set of static benchmarks. So we all focus on, give me the data sets, give me the benchmark, and I will show you how I can improve by some points. This has become a bit too extreme, in my opinion, today. And this has been, I would say, it has become also a bit, I would say, even if it's still mainstream, it's not really what we are experiencing in terms of the way we approach modern technologies. If you think about, large something models, we all use them. I think, I've been using, I don't know, ChatGPT or others. I didn't benchmark them. I tried them. I said, okay, well, it seems to work. It's okay. I can go ahead with this. So it's not a matter of benchmarks. But that's basically the setting in which I'm working today, and I think many of you are working today. So something we should remember, it's trivial, but we forget, is that we are actually looking at the same thing. We are just looking from a different perspective. So if you are a person working on deep learning, you look in your, to your tile. But if you work on large language models, you look to your tile. But all these tiles are just basically facets of the same hypercube. We are actually looking at the same thing, but we don't move. We stay in our perspective. So the first step that I anticipate is just to try to relax the boundaries. So that it's not really a hypercube, it's a sphere, right? So there are not these edges dividing each of these keywords. So let's accept the fact that it's really an open thing. Let's try to move a little bit. The second step is embrace time. So time is not really considered that much in today's machine learning. I mean, there are time series and many important things, but it's still one of those keywords, not really the main driving signal of all the machine learning developments today. Even if it's crucial, we can revisit all the keywords by considering the fact that time has a role in the process. And this actually switches from, basically you see the laggages are not there anymore, the big data sets, but actually we have to think about a perspective in which we learn over time. And of course we learn in a lifelong manner, so I mean we keep learning every time, we never stop. And we learn it online. I mean, it's not a matter of just recollecting data sets and brute forcing them again. It's really learning as long as information hits our eyes, our ears, whatever, the perception, let's say, field. So the third step is just promote interactions. So let's think about this sphere as a big environment in which humans or artificial agents are living, and we've been, listening to interactions between AI and humans. But that's the point, right? I mean, we are living in the same environment. We have to interact. Different artificial agents should interact. And learning is actually the outcome of all this process, of this picture here, interactions, learning online, and there is a progressive development in this process. I mean, the qualities and the skills of each agent are not because of a data set. It's because of the interactions, the kind of, let's say, curriculum that it experienced over its life because of talking to other agents or to other people. That's the setting where we basically frame our ideas. So to just, in a nutshell, in today's AI is the top part of this picture. So we have, the different keywords, data sets, and static benchmarks. If you switch to collectionless AI, so see the cat again, that's where you basically move to this open context in which you can study machine learning technologies in this more open setting in which time plays a role. And Narnian is basically the counterpart of the static benchmarks. It's a framework, it's a dynamic world, a platform where you can study progressively developed agents. So just a small, quotation from something we wrote together with Marco Gori on collectionless AI. I'm just reading the red and blue parts. I mean, today we have a problem actually with machine learning that's, because of data centralization, privacy. The problem is there. Energy efficiency, limited customizability, and control. That's a fact, in my opinion. However, actually what we should look at is agents that are progressively developed over time by line learning, learning from lifelong streams, interacting with environments. I mean, all the keywords that I presented earlier. This is basically the main notion of collectionless AI. It's not a matter of data sets. It's a matter of continuously learning online. Of course, this brings several, possible solutions to the problems I mentioned, because we switch from let's say, cloud computing to something that can run on edge devices, small devices that we can control. I mean, I would prefer to have my agent, running on, let's say, on my phone without going to the internet at all, maybe, and just showing the reality that I want, so I can control it. I know what I've been showing to my agent, instead of, throwing everything in the web, in the cloud, and, letting somebody else play with my data. Of course, this opens to many challenges that are, just briefly mention them, that are how to redesign learning algorithms. We are doing a lot in this sense. I mean, you have to reconsider the notion of spatio-temporal locality. You want models that can operate locally in time and in space. We have to rethink neural architectures because we want them to memorize and not to forget. And of course, there is also the role of, system 1, system 2, or more generally of having access to some more structured knowledge bases to which you can interact and that are helpful also in terms of memorization. So these are the 3 challenges we are facing in the context of collectionless AI. We're working in all 3 fields, in all these 3 directions, let's say. And that's actually the second part of this presentation. So toward building collectionless AI agents, we developed Narnian. That's a platform, as I said. It's not necessarily related to collectionless AI. It's a sandbox in which you can grow agents. So it's a sandbox in which you can throw your agents to interact with others or with other humans, processing data coming from streams. So you have to process it and discard it and just go ahead. You don't have the privilege of storing all your data. And in this sandbox, there might be many agents. Some of them might be better than others. So there is a sort of social process happening. Again, we go back to many keywords we heard this morning. This is actually trying to allow machine learning agents to grow over time, not only because of their own exploration of the world, but also because of what other agents told them. At the end of the day, this progressive development of agents can lead to technologies that can be possibly transferred to the real world. So it's no more give me your training set and I will brute force it, but just let's try to progressively develop our agents. It could be really a social process, the one of allowing everybody to play in this platform, to enter the platform asynchronously with their own agents and see what happens by letting them interact. About the structure of these agents in the Narnian platform, they are agents that are able, of course, to learn, to generate, and to describe. And they process streams of data, visual data, audio data, whatever. They are composed of 2 main parts: a behavior that tells, how does the agent handle interaction with others, how does the agent behave, and the model. Well, it's not a great name, but it's how the agent handle the learning process. How does the agent takes decision, considering the data that it processes. The behavior in its most, let's say, simpler instance can be thought as a finite state machine. So in which you say, how there are a set of actions that you want your agent to expose. And this tells how the agent interacts with others, how the agent interacts in the world. And it could be, complicated enough to cover many nice settings. It can be made by the compositions of other automata. While about the model itself, the neural, let's say it could be a neural network or other things. We are using neural networks, but still it must be a model able to generate data. Take your, the large language model that you like, that's a generative model, but then it must also be able to interpret what it generates. So to be, let's say, self-aware of what it is going on. So these 2 parts, generative skills and interpretation skills, are the key blocks that actually you think Narnian agents should have. And just to conclude, we developed this interface to the Narnian world, in which you can just, it's a web interface. You can see the behavior of the agent, so you see the state machine with bluish and greenish blocks. And of course, the neural model, you don't see it. We are using state space models with what we call Hamiltonian learning. And then down to the bottom of the picture, you see the streams. It could be vision, language, and many, many other things. And there are different agents. At the top, you can switch from one to the other. And finally, types of data can be, vision, as I said, language, or just also, scalar signals. The last thing I want to say about this is that whenever you start really learning online, without storing data, without having the privilege of going backward in time, as you do with backpropagation through time, things are way more complicated than you expect. But that's what happens in reality. So even, dealing with scalar signals becomes way more complicated than one might expect. But that's Narnian. That's the framework in which we can experience agent. hoping to reach this perspective of collectionless AI that I presented. Okay, yeah, just something about our team. It's a team of people coming from different institutions. Yeah, we'll go quick on this. I mean, if you want to know more, there is a website where you can get details. And last mention, I mean, you know, we are organizing in a couple of weeks, actually, in Siena, a spring school on this topic. So, I mean, if you're interested, please join in, together with other colleagues from Pisa. So just to tell you know how much we care about this topic. Okay, so that's it. Thank you very much.
Thank you very much, Stefano. I think there will be, I hope, taking this pace, there should be time to somehow to have some conversation and get some questions after the lineup. So it's now the floor to Professor Paolo Nesi, University of Florence. Let us switch the slides. Please.
Thanks a lot for the microphone. So I am presenting here the status and what we have done in this take-up project that is called the Collaborative Explainable Neurosymbolic AI for Decision Support System for Decision Support Assistant. And so the main aim was exploring AI for supporting a new generation of decision support system that is exploiting the symbolic and the neural network models connected together with the idea of implementing new algorithms and models and also a specific new generation decision support system theory, and also to implement a specific prototype in a number of target domains. The objectives, and I am not reading all of them, but is to work mainly on the area of reinforced learning, to integrate aspect of explainable AI, taking into account the seasonality, mainly the temporal aspect in the explainable AI, to be capable to extract from the explainability, from the explainable AI, exploiting the explainable AI to extract a new knowledge and to take into account of this new knowledge in the decision support system, so to improve the experience and the capability of these, that's called agents for taking decision, and to explore also the interaction from human and this kind of new generation decision support system, to analyze how the human can influence or can interact with AI to improve the actual decision, and to actually develop instruments for specific scenarios. And so to arrive at make a validation of this new generation DSS in critical infrastructure, mainly for mobility and transport, environmental aspect, medicine and security, and complex manufacturing. So the project and the activity is focused on these four main domains. One is mobility and transport. It will be much better clarified later on with a specific example. For medicine, with Professor Frasconi. With complex manufacturing, with myself and my team, with the DISIT Lab as the mobility and transport. And regarding security and computer vision, with the MIC, Multimedia Integration and Communication Center in Florence. This is the team member. And for mobility and transport, we had published some recent work, mainly on explainable AI for time series, analyzing time series with a different explainable AI solution. And the other is a new activity not yet published regarding the neurosymbolic optimization for mobility infrastructure with a deep reinforcement learning graph neural network. The other activity in progress are the symbolic part with a new version of the ontology that we use, and also the integration with the large language model with the DSS. So regarding the first topic for comparing technique for explainable AI with a temporal analysis, we consider a number of representative time series with a seasonality or without seasonality, with outlier or without, and we compared Shapley and integrated gradient and Lime techniques with the idea of identifying specific new methodology for actually assess them, but also to provide a graphic representation to the decision maker regarding this. So I am skipping the mathematical definition. So for time series with the seasonality, you can see here the three different impact, three different representation, that for sharp on left, integrated gradient in the middle, and Lime on the right side. They are, so Lime results to be more sensitive on the variation, and the integrated gradient seems to be the best solution, the best approach to obtain a gradual and very good representative of the impact of the time series. So you can see here 1 week of traffic flow, for instance, behavior, in which you have the last part of this week represent the Saturday and Sunday. So regarding the time series without short-term seasonality, as you can see on the right side, Lime is very sensitive, and so pass drastically to negative influence to positive influence. So negative influence is green and positive influence is red. And so integrated gradient sharp seems to be better ranked. Finally, with time series with outliers, you see on the left side the sharp that is very too much sensitive, so is completely saturated the representation, and also the Lime is quite quite sensitive to the changes. At the final condition, we decided to adopt the Lime because the integrated gradient, because it's the most gradual and the most effective representation for the explainable, to extract information from the deep learning. It was LSTM, the approach that we analyzed with this explainable AI. So the second topic has been on neurosymbolic representation for the optimization of mobility. And the main aim is to give it a hand of the system to provide the suggestion about the complete traffic infrastructure restructuring. So to ask the system, okay, this is an area in which we have problems, please give us, as we can completely redesign the viability of an area. So you have from one side a graph, a neural network that has to be trained to actually produce changes in the network at the symbolic level, and a reinforced learning approach to identify the best solution according to some KPIs. So with this approach, we have compared the solution with the human activity, and also with the stochastic relaxation optimization approach, which is the actual state-of-the-art solution on that. So it's similar to what we have seen before. So one side you have the human that can create some scenarios, can make changes, estimate the KPI, make comparison, and with the trial and error can can decide which is the best solution to be put in place. On the other side, there are optimization process, including a neurosymbolic one that I am going to present you later on, that produce possible solutions and propose to the expert the possible solution to solve and to reduce the traffic. So to reduce the traffic, or to reduce the emission, or to reduce the fuel consumption in the area. So this is an example. From left side, you see the actual status of traffic, and this is an example of results. Left side, you see the actual status with the graph. The graph contains not only the single roads, but also how the cars can take rights or turn left on all the constraints that you can imagine, velocity and size and number of lanes. So it's a complex symbolic representation. From the right side, you see a possible changes. If you go in the upper part, you see some black segments, some segment marked in black that are the suggestion proposed by the GNN. So the system with the deeper GNN for reinforced learning has closed the loop with a symbolic discriminators that avoid to propose some symbolic changes that are not conformant with the rules for traffic, like putting all roads arriving in the same nodes in the same junction without having the possibilities to get out, or other things like that. And you need also to produce some results. You need simulators. That is the simulation for that can be used to actually recompute the KPI on a different condition in which the reinforced learning and the GNN is going to bring your system in a new state. So there is an evolving condition, the risk that the system is going to produce too much changes in the symbolic domain from this approach, and so there are a number of parameter constraints that limit also the number of evolution that you can accept to have from this decision support system. So this has been enforced also in a graphic representation tool to have a validation with the users. The results that we have obtained, results that the actual neurosymbolic optimization outperform stochastic relaxation, and in most cases also outperform what can be done by the humans, and obtain increment of performance that goes from 10% to 25%. So very, very interesting. Another activity that we performed, I don't know which time we are, is on physical informed neural network that is going to put together a neural network solver for partially differential equation, putting the physical model in the loss of the solver. So the idea for usage of the physics informed neural network for solving PDA is mainly related to the possibilities to reduce the cost for solving and executing the solution, and also to find a way to have a unique solver that can produce results from the PDA every time that you change with a unique execution. You can also change the element that you that you are going to put in the autoclave. You see in the picture an autoclave. An autoclave is an oven with pressure and flows. It is used for cooking material, composite material like the parts of the wheel of aircraft or the parts of F1, so high-speed cars or very extreme cars. So usually these kind of solutions are computed with the finite elements, with the open form simulation, and the critical issues is not on the steady condition, the stationary condition, but on the transitory. Okay, so you see here the transitory, so the transient phase. And you see the results in the first column on the left side, the results of open form, in the middle, the results of our physical informant neural network. And on the right side, there is the error that you have seen in the transient. So you have seen the effective reduction of the error that is quite low. The idea, so probably this cannot be read, but the idea is to have one unique solver that can be used by who is going to make this kind of production. So changing the pieces that you are going to put in the autoclave, and in few minutes to have the prediction of how much time you need to cook the material inside, to be sure that the material will be polymerized in the right manner. So if you would like to know more, you can so it's quite complex, but this paper has been in the preprint in 2 months top paper downloaded for 2 months before publishing, and now has been published since a few days. There are some other activity that the group, Florence Group, has produced, on which I am not really skilled to go in deep, and I am really sorry, but I am showing you the slide quite quickly, because they have been in a field that, on which I am not skilled enough to go in deep. And this is the slides for Media Integration and Communication Center that work on security and computer vision. So they are they work mainly on neuromorphic vision. I think they are special camera. This is what I understood. They are special camera that are capable to provide the signal in the single elements in which there is a change. I don't know actually more than this. And so they are using this to create a new representation, a new system to actually detect the variation and the security aspect and in the domain. Another work was done by the AI lab on medicine and the interaction with the medicine, with the application of large language model in the medicine. One work was in a system for identify anomalies in electrocardiograms, and this is quite well represented here in these pictures. Another one was in the algorithm for solving problem for the learning set. And another one was a large-scale study to investigate the replacement of the traditional stereological approach for cell counting. This is from...
Okay.
Sorry. Thanks a lot. In the slides there are references, so I hope that the slide will be shared.
Will be shared on the slides.
And next step are, we are trying to close the loop and to exploit what we have seen in something that can increase the knowledge that we have for the new round of this kind of decision super systems.
Thank you very much, Paolo. We now have Professor Francesca Chiaromonte and Andrea Vandin from Scuola Sant'Anna. In the meantime, also Professor Diego Garlaschelli joined us from Scuola IMT Lucca, so we are complete.
Stringiamo un pochino, okay.
Please. So, if we say around 15 minutes each, we still have time for a little conversation at the end.
Le slide. Sì, vai, accendi.
No, va bene. È uscito. So hi everyone, thank you very much for making us part of the FAIR family. It is very nice to be here with all the colleagues. In this brief talk, we will tell you about some recent developments in the Smart Construct project, statistical methods and reduction techniques for learning from complex structured data. This project is hosted within the Lembeds family, which is a department of excellence funded twice by the Ministry of Research in Italy. It is led by Francesca, who is here. We have, similarly to the previous slot today, we have a wide range of profiles ranging from economics, management, law. We also, as you know, recently hired another computer scientist, Paolo Ferragina, awardee of the ACM Paris Kanellakis Prize. We develop methodology in data science, statistical learning, machine learning, and AI, and we target applications from the social sciences. We also go beyond that. We also do teaching with this idea. And our efforts led to the establishment of a new area in data science for our honor students. So Sant'Anna releases a new diploma in data science starting from last year. Smart Construct is a grant funded by a cascade call of FAIR. It is a 15-month project started about last summer. With Francesca and I as PI, we involve, the core faculty involves a number of profiles, economics, law, statistics, and computer science. We have also junior researchers like Saverio from the Institute of Management, Irina from the Law and Political Sciences Institute, and Simone in the economics department. So Smart Construct has been built around 5 dimensions, studying issues connected to functional data analysis, data and model reduction, process-oriented data science involving human-centric processes, statistical and machine learning mediated design and optimization of simulations, and networks and discovery of causal structures. This is a not complete list of results obtained so far. Some of them are work in progress, some of them are already out. I'm not going to read all the titles. What I want to say is that these 5 dimensions often have points in contact, so several of our results touch more than one dimension. If you want to know more about some specific topics, we have Irina Carnà here for the law part. We have Saverio Barabuffi here for the management part. Simone and Riccardo Tonini and Porcetta related to more time series analysis and machine learning applied. So in this talk, we would like to briefly overview some selected projects, very briefly, on covering some of these dimensions. Don't worry, it is a few slides per project, so we're going to be fast. So the first one involves Riccardo, who is a PhD student in the national program in AI, where we are involved, Francesca, myself, and Professor Lillo from Scuola Normale Superiore. Essentially, here we want to use deep learning to generate synthetic data. Why? Because, as you know, using sensitive data has a lot of problems, a lot of constraints. Can we create anonymized copies? Can we create a doppelganger of our data which avoid privacy issues while preserving the structure of the data? And we will hint at an application to financial networks. So research on statistical learning, machine learning, and AI methods run on, as an example, economic, financial, big data can help in fraud prevention. Can I study a history of payments to discover money laundering or even more severe problems, or customize payment offers or similar? The problem is that this financial data is very seldomly available, publicly available, actually never. Even if you manage to do agreement with people owning this data, then there are problems in this data getting out from your partner. So either you visit them locally or you don't do research. So this may prevent to fully unleash the potential of big data. Possible solution that we are investigating is making synthetic copies of such data. We discover patterns within the data. We create a copy of the data, preserving these patterns, these relations, these correlations, but losing information that may give problems. A financial network is, just think of it as a sequence of payments where nodes are people who pay or people who get money. You have a direction because you want to know who pays whom, and you have weights in the edges because you want to know how much each payment is about. We also want to have attributes on the nodes to know what is about a node making a payment, what is about a node receiving a payment. Like the code, in Italy, the code Ateco, which tells you what is the field, the domain of a company. In this research line on which we are working on ingredients like graph theory, synthetic data, graph neural networks, network reconstruction, and link prediction. So the idea is that of given a directed, weighted graph, where attributed graph, where we have information on nodes, we have information on edges, we have information on the direction of edges. We want to build a deep learning model which learns a representation of the network in a different space, an embedding. We make a different representation of this data. As you can see, from this node embedding, we can fully reconstruct the original graph, but we get actually a synthetic node embedding from which we generate a synthetic graph. So at the moment, we are working at the link prediction task, which is not so well developed for this type of networks we're focusing on, and we have a draft under evaluation at an important conference. We tested our approach on 40 real-world networks. We tested against state-of-the-art techniques, and we outperformed them in a given number of performance measures. The second project we would like to tell you about regards a different type of process of data science, which focuses on process. So I don't do regressions, I don't do classification, I don't do clustering. I try to discover the process that generates the data. I want to study the process underlying the data. this is a collaboration, multidisciplinary collaboration involving Giovanni Comandé and Vittoria Caponecchia, who are experts in the law domain. So if you think about process-oriented data science, typically you have a reference process in mind. Here is the process of this measure. The process is, I don't want bikes in this park. Often, these systems leave traces. They collect logs of actual executions. We want to use these logs to discover the real process. So as you can see here, many bikes actually enter the park, so the actual process is not the same as the reference one. And about 20 years ago, people had this idea of connecting the so-called process science, people studying processes, with data science, obtaining what they call process mining. It is highly supported by industry. You find process mining plugins in Power BI and in many other established platforms. In Sant'Anna, we studied it to discover the process of patients, Tuscan patients, and also how legal courts work. In particular, I would like to tell you briefly about this simple case study. So this is a portal handled by the Ministry of Justice. Essentially, for each legal case, you find the different phases in which it evolved and the time. This is available data. We see this as an execution of a process, the process of how a legal court handles certain cases. For some reason, we focused on simple divorces, just by chance. So, for example, what does it mean to focus on the process? If you just focus on numbers, you can see that in 2019, things got much better. So we took divorces in a given time period in two Italian legal courts. In one Italian legal court. I cannot tell you which one. If we compare the length, 2019 is much better than 2013. The median length in days is 93 days rather than 181. Why is that? Well, we noticed by doing very, very simple studies that part of this process had these red edges, which means in this graphical representation, very time-consuming tasks. And this was very frequent. If you zoom, it is about changing the judge that has to do with that legal case. We can see that more than once per legal case you change the judge, and each change was taking really a lot of time. So in 2019 things got much better. Why? Because this part of the process has been anticipated, and it happens much less frequently. It is an activity that takes out time. So what they did, they found a better way to allocate the right judge from the very beginning. So this is a process-oriented explanation to this data. This is just the ABC of this process-oriented data science. You want to be able to compare different processes from a quantitative point of view. Briefly, I can tell you about some recent results on anomaly detection, starting from a collaboration with a company in Tuscany, in Lucca. We developed a simple but accurate methodology for anomaly detection. So the simple because in this case we don't use deep learning or so. We use simple, well, let's say simple statistics like smoothing, variable inflation factor, particular notions of distances, but not to a sort of Euclidean distance normalized by standard deviation, the Mahalanobis distance, and techniques from extreme value theory, and simple regression techniques to identify which variables cause the anomaly. We based it on a recent literature review from a top venue in computer science, VLDB, which review plenty of anomaly detection techniques. We compared with the anomaly detection techniques similar to our. We compared on a number of online benchmarks used for anomaly detection, and we are on the top left of this plot. We are faster, we are more accurate for this type of task we are considering. This work is under review. We hope to get some positive results soon, outcomes soon. And maybe, Francesca, you want to add some?
Where are we with time?
We have 1 minute.
Okay, so just very, very quickly, because these talks have become too long otherwise. Another line of research that we're engaged in has to do with functional data. Functional data, come va avanti? Okay, so functional data is an area of statistics where data are not points or vectors or matrices or Euclidean type objects. They are functions, continuous functions on continuous domains. It's got lots of applications in lots of different fields. Recently, with several collaborators, we've been investigating the possibility of finding motifs in functional data. This is not a supervised operation, it's a discovery thing. It's actually pursued through a local clustering approaches. We look for patterns in these curves that occur repeatedly, either within a single curve or across a set of curves. We have developed several different approaches to this. Some extend on k-means type algorithms, which are probabilistic and which are local, so we allow curves to shift against each other, and then we extend seeds of similarities that we find. In a completely different approach, we cut the curves in very tiny portions, overlapping portions also, and then we use hierarchical agglomerations to find recurring parts. This work's been going on for a while, including some recent developments where we have extended the second, the hierarchical agglomeration-based motif discovery algorithm. And this is just a slide to give you a sense that this type of motif discovery in curves, in functional data, can actually have huge applications. Oh, there are some colors that don't come through. Okay, it doesn't matter.
It is the
it's totally fine. This stuff can be applied in many different domains. Sometimes the continuous domain on which this functional data is represented is time. So longitudinal data can be treated as functional data. Sometimes this continuous domain can be also two-dimensional space. Sometimes this continuous domain is a genome, okay, along which you're seeking certain regularities. So there are huge applications in climate sciences, in economics, in omics, in biomedical sciences. We have applied this also in epidemiology. Okay, I'll stop here because this way we avoid overload. Thank you.
Thank you.
Thank you very much, Francesca and Andrea. We have now Professor Stefania Bellavia from University of Florence, because Florence has two projects and we will listen from Stefania about the other one.
Good afternoon in the meantime, and thank you for this space for presenting our project. Sì, va bene, devi andare alla seconda slide. Vai alla seconda slide.
Non stavo trovando le slide.
Okay, thank you. I'm Stefania Bellavia from the University of Florence. And yes, this is the second project of the University of Florence. The principal investigator is Duccio Fanelli. And the project is a project about mathematical and physical approaches in machine learning. And this is the staff of the project. And so you can see that we are in 3 different departments, and we are mathematician and physicist. And we have recruited 3 postdocs one for each department, Stefano Gaiani, Krunal Raval, and Greta Malaspina, and they are all here. And they are involved in 3 different streams of research, and there are the stream that I'm trying to highlight here. So I'm going to start with the use of dynamical systems for classification and their relationship with neural network. Then I will move on shape learning models. And in the last part, I will discuss my research area, that is randomized optimization for training. So in the first 2 parts, we are developing models, and in the last one, we are training models. And if I have time, I also give some brief description of what we are doing in data imputation. So starting with dynamical system, this is a research that is carried out by Stefano Gaiani, Filippo Caruso, and Duccio Fanelli from the Department of Physics. And what they are doing is to use bio-inspired dynamical system for image classification. So they started for a model that is quite used, that is this one, that is quite used in neuroscience. And they use this model, this dynamical system, for classifying images. So I'm trying to explain what they do, as it's not my activity and it's not easy, but I think that I got the point. And so they have this model. There is a deterministic part and this part here that take into account random noise. And xi is the activity of neuron I. And what is interesting is that they have a network, and each neuron is related to a pixel of the images that they have to classify. And then they have here they have in the model this matrix, that is the matrix A, that takes into account the relationship between neurons, and the function f here is the activation function, that is the sigmoid in this model. And so what they do, they train this model and they learn the matrix A, so that at the end, when they have done the training phase, this dynamical system has distinct stochastic attractors, one for each class in which we have to classify images. And if the process works well, each item is attracted by the correct attractor, and so it's classified in the right class. And what is interesting is that there is a relationship. They can prove that this process gave rise to a neural network. So at the end, they build in an adaptive way the neural network that they use to classify the images. And this is something that we find in our project more than once. That is the effort that we do to provide adaptive methods or model so that to reduce the tuning that is generally needed in this framework. So this is our effort, and to use mathematics and physics to reach this aim. Then, moving from this model, they are trying to use more sophisticated models. This is the model of a random walk in a network. And again, they have this network that is induced by the images, but they modify the network, so have to have what they call absorbing traps that again have to attract the images in the right class at the end. And then they, here the meaning of xi is different, as it is the average density of walkers at node I. And then they are also considering quantum variant that you can find here, quantum variant of these dynamical systems, so that to test the possible advantages coming from the quantum nature of transport. And once that I arrive to the quantum model, I can move to something that is more familiar to me, as this is quite far from my knowledge. And then the second stream of research is related to surface reconstruction. And this is research that is carried out at the math department by Carlotta Giannelli and Kruna Raval. And what they have a cloud of 3D points that you can think that, for example, comes from medical imaging. And then they want to rebuild build the surface that is provided by these points. But they want to do this using spline, so that at the end what they have is an analytic expression of the surface, so you can compute derivatives and you can work with this analytic expression. But for doing so, you need to go from this cloud of points to a planar I can say the space of parameters that is planar is 2D. So for doing this transformation, you need a map that goes from here to here, and then starting from this one, you can build the surface using a spline. And but the way you map this point in the 2D space plays an important role. As here you can see we have two different maps and the final reconstruction is completely different. So it's important to have the good map from going to here from here. And what they want to do, and they also started to do in this paper, is to learn this map using a neural network. But in order to have a good map, it's important to have a so-called quasi-conformal map. That is a map that is able to control angular distortion. So what they are doing now is to use a neural network, but as in PIN, in the loss are included physical information on the model. Here we are including, they are included mathematical information on the problem, and they are included the angle information, so that at the end they learn a map that is a quasi-conformal mapping. So they are able to preserve this important property that is important to have a good reconstruction. And moving to my research area, that is stochastic and randomized optimization for neural network training. This is research that I carry out at the Department of Industrial Engineering, that is my department, with Greta Malaspina and Benedetta Morini. And the aim, the general aim of this activity is to provide methods that are adaptive on one side, and on the other side that are able to use also second-order information on the problem in order to handle non-convex loss function. And we would like to do this, reducing the overall computational cost with respect to standard or deterministic methods, and to try to keep the same accuracy, at least in high probability, as we are moving from deterministic to stochastic optimization. Some of the strategies that we use, and this is not something related only to our research, it's a general trend of the numerical optimization community. What we are doing is trying to use some important strategies that we have in the deterministic setting to the stochastic setting. So this is what we are trying to do, and it's not always easy, as the stochastic setting is really more difficult. And anyway, when we use a method for training a model, we can think to the stochastic gradient or Adam or everything. In any case, hidden in the method, there is a model that is a random model if we are using a stochastic method, and the random is here, as we generally use a stochastic estimator of the gradient. And so we have this model, and if we don't have this second order part in the model. We have a first order model that is the model that is behind any first order method that we use when we train a network with Adam, Ada grad, stochastic gradient, what is it? But in some situation we need, or it would be useful to use some second order information, as it's possible to exploit information about the curvature of the function and to have something that is able to handle ill-conditioned problems. But it's not easy, as it's in the deterministic setting it's expensive, and if we put this in the training of a neural network, it becomes something that is really too expensive. And it's also difficult to implement. So what we can do, there are two different possibilities. One that we have already explored, that is to use something very easy to approximate the second order, that is a multiple of the identity matrix, and at the end we end up with something that is like the stochastic gradient, where we have here in this mu k some second order information that comes that we are able to compute using only first order information. Or we can move to the randomized linear algebra. And the randomized linear algebra is a stream of research that is exploding now, and as it's something that is important to handle problem where we have large and dense matrices and we want to reduce and compress information. And at the end, we have something that gives rise to accurate solution with high probability. And for example, we can, choosing in a proper way row and lines and columns of these two matrices, we can compute two smallest matrices, and the product of these two matrices is a good approximation of, in high probability, of the product of A times B. So we have compressed information using some tools that comes from randomization. And we have, now sorry, I forgot the time, so I'm lost. Okay, so I'm going to the end. And so we have already worked on this area using random sparsification of matrices or random row compression. So what we do, we have a second order method, and we handle the linear algebra, that is the difficult part of these approaches, with this randomized linear algebra. And what we are doing now is that we are projecting our problem in a subspace. So we are doing a model reduction in a subspace and of small dimension, and we are looking for the direction that we use each time to update the iterate in this small subspace. And this subspace is built using a so-called sketching matrix. That is a matrix that with high probability preserves norms. So obviously the subspace has to be chosen properly, otherwise you cannot gain anything. And with this approach we have a relevant gain in computational cost when we solve nonlinear systems that are underdetermined. And we are using we are planning to use these tools also for solving the so-called matrix completion problem. That is the problem that we have when we have a data set, and so we have a matrix, and there are some entries that are missing for several reasons. And we would like to recover the missing data. This is something that is possible if we have data that are redundant, otherwise it's not possible. And again, we have a linear algebra core that is the most expensive part, and we are planning to use randomized linear algebra. And so now I understand that my time has finished, but I'm at the end, so I thank you for your attention, and these are all the main topics of our project. Thank you.
Thank you very much. Now, after Stefania Bellavia, we have the final contribution by Professor Diego Garraschelli from Scuola IMT. Just a second to recover slides from this device. La facciamo? Questo è l'Accademia.
Okay, good afternoon. While they are setting up the slides for me, so let me introduce myself first. I'm Diego Garraschelli, professor of theoretical physics at the IMT School for Advanced Studies, Lucca. And I'm here representing one of the Cascade projects for FAIR. The project is called ReconNet. It's about a reconstruction and resilience of economic and financial networks, so it connects to something that was mentioned, luckily, just before by Andrea Vandin. And by the way, we're also interested in synthetic data generation, and I'll try to give a sense of it. Okay, so let's see. Okay, so
is the
yes.
presenter working?
Yes, now I can also see it from here. Yeah, so thanks a lot. Okay, so the scientific team is, the official team put on the project is just these 3 people, but of course there is an entire research group, which is the networks unit we have at IMT Lucca, which I'm leading there. And so I want to give you a narrative about also a larger effort around this particular project. So we spend a lot of effort in problems of network reconstruction. And one of the key motivations is precisely what Andrea was also mentioning, the data about financial networks, so network between banks, for instance, or supply networks between firms are highly confidential. And typically you do have information, but in the form of aggregate data. It could be aggregate as in the sense that I'm trying to convey with this slide here, so that for every node, you do know what is the total flow coming in and going out. So it's like you have the total weight of all links that income that node, and also separately the total weight of all the links that go out. And then you would like to, reconstruct the network that corresponds to these flows. Of course, there are multiple solutions. It's an ill-defined problem. So we adopt a probabilistic approach, which is the celebrated maximum entropy principle. So basically, we construct the the probability over all possible weighted networks in this case that are such that the constraints that we do see from the data are replicated as expected values. But for the rest, this probability distribution is entirely random, so that we minimize our bias. So we are maximally non-committal to missing information, which is the way that Jaynes put it very clearly in the 60s. So we take an information theoretic approach, and we have to couple this with the data, of course, that we have. But this is not the flavor I want to talk about today. So we have done a lot on this. There is also this reviews on Nature Physics. But today I'm going to talk about a different flavor of network reconstruction, which comes to the main topic of the talk, which is now when you have a different type of aggregation. So now you do see the entire network, so all the links, but not between the original nodes, between aggregates of nodes. So now you can imagine that there is a coarse graining process behind. You know which nodes perhaps are in which blocks, and you do see the links between the blocks, but you don't see the links between the microscopic nodes. So it's a completely different setting, and doing maximum entropy here is not the best solution, because what you have here is a non-additive function of the underlying degrees of freedom, so of the underlying links. So we have to solve this via a different principle, which is the principle of consistency of the probability that generates the microscopic graphs with the probability that generates the coarse-grained graphs. And so we are in the quest of this consistency, and we discover something quite nice, like there are only certain network models, only certain random graph models that are consistent upon aggregation, and also only certain node embedding algorithms that are consistent upon aggregation. So this is the main gist of it. So basically, well, also here this problem is connected not to maximum entropy in physics, so not to statistical physics in its construction, but in the renormalization aspect of statistical physics. So there's another review coming in. So let me try to explain the problem from the point of view of node embeddings, because this links better to the AI community, I guess. So imagine you have a network so that you could see. Imagine you can see the microscopic version of your network, and then you run some node embedding algorithm that basically assigns each node in the original network, a vector in some space, in some embedding space. This in general is a lossy process, in the sense that given the vectors that are output of these algorithms, you may not be able to reconstruct entirely the microscopic network. But when this is the case, it's very useful because, first of all, it's a method that can preserve privacy. So now if you give someone the embedding vectors, you are not giving the sensitive information which is encoded in the original network. But also because you can do generative basically AI with this. So once you have the vectors, there is a probability distribution that outputs graphs that are statistically equivalent to the original graph. Okay? So imagine you are doing this, and the scale is fixed. So the nodes are those points, and the vectors will be as many as the nodes. Now imagine someone comes and coarse-grains the original data, which brings us to the case where you can imagine you do not see the original network actually, you see only a coarse-grained version of it, which means that you know which blocks are connected if there was at least one connection between the underlying nodes. And now the question is, it's a purely theoretical question at this stage. Imagine you use the same node embedding algorithm that you would use for the microscopic network. Now you get different node vectors. You have fewer nodes, you have fewer vectors. The question is, how are the two embeddings related to one another? We discovered that there is no easy answer in the literature about this. In doing so, we discovered also that the fact that you embed nodes in a vector space, it's not fully exploited mathematically, because the defining properties of vector spaces is the vector sum, a multiplication of a vector by a scalar, and it's not clear what happens if you take embedding vectors of nodes and you sum them together. What happens? What is the interpretation in terms of the network? And similarly, multiplication of a vector by a scalar. So we addressed these two problems in a sense at once, and we explored a way of enforcing that node aggregation, so combining two nodes into one block, corresponds to the operation of summing two vectors for the embedding vectors for the corresponding nodes. Okay, so then I just want to go very quick and show results, basically. So imagine you have this rule, so there is a microscopic network on the left, and then you do some partition of the nodes that then map your network to a coarse-grained one. You would like now to make this thing consistent if you have an entire ensemble of random graphs. So now imagine you have, on the microscopic nodes, you have a probability distribution, which is nothing but a random graph model in mathematics. And now you know that that one partition that coarse-grains your network to a reduced set of nodes will also induce now a new probability distribution over coarse-grained graphs. The question is, what do these two probability distributions have in common? Are they consistent in the sense that if I started with the original model and defined it already at the coarse-grained level, would I retrieve exactly the same probability for each possible graph configuration? So it turns out that the problem is non-trivial, and we found one solution in the case where the probabilities between nodes are, different pairs of nodes are independent, okay? So that knowing the probability of connection between pairs of nodes is the same as knowing the entire probability distribution, okay? So we identified this unique form, functional form of the probability of connection between pairs of nodes. And we noticed that this probability has the property that it depends. So this is the probability that node I and j are connected, okay? And this depends on parameters xi and xj that are additive, okay? In the sense that if you now coarse-grain two nodes into one, then this probability will induce a probability of connection between the agglomerate of two nodes and any other block, which will depend on the sum of these parameters inside the block. And now if you make these quantities vectors and this product a scalar product between vectors, then you have basically the rule for embedding so given node embeddings that are vectors, how you should combine them if you want to represent the operation of coarse-graining nodes, okay? So I'm just showing now results of applications, for instance, to the very simple network, the network of international trade between countries, and then we did the same for industries in the Netherlands. So here we took what in the economic literature is known to be a good predictor of the existence of trade, which is the GDP of countries. We also considered geographic distance between countries. And if you put these ingredients in the right place inside the functional form, which is the solution of the problem we had identified, then you realize that there is only one free parameter left, this delta. It's a parameter that tunes the overall density of links in your network. So you can make the network sparse or dense. So if you tune it in order to make the network as dense as the real one in expectation, then you see that you no longer have to fit this parameter as you start making agglomeration of nodes. So now you start coarse-graining your system, and once the parameter has been fitted, the density of links, the expected density of links across these horizontal levels of aggregation and other quantities, like the assortativity in the network, all the clustering coefficient, they remain very close. So the ones produced by the model and the empirical ones remain very close to each other, even if you're not refitting this parameter. So this has to do with these invariants I was mentioning before. So this particular probability is invariant upon aggregation, which also means statistically, you can fit the parameter at a convenient level of aggregation, in particular where you have the data. So if you have a coarse-grained version of the data, you can fit your parameters there, and then impute the probabilities between microscopic nodes that you do not see. Okay, or for which you do not see the network, but that's more important. And the same single parameter is able to replicate even locally properties like how the degree of nodes relates to the GDP in this case, how the average degree of the neighbor of every node relates to the GDP, and how the local clustering coefficient relates to the GDP. And the same without refitting, if you take the same value of the parameter but aggregate the network and redo the comparison between the model and the real network, you see that this consistency is preserved. So the last example I want to make is now, what if we do not treat the GDP as a parameter that we can have from the data, but we treat it as a latent vector that will be the output of a node embedding algorithm. So now we just take the network and we find the optimal embedding vectors given this probability rule for connection between pairs of nodes. And you see here, this is the comparison between what you would get, say, the degree from the model and the degree from the data, the average nearest neighbor degree from the model and from the data, again, the local clustering coefficient, and how these quantities scatter plot against one another, basically. including the degree distribution in the network. So basically there are colors here. One is for the real network. The other is for the model fitted at the same scale at which you have the network. And the other one is actually obtained by fitting the embedding vectors at the resolution level that is different from the one that you are then using for the comparison with the empirical data. So you first fit the vectors, then do the vector sum, and then you get predictions for the aggregate version of the network. And we did the same for our more, and this is a comparison which is interesting with another node embedding algorithm, which is called nonlinear PCA. We found out is the, say, state-of-the-art node embedding algorithm for problems of this type. But it doesn't have this invariance guarantee, and you see the mismatch now when you switch from one scale of description to the other. Okay, so this is basically it. Let me just show the same results, but now for a much bigger network. This is a network of industries in the Netherlands. So it's thousands of nodes. And again, we could find this very convenient consistency. By the way, the number of dimensions, so the dimension of the vectors is not pre-specified, so you can later on do model selection between different choices of the embedding vectors. And we found that very low dimensionality, like 1D or 2D, can already give results that are quite as accurate as going all the way to 16 dimensions or so. So this is it. I want to close it here so that we can have some minutes of discussion. Thanks for your attention.
So I really would like to thank all the contributors to this session. You've seen that you also, in this variety, you also notice that there is also some data science core of our community that emerged quite clearly in the talk by Diego and Francesca and Andrea. And Paolo Nesi as well. I think that we have time for a couple of questions, if there are questions from the audience. I have one for Giuseppe Riva, if you don't mind, which is, I would like to know what you think about the fact that if you think about the work of Kahneman and how he developed this theory of system one, system two, it's a lot of empirical work with experiments with human subjects that making decisions in very funny ways. And so I wonder, how can we somehow translate this body of knowledge in a situation where human participants are also intertwining with the AI participants, and what kind of role the different interfaces we may use would impact on this research?
I think that this is a critical issue, because one of the problems in the study about human interaction is that there are more models than real experiments. So I think that we need more practical research, especially related to the decision-making process. Well, from psychology, we have many different models about how to do this kind of interaction. However, I think that the biggest challenge is replicating the processes that we have between humans in human-AI interaction. We found, neuroscience found, that this kind of interbrain synchronization is a critical feature for creating a balance between different humans. This balance, this equilibrium is generated by the physical brain. And in this sense, we have to explore how to generate this kind of synchronization between humans and AI. We know that it's not just a problem of language. Language is not enough. So we have to explore other tools. It's a big research area, and I think that some of the research we have seen in the morning are putting some direction that we can follow.
Thank you. I see a raised hand by Francesca.
I wanted to make a small comment. I see a few students here. There was a reference to a paper showing how important it is to be in a classroom together, okay, to create this syncing mechanism. So come back to class. This was a side note. How symmetric are these mechanisms? Meaning, I was making a joke right now with Andrea. Imagine if what happens is that we converge to them instead of the other way around, right? Which could be quite a powerful and disconcerting.
This is quite interesting in the sense that interbrain synchronization create a convergence, but it happens that knowledge can create a divergence. So the challenge is generating a divergence that can be managed by the synchronization. So it is critical to induce a divergence that is not so high. We don't know the line, the line between friends and enemy. This is the biggest research topic now in neuroscience. Try to understand what makes the difference.
But are there special actors in this, let's call it game, it's not a game, but sort of core players that sort of drive these convergence again, or could?
Yes, it's the problem of leadership. We know that leadership makes the difference, and we know that leaders have a specific ability of creating interbrain synchronization. So a leader has the ability of generating shared attention with the followers that is able to increase the level of synchronization.
We have to prevent the AI leaders.
You can continue. No, but just a comment. I hope that this does not hold in an online classroom, because this for us is very important, of course. Just a pair of comments, if I can, just from the University of Siena. And I would like to understand, you talked about, of course, agent and your framework. And what's actually the relation between your framework and reinforcement learning? So
that's a good question. Actually, I think in our framework, basically, one of the components is the behavior of the agent, right? How it behaves. And today I've been showing just a finite state machine, basically. But that's the space where reinforcement learning algorithms usually play. I mean, you learn the policy to decide what actions to do in function of, what happens during the exploration. So considering our framework, reinforcement learning is what could be studied in what I was calling behavior part. So in replacement of a pre-designed finite state machine, you could have something that can be learned from data. So it's actually part of this vision, right? It's one of the possible instances. But actually, what I presented is more general than that, right? I mean, it's a more generic view. You have both generative models and reinforcement learning and classification. Everything stands inside of this vision. But yeah.
Okay, thank you. And just for the Scuola Sant'Anna, just one of the comment or just a question for you. You talked about an approach to anomaly detection, and you just told that it's a generic approach. Okay, in my experience, when you just discuss about anomaly, you have just to focus on the problem, because anomalies can change, of course, from one instrument or one appliance you are monitoring to another. So it's really generic, the approach, but in any case, you have to tune in some way just to understand.
Of course, I was overselling it.
Okay.
No. So, in fact, the whole idea started from a concrete case study from our industrial partner. They have a production line with 200-something sensors. But these techniques per se are general, and in validating the approach, we used 10 or 15 benchmarks online for anomaly detection taken from different domains. In all these cases, it has shown good results. But of course, one has to, and then you need to tune it. One tuning parameter we have is, for example, if you're interested or not in short anomalies. A short anomaly is like maybe some dust that touched a sensor. So maybe you want to tune that, and we use the smoothing for that. That's a good point.
Just another observation, and we close it.
Time series data, and the power of it is that it is so simple that retraining it is.
But another aspect that's normally the company are looking for this aspect is the explainability in any case.
Yes.
So they want just to really understand the anomaly from what is generated really.
The last part of our pipeline is essentially, we run a regression model, one of these models that naturally can tell you which features are important for so we label anomalies, and then we'll run a regression or a classification task on this synthetic data, and then you just know which features are important for the selection. If you use a random forest, it tells you which columns are important for saying 1 or 0. So we tell them, look, this anomaly is due to temperature going high, and then the process expert can explain.
Okay.
Yes.
Thank you.
Thank you very much.
We can continue later because it's late. Sorry.
Oh, nothing to add. I think we can really thanks again the speakers, Giuseppe Riva, Stefano Melacci, Paolo Nesi, Francesca Chiaromonte, Andrea Vandin, Stefania Bellavia, and Diego Garlaschelli. Thank you very much for enriching this. Now, just a change of stage, quick, and we proceed with the industrial partners session. O mi casca giù di qui?
No, non te casco. Ormai.
Non mi cascare.
Io vi saluto che ho il treno tra poco.
Grazie.
Che scappo via, grazie dell'invito.
Vengo a visitare.
Molto volentieri.
Molto interessante.
Grazie.
Sì, volentieri, sì, l'abbiamo filtrato sotto.
AI driven innovation, giusto?
Sì.
Ok. Quindi questa l'apriamo e l'altra erano qui. Ok. Ora sinceramente al volo non mi ricordo che ci fosse prima tra Deloitte, perfetto. Vai, anche senza farla apposta.
Okay, I'm sorry because it's very late, but no, non è mia. Okay. But I think that's it's better just to start as soon as possible with the last session. This session is a little different from the previous section because we have really companies here, so we have just experience from the industrial sector, service sector, and I think it's very interesting in a project as fair to have also this experience told to the researcher. I'm sorry that the room is not so really full, crowded now, But the experience of a company is interesting because in some way we can touch with our hand what are the results of our research, but also because we can understand what are the trends in terms of the use of the AI in the world today. We continuously knows that, and we just hear that the AI is fundamental, and in some way they describe the AI today as something that's very against the humanity, but we know that this is not the reality if you use the AI in a correct way. So I'm really happy to introduce the two speakers, or three speakers today, from the two companies that really have strong relation with this POC. One in this innovation grant. The first company is Intesa, represented by Paolo Baracco and Francesca Placenti. And the other company is Deloitte, represented by Rosa Pia Devanna as a speaker. What are the innovation grants? The innovation grants are really the fund that's fair, dedicated in some part for the company. The company, of course, co-funded this project. The idea is just to develop something, but internally to the company with the support in some way of the researcher in this POC one. So I hope that this interaction in some way will give some result, as I hope we will tell now. And I hope that will open also the possibility for some of these researchers that you heard in this day, just to have also the possibility to enter in the future as in this company that collaborate with us. Okay, I leave the floor to the first speaker, Intesa Sanpaolo. Yeah. And I don't know if start. Yes, okay, we start Francesca.
No, sorry, I'm Laura Castello.
Oh, sorry, Laura Castello.
Okay,
sorry, I'm sorry, very sorry. Laura Castello.
Name.
Yes.
Okay.
I don't know if also Francesca is here.
Exactly.
Yes, okay.
Exactly. So, hi everyone. So I'm Laura Castello, and together with Paolo Baracco, we are here, as already said, from Intesa Sanpaolo, and we work specific on compliance digital transformation. And we are here, I'm sorry,
yes.
The telecommand for the slide? No? Is lost.
Okay, it's there.
Okay. Thank you. So, okay. Perfect, thank you. So we are here to talk about human-centered AI framework for high-risk financial application. This is the aim, but also the challenge of the research project that we are conducing in partnership with colleagues of University of Pisa and the Scuola Normale Superiore. I remember also that Intesa Sanpaolo is a foundation member and also a FAIR affiliate. So here we outline the agenda for today's presentation. We will delve into the AI Act regulation, discussing its timeline and key concept. This structure will help us navigating the complexity of AI governance and ensure compliance with the regulatory expectation while promoting ethical AI practices. Secondly, we focus on our collaboration as Intesa Sanpaolo, which emphasizes research activities, training, and partnership aimed at fostering responsible AI. The AI Act, as everybody know, represents a groundbreaking regulatory framework for artificial intelligence within the European Union. It established harmonized rules for the market, introduction the use of AI system, ensuring that operator adheres a specific obligation. This slide shows the key principles that underpin the AI Act, which are crucial for understanding how we can align our AI initiatives with regulatory requirements while promoting ethical practices in AI deployment. As you know, the regulation is horizontal, so is written cross-industry, and therefore it applies for bank, telecommunication, and other sectors. The regulation protects individuals and their fundamental rights, health, and safety. So systems are classified accordingly to the impact they have on the rights of individuals. The AI Act reserves also an important space for privacy and data protection, repeatedly referencing to the GDPR. Here in this slide, we show you the timeline that provides a comprehensive overview of the key milestones in the adoption of the AI Act. Starting from the European Commission first proposal in 2021, we can see the progression toward the enforcement of the AI Act. So each date marks a significant step into regulatory journey, highlighting the European Union's commitment to establish a robust framework of AI governance. What does it mean? That for us, understanding the timeline is essential for anticipating a coming change and preparing strategies accordingly. The regulation formally came into force on August 2024, 20 days after the publication in the official journal, which occurred in July. Each milestones are not retroactive, except for the milestone on prohibited system that already came into effect on February this year. Among the future milestones relevant to us, we can say the application of GPAI models requirement in August 2025 and the high-risk requirement application in August 2026. This slide shows us that in the upcoming month, the publication of secondary act and technical standard is expected to implement the AI Act. A colleague before, if I don't remember wrong, Caterina, said that the AI Act is the first point, that is the starting point, and this is in reality. Based on the current visibility, we can mention as relevant the GPAI models column. We have GPAI code of conduct. 2 drafts of code of conduct has already been shared, and the 3rd is expected to be published in March, maybe, providing more precise specification for both providers and deployers. And we attend the final version on May 2025. There is also interest in the last pillar, other, in the guidelines on definition of AI systems. In the next slide, my colleague Paolo will provide the definition of AI system as an automated system capable of inference and with a certain level of autonomy. But in practice, what does it mean exactly? So now, thank you for your attention, and over to you, Paolo.
Thank you, Laura. Good afternoon. My name is Paolo Baracco. It's a pleasure to be here. AI system definition. Defining what is an AI system is very important. And following the AI Act, an AI system is a machine-based system that is designed to operate with varying levels of autonomy and generate outputs. In the right of the slide, you can see 7 attributes that define what is an AI system. And probably the most 2 important are, for our understanding, the autonomy and the ability to infer. Ability to infer, I mean the ability to deduce from input data some outputs. I can do an example. I can write a traditional program to determine a decision tree, a simple decision tree, like a sequence of if then else. Or I can use, for example, a Python library, an algorithm, to derive from input data the output. In the first case, I don't have an AI system. In the second case, it's an AI system because I infer from input data some output. So, as I said, in our understanding, the ability to infer, so to deduce from input data the outputs, and the autonomy are the two important attributes to consider in classifying the AI system. Sorry. Sì. Okay. In this slide, I show you the pyramid of risk. The pyramid of risk is a manner to classify the AI system according to the AI Act. On top of the pyramid, you can see the prohibited system. So the system can, for instance, if it's used, can cause physical or psychological damage. In the middle of the pyramid, you can see high-risk system. High-risk system are the systems that are used, for example, in credit score area or in HR area and so on. At the bottom of the pyramid, there are not high-risk systems, like, for example, a spam filtering email. In the middle, covering both high-risk system and not high-risk system, there's a special category. There's the obligation of information when the AI system interact with the individual, with the natural person. So it's applicable for both high-risk system and for not high-risk system. In this slide, I deep dive on high-risk system classification. As a financial institution, we are interested in the bottom left of the slide, so all systems that are listed in Annex 3 of the AI Act. And on the right of the slide, you can see all the categories. And as a financial institution, we are interested in employment, work management, access to essential private services like, as I said before, credit scoring, life as insurance, and so on. And this is a map of the classification for AI system. Generative AI. Generative AI is a special kind of AI that pose also some issues. Generative AI is very rapidly evolving in this time within the AI landscape. And this slide highlights its significance and potential application. As we explore generative AI, it's important also to consider both its innovative capabilities and the ethical implication that it presents. More in details, the use of general purpose AI models embedded in AI system could pose some issues to address, like confidentiality and privacy, hallucination, and intellectual property. So we are currently studying and building safeguards in order to minimize those risks. For example, for hallucination, we have to use some clear disclaimer that the output provided by the system could not always be reliable, accurate, and complete. So we have to pause attention of the output of a generative system. I recall now the main concept then constitute a responsible AI framework. You can see some pillars: fairness, explainability, transparency, human oversight. All all these pillars, for example, for fairness, we have decided to conduct a bias assessment on training data and apply fairness metric on output of the system, of the algorithm. For explainability, as Intesa San Paulo, with collaboration with Centai Institute, we have built an XAI library that could be imported in a code, and the library calls the best explainable for the specific use case. Finally, I would like also to stress that all these controls and checks are included in a resource manager process, which, starting from the inherent risk, determines the residual risk. Intesa San Paulo promotes its commitment by participating in various initiatives, both at European scale, such as the EA Pact, a European project aimed at implementing the requirements of the Act before the regulatory deadline, and also training and research nature. At the left of in the slide, you can see the PNRR Responsible AI Framework, where Intesa San Paulo collaborates with Università of Pisa and Scuola Normale di Pisa to build a responsible AI framework. Another PNRR you can see also on the right of the slide with the University La Sapienza di Roma, where we are trying to build some newer explainer on counterfactuals. And finally, I deep dive on the research activity on responsible AI framework with University of Pisa and Scuola Normale di Pisa, where, as I said before, we want to build a control framework for financial application. I mean that we are currently investigating main issues like data governance, like fairness, explainability, because when we use a general purpose AI model, for example, we don't have access to the training data or validation of test data. And also for explainability, we don't have access to the black box model embedded in the AI system. So currently we are investigating many issues and try to find a solution. Thank you everybody for your time. I finished my presentation. Thank you.
Thank you. Thank you very much for the presentation. I suggest just to really have the other presentation, then we can really have some questions, okay? So I leave the floor to you over here. To the speaker for Deloitte.
Thank you.
Rosa Pierdevan. Thank you.
So, I guess we are the survivor. I promise that I do my best to cut it short, because I know that you're tired, and I will do my best. Anyway, today, as Professor already said, my name is Rosa, and today I'm here representing Deloitte and especially our collaboration with Università di Pisa. And we are working right now on two specific streams, which see involving AI for particular tasks that will have a very important fallbacks in industrial how I can tell, applications, industrial applications. The first one that we're going to see now is the one based on the energy consumption forecasting, which is leveraged on the family of AI architecture, which is the federated learning architectures. And the scope, the main scope of this first stream is the one to developing AI that will allow us to forecast in finding the best trade-off between a good forecast and also use of a huge amount of data without compromising the privacy of that data for a lot of application in energy industries. Just think about that kind of application like the best allocation of energies, or also the better adaptability of the fluctuation demand trends of energetic communities and so on. So because of this, we decided to follow this path with, again, federated learning. And just a quick overview of the kind of phenomena that we are trying to study in this case. We are talking about time series data, and this kind of time series data, as literature reviews also said before me, as you can see in this slide, there are a lot of concerns and challenges that we need to face when we try to forecast this kind of data. For example, the strong variability of data, which belonging with two different realms, but both are very unpredictable and stochastic, such as, for example, the weather. The weather has a strong impact on the energy consumption of a house and a whole community, and also the overall behavior or the family of that users that are spending that energy in that house. So these, among others, are the main challenges that we try to face in this development. So we decided to start with just one model applied on just a single house, and at the same time we're searching for a data set which should comprehend as much data as we can find. And in this case, for this case of study, we choose this one, which is a data set, is an open source data set, which has the first particularity of this data set is that it has resolution of a minute level. So it's a very granular data set that permits us to make this kind of studies at a very particular resolution. And at the same time, it comprehends both data about the consumption, but also the weather. So this data set has been acquired in a small energetic community in Ireland, and it comprehends 20 houses. And in these houses, you can find both normal providers and also houses that leverage both from energy that comes from grid and also renewable energy. So in this data set, you can find also data about charge and discharge of the battery in that cases. Of course, I will cut it short about this. This is how we treat the data, of course, because as you know, especially with this kind of time series data, you need to make a lot of feature engineering and also pre-process your data before to use it for the training of the model. One of these was, for example, to apply sine and cosine transformation just to find some time variables and some trends in our data set. And at the same time, we apply a sort of sliding window on the data. So in that way, was the scope, the aim was the one to feed the model with a span, a sliding window of 8 days, with the aim to forecast the next day, the 9th day, and so on. This sliding window moved on during the days, trying to forecast the consumption day by day. Of course, we tried plenty of models, but with just one main constraint. The models that we tried were all the basic type of models, especially the one belonging to the machine learning families of decision tree, for example, because you know one of the best characteristics and also The constraint itself of federated learning is that you need to put as much simple as possible the model in order to make it could run in all the other utils and can provide the main server just with the weights information. At the end of the day, this is the best result that we had. As you can see, it's not the best because of the metrics. Of course, we choose this as the best, but in order of the metrics that we obtain from each model. And as you can see here, the error, the mean square error is not that much, especially if you think about that we are talking in the order of kilowatt per hour. But at the same time, the R squared is low, so not all the variance is well explained. But at the same time, the topic that I would like you to focus on here are the peaks of energy demand. Because even if we are still not have a proper information about the quantity of that energy demand, so we cannot tell precisely how much energy will be asked in that time when occurred the peak. At the same time, we can tell with a reliable precision where will be the peaks. So we have not a precise quantitative information, but we are in a good way for the qualitative information, which could be already helpful for industrial applications such as, again, the best allocation of energy and the control of the grid of energy. So I just spoiled a little bit of this kind of application, but if this framework works, we can expand this kind of web frameworks on a lot of other industrial implications. Just think about, for example, at the main particular feature of this kind of framework. The thing that I said at the beginning of this presentation, the fact that most of the data could remain private. So think about that kind of scenarios like in health sector, where you can collect the data from patient and you don't have to share that data with other servers, because federated learning works in a way that you just need to provide the new ways to adapt the model which is in the server, and in that way you don't have to provide also the sensitive data of your patients. Same thing we can tell about the financial sector, insurance, energy. Now I go fast because there is this second stream that I want to talking with you, and it's the one about the large language models. As you cannot see here because it's the title is wrong, is again the one from the previous stream, but I will tell you this the scope of this second stream is to perform brand reputation, in this case about European Union, by doing sentiment analysis on Twitter and their respective comments using large language models, small large language models, which we try to make it run on our machine without using internet, and just trying to find out if their performance are reliable enough to perform, again, this kind of brand reputation. So in the future, we expect to have a subscription that will allow us to use an API and get both Twitter and comments from X. But for now, that we still do not have the possibilities to use this API, we find an alternative way to starting to test the performance of the LLM on the local machine. In order to do this, we create a semi-synthetic dataset. Semi-synthetic because the real part, the true part of this dataset was from 12 Twitter, taken from X, just using his query, the hashtag UA. And then we ask to top-tier large language model, so not the same that we are using on our local machine, but another one, in this case, of course, GPT-01, to generate for each Twitter 10 comments. And for these 10 comments, we ask GPT also to provide us the ground truth. For example, if I asked to ChatGPT to generate for me 10 comments, which would be absolutely positive about the European Union, you should also provide me with the ground truth. So with just one shot, we got both ground truth and a generated data set with 144 comments and tweets. So we defined in this way the classes, the 4 classes in which we wanted to classify this sentiment, and at the same time, we fit with this data set the model of Llama on our local machine. Just a little deep dive on the classes that we choose that are positive, negative, ambiguous. When, for example, you have an initial part of your comment which is extremely positive on that topic, but the second part of that comment is also negative, so it's ambiguous and no opinion at all. For example, a comment from ANSA or SkyTG, something like that. The key features of the model that we use on local machine are that it is context aware, that it has multi-attribute evaluation, and also we use a chain of thought reasoning approach. And this is the final outcome of this second stream. As you can see in the first diagram, the first graph, sorry. Except for the positive and ambiguous classes, it seems to be not a good performance of the Llama against the ground truth. But what we think when we saw at first glance, this graphic, this representation, it was, what if that kind of difference in you see the representation of negative class, the red bar, which is the bar of the Llama results, so our results, seems to have almost the same span, more than the negative comments, that no position. So we try to make an in-depth investigation about this topic. We try to find out how many times positive were correctly classified as positive, negative as negative, and so on. And what we found out, it was that actually the most polarized, most strongly opinion was correctly detected, as you can see also in both the central and the right representation. We have an accuracy for positive and negative classification sentiment superior of 95%. And so what we can tell about this, that for now, the most problematic classes are the ambiguous one, the no class one, because for now, the Llama is strictly tends strictly to attribute to give to the comment a positive or negative class. It doesn't have this huge span to choose another kind of position, like no position or ambiguous. But at the same time, it's something that could be fine-tuned by changing the prompt and changing the way we try to make this operation. Of course, this is just the first stage of both streams, and we will improve day by day all the results, going through trying to achieve all the industrial implications, achieve a product that will fit a lot of this industrial implication that basically are almost the same. Like, I want to make you an example of this kind of implication. Think about the energy sector and the energy companies, the provider of energy. Just think when they have to decide, I don't know how to translate it, but the PUN, that index that companies use to that is different month by month, and knowing where the opinion, the global opinion, and all the environment is going on, could help alongside with time series data to forecast also this kind of data. And at the same time, it's something that could be used also for finance sector. For example, for manage better the risk, trying to forecast the next moves of the market. There are a lot of implications in this kind of scenario. So this is what we're trying to do. We are in the first stages, and we hope to go further.
Thank you very much. I think that's we had two very interesting presentations. One focused more about the act and what is the act we really have as impact in the companies, but not only, because also in the research we have to take in consideration, of course, the effect of the act. The other presentation was more on technical aspect and how what we are doing also inside the fair research can help really to develop something that can be really positive for companies. I have questions, but I want to leave really the floor to the others if someone wants just to really make some question. Oh.
Okay. What do you think it's a very provocative, I guess. It's the impact of this UE Act compared to the GDPR. And if you really see a difference, or we are really running for something that in the end will have or not an impact?
But I think that they are complementary, and there are many points of contact. One difference, for instance, is if you think of sensitive data, according to GDPR, you can't use sensitive data. According to the AI Act, if you have to the biasing an AI system classified as high risk, you can treat sensitive data. So there are many points of contact of similarities, but there are also some points that conflict. But you have to consider both in a complementary manner.
Other questions? Okay.
If I can add, because if you ask a company, what do you think about GDPR? They think that you are really asking some burden again, like administrative stuff they have to do, but in the end, we are going to do the same job in the same way. Do you think you really change something the way you are doing stuff in a manner that is different from this previous act? It's a kind of provocative, because if you talk about law, most of the companies say that it's administrative stuff.
It depends, because the act came into force really after 2 August on 2026, when high-risk system came into force. I don't know in this moment what could be the real scenario in the coming months, but I think that the AI regulation is, as I said before, to think in a complementary manner with GDPR. It's not an obstacle to the research, to the innovative project. It's like a standardization. I think so.
Just a curiosity, but the interest related to the act from Intesa San Paolo is just for internal reason, because you use AI system, of course.
Yes.
Or is also, or is for outside, in the sense that if you receive just a company and they want just to get money for some AI system to produce, you want to understand if it's a really responsible AI system or not. So what is the perspective, the main perspective for the bank?
Both of them, because Intesa Sanpaolo can act like a provider and a deployer if we develop, for instance, an AI system. But also we act as a provider when we use GPT or Gemini inside our system. A great implication of the AI Act and the guidelines of AI system definition try to clarify this, but not clarify so much, is, for instance, when you think about logistic regression and linear regression that are mainly used in a risk area. The definition of the AI system clarified that if you use simple linear regression or logistic regression for optimizing method, is not to be considered like an AI system. But if you use in a model more complex, if you have to classify as an AI system. So the boundary, it's not so sure, and the lawyers have to have much work.
Yeah, but there is a big interest in any case for this reason.
Yes, absolutely.
Dino?
If I might add along this discussion, which is very intriguing, what will be the foreseeable impact of the AI Act. According to our experience, and also to the experience that we're doing together with the colleagues at Intesa Sanpaolo, my personal perception is that it's totally different somehow to try to put band-aids on already existing systems that were not conceived within, let's say, a regulation framework, but they have been developed a little bit in the wild. It's a totally different story with respect to designing new AI-based solution within, for instance, within a company like Banca Intesa, which has a very robust innovation capabilities and research capabilities, abilities of, and in a sense, I believe that especially for high risk, where if you look at the prescription of the law, mostly what the law is requiring is good, wise design, in a sense. You simply put together what is very customary for, let's say, well-designed and well-managed software projects. In a sense, the requirements about bias, forecasting, privacy concerns, agency of the people that will be using the system. So it is essentially a way, in my view, if wisely taken, is a way to produce systems that are higher quality with respect to what is customary today. And if we are able, in my opinion, a lot of, let's say, concreteness will be put in these months. There's all this discussion on the code of conduct for associated with the AI Act, and code of practice, sorry, not a code of conduct. And if this will boil down to concrete measure of good process, I think this could be influential for designing a new wave of more responsible AI technology. This is my take. I don't know.
We will have the LLM for developing this type of system in the future. Other questions? Yes, okay. Francesca?
Without getting into too gloomy a territory, but there have been many suggestions that another thing that may change entirely now with the Trump administration is the way this thing unfolds in Europe, right? Because and again, there are 2,000 different views on this, but apparently one big engine behind the fact that the whole tech sector flipped towards Trump was that they know that things are going to change very dramatically faster than expected, and this was a way to ensure that their hands are freer. And of course, also a contentious attitude towards Europe means that they're going to be there saying, okay, we're not bound by what you do, we don't care, back off. Let us be creative and let us destroy and create the way we do it. Any sense of, how this is being absorbed, or whether plans are being adjusted in Europe to try and go down the path of European regulation now that this has changed so dramatically on the other side.
Okay.
I agree.
Other questions? Okay, for Deloitte, what's actually your experience in developing these tools that you really briefly told us? What are the expectations from the point of view of the company about the development of this area of research about the new frontiers of
what
AI?
I can tell is that the company is thrilled because it's something that is brand new in the company. And I'm also thrilled, but for another reason, because this is the first time that I'm on the other side. Because as I already told you, and until last year I was involved with CNR. So for me, it's more familiar, this kind of environment and this kind of approach to research and to development than the other one, the Deloitte one. So what I can see now that I'm collaborating in a brand new way with a corporate, because all these past years that I was into research, it was something that was most of the time just theoretical, and always they tell me, and I also tried by myself, that in the corporate it was completely the opposite. This is the first time that I'm finding something such a hybrid of these two kind of approach, and it's a very good thing, I guess, because there is experimentation, there is nothing just to make the client accomplished, but at the same time, there is a goal at the end. So you just study and research, but at a certain point, you will see developed what you are researching on. And it's true, and I can feel this sensation also all around me in my team. And I don't know if we can transmit this sensation, because I can see that also in my colleagues, David, they both call Davide, so Davide 1, Davide 2, and yeah, it's a very good thing for me.
But okay, Deloitte just work as a consultancy company most of the time. Just make some consultancy with two other companies. So, what is the feeling, in your opinion, about the other companies, the companies with which Deloitte works, about the application of AI? I just explained my question because my impression is that most of the company was to apply AI. Also because today is a brand, no? You are just to use AI everywhere. But most of the time, they, in one side, they don't really have the competencies, of course, just to start, to really implement some new AI system. Yeah. But on the other side, they are afraid, as in some way was explained before, because they don't know exactly what's actually on the one side, the limitation of the act, on the other side, the application of the act.
Well, you know, there is also another thing that I've noticed. Is still that most of the companies are in the stage that need to storage and to clear their data before starting to create AI. So
this is the big problem.
They are even not minding to assume and make that kind of part of the corporate grow, because they are so focused on other tasks that comes previous, that AI generation and AI implication. A lot of companies are more about cloud storage, data processing. I guess that it's a phase that is coming. It's a phase that is spreading now, and it's something that we will see spreading even much more in the next days.
Some comments from Intesa San Paolo about this, or from Dino? No.
I agree. The data quality is the very problem behind the AI Act, because the algorithms are like a commodity, but the quality of data is the fundamental. And if it's not good...
There is, okay, now probably better, but in the past we didn't have this culture of data in the company. They just really collect data, but without really thinking about the use of the data in the future. And this is the big problem that normally you have when you start some collaboration with companies.
A lot of companies didn't see the potential of the data, so they keep on hearing that it was the new petrol, the new big money, I don't know, storage, but cannot properly tell why. When AI spreads in this exponential way in these years, they just find out how important was also make that data in a clear structure, process them, make an order with all that data, and so that comes the problems. So they are still facing this kind of challenge for now.
Thank you. Dino, want just to make some comments?
No, I had a kind of technical question for Rosa Pia De Zana on this prediction model for energy consumption. And I see that you start from households, no? And I believe that the pattern of consumption of different households can be very different, right? So I wonder, there's a spectrum from having a model for every single prediction model for every single household, or having a global model for all of them, or something in between. What is the best strategy here for aggregating this?
Well, you know, not gonna lie, that's why I put a slide inside the presentation where I said there are a lot of drawbacks and challenges, just to say that, yes, it's quite hard. But at the same time, you know, the thing is, it depends on what is your scope. Because if, for example, I just need when I will have a huge peak of demand of energy, I don't care if there is a house that has a peak that which is not that higher, or it's a peak that overall, among the whole the community, will be in that time at that moment. And at that point, it's, as you can see, it's something that could be easier to predict, because I don't want a prediction precise with which respect the perfect consumption hour by hour. But I just need, for example, to set up my grid as a provider to make all the community that is fitted from my energy, that is always covered by my energy. So I don't care if this is just one example. If I decided to pursue this kind of scope, I don't need to make a very high precision, precise forecast. I just need the timing in that forecast. Depends. There are the opposite scope, for example. If I just want what is the higher request that I could have during a day, I don't care when will be the peaks. But I can just try to forecast the maximum amount of energy that they will, the power that they will require. I was mixing up the languages. The power that they will require to me in that moment of the day, or in the day, without thinking about the moment. So you can just focus on the qualitative forecast, quantitative, it depends. That's the perk of working with company, that you already have the point, the scope, and you can set up what you're trying to get from your data just to push that setup. And sometimes it's even easier than simple research. It's for lazy people, not gonna lie.
Thank you.
Thank you. I think that we can conclude. Okay, I remember that we have the poster session.
And the aperitif.
And the aperitif.
You're all invited after such a long day.
So you can just have a drink and you can see the poster. Okay. Thank you very much. Thank you for the speakers.
We reconvene tomorrow morning at 9. So see you then.